I welcome you all on this wonderful platform that is BYJU'S exam prep. Please tell me, am I properly audible and visible to all of you or not? Yes, please tell me that. So guys, today is the marathon for material science. Yes, tell me, am I audible, visible? Okay guys, hello Ajay. So guys, I would like to tell you that as you know, today we are going to have the marathon for material science. Even if you have not studied material science, then also this marathon will help you to learn as per the requirement of the exam. Okay, so we are entering into the material science. Just let me share the session in the Telegram channel. Okay, so then we will start. Okay guys, so Aniket, good morning. Shreyas, good morning. Harsh Kumar, good morning. Lemon, good morning. Ajay, good morning. Aritro, good morning. Darshan, good morning. So guys, whenever we are talking about the material science, as you know, it is in the syllabus of every paper. But when we are talking about GATE is asking from the very limited part, because you know the approach of GATE is going to be generally numerical. Okay, but when we are talking about engineering services or we are having the PSU's exam, they are treating this material science not as a part of production. They are considering it as a separate subject. Like it is also there in ESC paper 1, and for mechanical it is also there in the technical of mechanical or technical part. So guys, yes, mechanical part is going to remain same. Whatever you are going to study, it will help you in all the exam for sure. Yes, for BARC also, but in BARC weightage is less. Okay, the weightage in BARC is less for material science, but for other exams like ISRO and other exams, the weightage is slightly on the higher side. Okay, so guys, we are starting the subject. This is some detail about me. Today's part is related to production somewhere, and why it becomes important. If you see the previous year's trend, from last 3 years the weightage of material science is observed to be very high. Like if you see 2 to 4 marks every year material science is coming. So today's topic is not very big, but as I said, sometime weightage is going to be exaggerated, it is going to be more. So guys, Mechanical by Dheeraj Sardana is the Telegram channel where you will be getting the PDF of this session. Okay, then my dear, this is the mathematics schedule. You will be having on 20-second differential equation, then quantitative aptitude, then calculus, then analytical aptitude, then matrices, then special aptitude, then numerical method. Likewise, we are going to have one topic every day. Good morning Malesh, how are you? So now we are moving further guys. As you know, marathons are going on. So guys, now we have almost completed. SOM is over, FM is over, this is over, this is over, this is over. Machine design is over, industrial is over, engineering mechanics is over, applied thermodynamics is over, HMT. Now HMT, material science today will be over. HMT will be live tomorrow. Okay, tomorrow be ready. Tomorrow you would be having two things. One is vibrations, and when we are talking about vibrations, it will also cover the second part of TOM. And second thing, you would be having tomorrow nothing but the HMT. So be ready for that. Okay, and then we are left with only one last one. Okay, so let us move further guys. Now we are talking about the scholarship test. You know, we are having on 21st of January, you can appear into the test to get up to 90% of the scholarship. Okay, Darshan, okay, I will check that. And then we are going to have on 24th January the workshop how to secure single digit rank in GATE 25. And for this workshop you can register for free if you are preparing for GATE 2025. Okay, and I would also like to tell you one more thing here, that if you want to have one-to-one counseling with our counselor, the link is there in the description of this session. Aritro, that you will get to know tomorrow. Obviously HMT faculties are Suraj sir and Chandra sir, so most probably their combined session would be there. Okay, fine, let us start now. So guys, whenever we are talking about the material science, so before we enter into that, the first thing we need to understand is what is the property. So whenever we are talking about the property, property is defined as the quantitative indices given to the behavior of material. Like whenever you have seen your parents are talking to your relatives and they are telling that let us say I am talking about Darshan, let us say Darshan's relative are telling to the Darshan parents are telling to the Darshan relative that Darshan is a short-tempered person. How they get to know? By looking at, observing at the behavior of Darshan. So I would like to say whenever we are going to see the behavior of material, so it is quantitative indices given to the behavior of material, and behavior can be observed only when some conditions are coming. Like when you get to know who is your good friend, when you have some condition and the person who is going to help you the most, you will find that person is your good friend. Okay. So my dear, that's why I am saying that quantitative indices given to the behavior of material when they are subjected to the external loading. And when I say quantitative indices, I mean some number. Like you say yield strength is 270 MPa. So when you say this is the number you are giving to the behavior of the material. And when you get to know when you are going to load the component. Then my dear, whenever we are talking about why we are interested in properties. So my dear, actually we are interested in the excellent performances. We always want excellent performance from the material. So when we are looking for the excellent performance, that will definitely be depending on the properties. Okay, and properties would definitely be depending on the materials. Okay, or I will say the structures. So property will be depending on the structures. So when we are saying property will be depending on the structures. And when we are talking about structures, structures would be depending on many things. Which are the things? It will be depending on the material. Okay, what material it is. It will also be depending on the heat treatment processes, and it will also be depending on the manufacturing processes. So likewise the things are going to happen. So guys, as we are looking for the excellent performances which are which are definitely depending on structures and these things. So guys, in material science we are going to study these two things basically. Okay, because properties you have already seen in the strength of material. So when we are talking about the structures, structures are defined at three levels. The very first level of structure is the macro structure. The second is the microstructure. Third is the crystal structure. Okay, so these are the three levels of structure. So guys, do like and share the session. So when we are talking about the macro structure, what is macro structure? So my dear, the structure which you can observe from your naked eyes, or you can say if you have a habit to see everything from the microscope, then the level of magnification of microscope should be less than the 100 times. So I said two conditions. Either you are going for the naked eyes, or you are using the microscope, and then you would be having the zoom level to be less than or equals to 100 times. Okay, so then you are going to say such structures as the macro structure. Now you may be thinking, sir, but what is the benefit of going with the macro structure? The benefit with the macro structure is like if you see some structure is like this, then by looking at this you know that there are some sharp corners, and wherever sharp corners are there, you can say their fatigue strength is very less. Similarly, whenever you see a component like this, you see notch is there, you will find that here notch is there, so ductility of this would be very, very less. So by looking at the geometrical characteristics, you are get to know about the surface properties and some other properties. Like here you have told that because of stress concentration, fatigue strength would be less. Okay, and here what you have said? Here you have said ductility would be less. So likewise, by looking at the surface, we can say about some of the properties. Okay, then we are going to have the second type of structure, that is microstructure. So my dear, microstructure means, as the name is having micro itself. So it is the structure which cannot be observed from the naked eyes, but they are seen from the microscope. And here the zoom level of microscope is more than 100 times. Okay, so what we are going to observe from here? We are observing here grain boundaries, phase boundaries, grain orientation, and all these things we are going to see in the chapter number 2 when I will be teaching you the crystal imperfections. Okay, so for this you need to wait, because this chapter is related to the crystal structure. So first of all, we are going to have discussion on the crystal structure. So guys, now we are moving to the third thing, that is crystal structure. So when we are going for crystal structure, we need to say that engineering materials are classified into two categories. Number one is crystalline, number two is amorphous. So my dear, whenever we are saying a material to be a crystalline material, when it follows 3D long range periodicity of atoms, molecules and ions, if it is going to follow 3D long range, 3D long range, periodicity means repeatability, periodicity of what? If you are going to have the periodicity of atoms, then my dear, we will be calling it as atomic solids. We would be calling it as atomic solids, and atomic solids example is nothing but the metals. So metals are the atomic solids. Whenever we are going to talk about the molecules, then we will be calling them as molecular solids. Then we will be calling it as molecular solids. Okay, then we will be calling it as molecular solids, and we are going to call them as polymers. They are nothing but the polymers. And then my dear, whenever we are talking about at the last is nothing but the ions. So they are said to be the ionic solid. They are said to be the ionic solids. And ionic solids are nothing but the ceramics. Okay. So my dear, these are the materials which we are having, and they are having the crystalline structure. So I would like to say, whenever we are saying about the crystalline structure, it is three-dimensional long-range periodicity. Means you will see repeatability in all the three dimensions for very, very long distances. Then we call it as a crystalline material. Now my dear, whenever we are not having this 3D long-range periodicity of atoms, molecules and ions, we call a structure to be amorphous. If you remember, here I used to tell long stories, but here, as it is a marathon session, I will not go for that stories, because here we are we have to complete that subject in, let us say, 5-6 hours, which we were previously doing it in 35-40 hours. So we need to restrict for the stories at least. So here I will tell you when we are going to have the crystalline material, when we are going to have amorphous material. It is like, let us say we are having a classroom, and in that classroom, let us say 500 chairs are there. Okay, 500 chairs are there. And if you are going to have 500 students and you want one student to be sit at one chair, so you need to give the time to them so that they can settle down one by one on over the on the seats. Okay, like if you are going to have in between some seats are empty, so those persons will be going to those seats and they will be sitting down. It is the normal condition. If you will not provide the seat to them and you will say just sit down at one instant, then they cannot reach to the destination. So the point is, if you will be keeping cooling rates slower, you would be having a chance of getting crystalline structure. If you are not going to provide the proper time for solidification, then my dear, you are going to get the amorphous structure. So whether we are going to get crystalline or amorphous structure, it would be totally depending upon whether you are going to provide good time for solidification or not. Okay, everybody understood? Malesh, Aritro, Darshan, Aniket, Ashray, Shreyas, Harsh, Lemon, Ajay, please tell me that. Are you getting it or not? So guys, whenever we are talking about fast cooling rate, you would be getting amorphous structure. Cooling rate is sufficient, you would be getting crystalline structure. Okay, so I already told you about atomic, molecular and ionic solids. Now my dear, we are going to see what are the various constituent of a crystal structure. So whenever we are going to make a crystal structure, in a crystal structure there are two things. When we are talking about the crystal structure, there are two important things here. The very first thing whenever we are talking about is, it is nothing but the crystal system. The very first thing is the crystal system. Okay, and the second thing is brevis lattice. So guys, one is crystal system, other is brevis lattice. Yes, Aritro. So whenever we are talking about crystal system and brevis lattice, what are they? We will be understanding. But before understanding that, we need to understand, like we can see the macro structure from naked eyes. We can see the microstructure from microscope. What about the crystal structure? So I would like to say we cannot see the crystal structure. Crystal structures can only be observed. So crystal structures are observed, they cannot be seen but can be observed by X-ray diffraction experiment. So crystal structures can be observed only by X-ray diffraction experiment. So when we are going for X-ray diffraction, and if you can observe only with that, then my dear, obviously whenever we are saying they are going to be of very smaller amplitudes, that's why we cannot see them. So when we will be observing that, there would be two things. One is crystal system, other is brevis lattice. Crystal system is telling us like you are having a home, So in this home, whatever be the structure, I am showing you top view of the home. So in the top view, let us say this is a room of your parents, this is a room of your grandparents, this is a room of yours, and this is the common area, and here let us say you have kitchen and all, and here would be the entry point. So this is the common area. So this is the structure of the home. I said these are three rooms. So these are three rooms, this is common area, this is kitchen, and then this is the entry gate. This I have told you. So then if I say here 6 people are living, here 6 people are living in such a way that 2 persons are living here, 2 persons are living here, 1 person is living here, and 1 person is living here. There is a servant room, let us say. So now I am telling you 6 people are living in this like that. But 6 people could also have lived like that. One here would be 2. These also can be like all the 6 are in one room only. Yes, it can be. So my dear, whenever we are talking about the structure of the room, yes Danesh, good morning. Whenever we are talking about the structure of the house, it is nothing but the crystal system. So crystal system is telling us about that how a unit cell looks like. How a unit cells look like. What is the geometry of the unit cell? Unit cell is like a home for the atoms. Then my dear, whenever we are talking about how these peoples are living there, that is nothing but the brevis lattice. So brevis lattice is telling us about the atomic arrangement. So how the atoms are living in this unit cell, that is given by the brevis lattice. So my dear, whenever we are talking about how a unit cells looks like, you can see for that we have some parameter. Like this is x-axis, this is y-axis, this is z-axis. So these x, y and z axes are said to be crystallographic axis. Now my dear, these axes are making the angles alpha, beta and gamma. You can say all these are 90 degree, it may not be, it depends. So when we are talking about alpha, beta, gamma, they are said to be interaxial angles. And obviously the sides A, B, C, they are said to be the lattice parameters. So we are having three things, x, y, z, because they are having different angle between each other. They can have 60, 70 like that also. So there are three axes which are said to be crystallographic axis, three parameters A, B, C and alpha, beta, gamma. Some of you may be thinking, sir, why in the material science always alpha, beta, gamma is there? The reason is the work was done by the Greek peoples. So that's why they have used Greek letters. Okay. That's why all the time you study alpha, iron, beta, gamma, whatever this is. Okay. So I would like to say this all will decide how the unit cell will look like. And brevis lattice will tell you that how the atomic arrangements would be there. Now my dear, whenever we are going to have all the materials in this universe, and whenever you will see that what kind of crystal structure, core crystal system or brevis lattice they have. So in this universe, all the materials are going to satisfy with the 7 crystal system. So 7 crystal system and 14 brevis lattice. Okay. So 7 crystal system and 14 brevis lattice are going to be enough to cover all the materials of this universe. You may be saying two doubts here. First doubt is, sir, why not every material is following one crystal structure? So guys, here I would give you an example. Like whatever the number of students here attending the class, do you feel everybody would be sitting in the same way? No. Someone may be sitting like this in front of laptop or computer. Some person would be making some small notes also. Some person would be just lying down on the bed and watching like that, है ना, on the mobile. So here everybody from you is not going to be same. Why? Because you are going to watch the session in a position where you feel more comfortable. So likewise, whenever you are going to solidify any material, then my dear, the crystal system or brevis lattice adopted by that material will be depending on where that material is going to have the minimum potential energy. Like you are going for your comfort level, materials are going for their minimum potential energy, and for that, my dear, the atoms are going to take that kind of system or that kind of Brevis lattice during solidification where they find minimum potential energy, and that totally depends on the configuration of that material, like what is the atomic radius, what are the number of electrons, number of neutrons, number of protons and all. So guys, because of that, whatever the structure they would be taking, it would be depending on where they feel minimum potential energy. So like you are looking for your comfort, they are looking for minimum potential energy, because minimum energy, more stability. Okay, that is the point. Now my dear, second question may be कि whenever we are talking about these 7 crystal system and 14 Brevis lattice, what are they actually? So when we are talking about what are they actually, so here we would be having this table. So we are going to have, like, by going into that, you know, crystal system, you must have studied simple cubic, body centered cubic, face centered cubic. So my dear, whenever we are using this word cubic, cubic refers to the crystal system. And whenever you are saying simple, whenever you are saying face centered, whenever you are saying body centered, this clearly refers to the Brevis lattice. So actually, when we say body centered, when we say face centered, when we say simple, this is telling us the arrangement of atoms. And when we say cubic, it is giving us the geometry of the unit cell. Like when you say cubic, you have all ABC are equal. You have all alpha, beta, gamma are equals to 90 degree. So this is telling us what? Ki interaxial angles are 90 degree, ABC are becoming equal, so cube would be the structure. So this is giving us the crystal system. Now my dear, in that crystal system, let us say I am making it. In that crystal system, let us say I am making it. Okay. So if I am making it like this, if you are having only atoms present at all the corners, if you are having atoms are present only at the corners, then we will be calling it as simple. Simple means all the corners will be having one atom. Then if you are going for the other structure like face center, body center, I am telling you that. So whenever we are talking about body center, in body center also you would be having all the 8 corners having the corner atoms. But along with the corner atoms, you would be having a body center atom also. In the center of the body, you would be having one atom. And similarly, whenever we are talking about the third structure, which is nothing but face center. So here, my dear, you would be having all the 8 corners to have the 8 corner atoms, no doubt about that. So they would be present everywhere. But along with that, here you would also be having the face centered atom. And face center atom would be present at the faces. Like when you will make the face center atom 1 here, 2 here, 3 here, 4 here, 5 here, 6 here. So you know cube is having the 6 faces. So 6 face center atom will also be present. So likewise you can make the face centered structure. Now my dear, we have at the last is end centered. So whenever we are talking about the end center structure, so you must have seen now key corner atom would be present every time. So you would be having corner atoms, 8 corner atoms. Now my dear, I have said this is simple, this is BC, this is FC, this is EC. So end center means you choose any 2 ends of your choice. Either you choose top and bottom, or you choose left and right, or you choose front and back. You choose any 2. You choose any 2, whatever you want. And those 2 would be having atoms. Like if you are saying top and bottom, then top and bottom would be having the face center atom. Then we call it as end center. So it can have only 2 ends can have that. Okay. So my dear, this is about the atomic arrangements. So we have seen these are the types of atomic arrangements, and you can see there are 7 crystal systems. But my dear, till date there is no direct question from this table. So I would not suggest that you have to remember that table. But yes, you need to understand about two structures. One structure is cubic, one system is cubic, other system is hexagonal. Because our majority of the materials are going to lie in these 2 structures, in these 2 systems. And if you are talking about the arrangements, then we will be going for BC and FC. Because these 2 arrangements our atoms are generally having. And the center is generally found in the monoclinic, triclinic. So they are useful for the doctors. They are not useful for our applications. So our concentration would be majorly on 3 things only. One is cubic, hexagonal, and in terms of atomic arrangement we will go for BC and FC. Okay. So this is our concentration will be body centered cubic, face centered cubic, and hexagonal close packed. So these three structures would be in our domain from now only. Okay, is it clear? Everybody is getting? So guys, if you would be with me till 5-6 hours, I am telling you, you would be master of material science for gate. Okay, and even for ESC this part is common, but this is not the total syllabus of ESC. ESC also have some other topics like ferrous material, non-ferrous material, polymer, ceramics, and all those things. Okay, so whatever this we will study, that is a part of ESC also, all PSUs also. So when we are talking about the basic definitions now, so very first basic definition is a unit cell. So unit cell is said to be the smallest part of a entire, but like if you have a material like this. So in this, you know, there are many crystal cells, many unit cells would be there. So this structure is entirely made from some of the unit cells. Okay, so crores of unit cells have combinedly made this structure. So unit cell is the smallest group of atom. Like whenever I am showing this, I will be making the unit cell like this. This is the smallest group of atoms which is going to be repeated for infinite times in all the three crystallographic axes to make the entire structure. That entire structure is said to be the crystal or line lattice. Okay, so you can say unit cell is the smallest part of crystal or line lattice. So when this structure, you know, let us say simple cubic we are talking about. So 8 corner atoms are there. So this is the smallest representative group of atoms. If you are going to repeat this, Ronaldo, this is 5-6 hour session, not more than that. Okay, 5-6 hours, but we will complete the material science. The rule is one only. We will go for the session until it is completed. And if you remember, Ronaldo, tome part was pending, so that we are coming up tomorrow. Tomorrow we would be coming up for vibration and part 2 of tome. So don't miss tomorrow, because we already have planned mathematics from Monday for you guys also, and formula series will also be starting from Monday. Okay, so don't miss the classes. Okay, so whenever we are talking like this is the unit cell. So when we are going to have this unit cell repeated for infinite times in the crystal, in all the crystallographic axis, then we are calling it as crystal or line lattice. Now there is a question coming into the mind of the students. Okay, Darshan, that also we would be planning today only. Don't worry, today by the end of material science, if the time permits, we may go for one more topic today, and if the time would be more already, then we will be planning the second topic on Sunday. Okay, so don't worry. So we will be completing these things by Sunday. So when we are talking about the unit cell, when it is repeated in 3 crystallographic axes, it is resulting into the line lattice. But the point is the line lattice real? The answer is no. When we are talking about line lattice, they are just made for the calculation purpose. Line lattice are made for the calculation purpose. So when we are talking about the actual atoms, actual atomic arrangements, so actually atoms are present as in the space, but these lines are not present. In reality, if you will see, what will be there? In reality, let us say this is one atom, this is another atom, this is another atom. In reality, atoms are in contact like that. Okay, and that I can show you here in 2D, but in reality that would be in 3D. So in 3D, atoms are touching like this because we are considering atom to be a sphere. In reality, this is the condition. Okay, but my dear, when we have these atoms like that, for calculation purpose, what we are doing? We are joining their centers like this. And when we are joining their centers, we are showing these lines only. So when we are like, this is one plane. Behind the plane, one more would be there. Hai na? So like whenever we show it in the form of lines. And we are going to make the atoms like this. But in reality, atoms are not like that. In reality, atoms are touching each other in the space. So this is just for the calculation. This is just for the calculation. Okay, but this is the reality. This is the reality, but whatever I have made is in 2D. This should be repeated in the 3rd dimension also. Is it clear for everyone? Yes. Is it clear for everyone? Yes. Okay. So when we are talking about the space lattice, so my dear, the other structure is space lattice. Whenever we are showing the crystal lattice without lines, like I have just made here, this is the you can say a crystal lattice, or you can say this is a unit cell, and we are showing here atoms like that. But if we show these atoms without lines, then my dear, it would be like this, and that view is said to be the space lattice. And when we are talking about the permittive cell, so I would like to say a simple cubic cell, a simple cubic unit cell is said to be the primitive cell, because this is a very, very basic unit cell. So guys, now we have seen all these things. Now we are coming on to the main thing. Whatever till in the last 30 minutes we have studied, that is just the introduction of the chapter, introduction of the subject, and we have not yet started the points from where questions are coming. From now we are going to enter into the area from where questions would be asked, and that heading is nothing but the characteristics of unit cell. Characteristics of unit cell. So my dear, whenever we are talking about characteristics of unit cell, here you are going to see the same things you have studied in 12th class. A to R ratio, coordination number, atomic packing fraction, allotropy. But guys, when you will see these things, you may not be aware at that time ki why we study these things. Like if I am finding out A to R ratio, what it will give me. So that thing you have not studied previously. So that you would be learning here for the first time. Okay. So my dear, when we are talking about A to R ratio, it is going to be calculated for 3 unit cells specifically. As you know, we need to go for body centered, face centered, and hexagonal close pack. But along with that, I will go for simple cubic also. So I will be going for these 4 calculations. Okay. So first we would be going for BCC, that is body centered cubic. You can see this is the atomic structure of body centered cubic. But before going into that, you need to understand the simple cubic structure. So let us go to the simple cubic structure. So when we have simple cubic, this is how simple cubic looks like. So you can see, I already told you that real atomic arrangement is this one. So you can see in reality atoms are just touching with each other. Okay. And you can see whenever we would be joining the centers to centers, when you would be joining the centers to center, then you would be having this diagram. Okay, but in reality, this and this are showing the reality. Everybody understood how the atoms are there. So if you are going to see in the simple unit cell, you can see that this, I will be showing with the dark color. You can see that this, which you are saying as the lattice parameter A, in the simple cubic everything is A. So if this is A, you can see here this A is just having the contact with the center of 2 atoms. So if I want to find out A to R ratio, you need to take that line where atoms are touching, then only we can find out. So here if you will see, you can see this is the line which is equals to A, and I feel you can feel here that we have the 2 atoms whose centers are present at the corner. So from here, can you say that A is equals to 2R? Please tell me that. From that, can you tell that A is equals to 2R? Please tell me that. When you say this A is equals to 2R, if you want to give me some examples, I would like to say polonium is the material which is having this structure. Polonium, which is having simple cubic structure. So very few elements are following this structure. That's why this is not very important. But A is equals to 2R for the simple cubic structure. Now we will once again go to the body centered cubic. Here my dear, you just imagine कि whatever the previously we were having the 8 atoms like that, if in between these 8 atoms 1 atom is inserted, then can you feel that all the 8 atoms will be going away from each other, because in between when some atom will be inserted, all these atoms will be going far away. So because of that, the structure will result like this. And now you can see, because of this body centered atom, these atoms are not in contact now. 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 You can see the gap between the atoms. And because of this gap, this time we are not going to say A is equals to 2R. Like previously we said A is equals to 2R. This time A is equals to 2R plus some gap. So that is why if you want to find out the ratio of A to R, we need to consider those atoms. Yes, Abdul, very good. We need to consider those atoms which are in contact to each other. So I can see, if I will consider this as one atom, this body center atom as second atom, and this as third atom, then I can feel these three atoms are in contact. So if we are saying these three atoms, the center of one atom is this, the center of third atom is this, and if I join these, so on this line all the three atoms are touching with each other. So if I make this line separately, I would be having body center atom like that, I would be having corner atom like that, I would be having corner atom like that. So you know that this distance is nothing but 4r. This distance is nothing but 4r. But my dear, if we are going to calculate this distance, you know that this distance is a, this distance is a. So this will be root 2a. So this is root 2a. And if this is root 2a, this is a. Then this you can find out by Pythagoras, because this angle is 90 degree. So this would be coming out to be root 2a ka square plus a ka square root. So you would be getting root 3a. So this distance is root 3a. So when you would be equating this, you would be getting a to r ratio is, a would be 4 by root 3r. Is it clear for everyone? Please tell me that. And you can see this is more than 2r. Is it clear? You can see this is more than 2r. So you can very easily say that A is more than 2r. Is it clear or not? Please tell me that. Is it clear or not? Please tell me that. Is it clear or not? Please tell me that. Is it clear or not? Please tell me that. Is it clear or not? Please tell me that. So when you want to say the materials which are showing this structure, then the examples like Arithro have said tungsten, molybdenum, vanadium, okay, all these elements along with the iron. But iron is showing BCC structure except one temperature range, that is 910 to 1450. So when we are talking about this range, in this range iron becomes FCC. And my dear, whenever some element is changing its crystal structure with the temperature and pressure, whenever some element is changing its crystal structure with temperature and pressure, then we are calling it as nothing but the allotropic. So allotropy is the property of showing the different crystal structure at different temperature and pressure. Yes, very good, Abdul. So when we are talking about this allotropy, that's why iron is said to be allotropic iron. Is it clear for everyone? Now my dear, whenever we are talking about this wonderful thing that these are the elements, I would like to say there is an interesting fact about BCC element. BCC elements are also said to be grain size refiners. BCC elements are also said to be grain size refiners. Okay, grain size refiners. Now you may be thinking, sir, what is grain size refiner? For that I will tell you something. What is grain size refiner? So my dear, whenever we are going to talk about, let us say we are having a molten metal of some FCC material. Molten metal of some FCC material. So, okay, so molten metal of some FCC material, and let us say in this you are going to add some particle of BCC. And whenever we are going to add some particle of BCC, I would like to tell you that BCC elements have a bad habit that whenever they see carbon, they make carbides. So when you will be having tungsten, it will make tungsten carbide. Whenever you will add chromium, it will make chromium carbide. Whenever you will make vanadium, vanadium carbide. Okay, likewise they are going to make the structures, they are going to make carbide. So I have written like, okay, chromium is also there, so like that. So my dear, when tungsten is going to make tungsten carbide, it is good and improving the wear strength of the material. When you are adding chromium, chromium carbide is going to be good and it is improving the corrosion resistance. Similarly, vanadium carbide is going to improve the fatigue resistance. Okay, so likewise they are having the improvement in properties like that. So if that is the case, when these elements are kept, they are going to make carbide phases. Carbide phases are always found to be hard phases, because whenever carbon is added, hardness increases. So those hard phases would be present somewhere in between, as you have kept it inside. okay, as you have added them inside intentionally. So my dear, as their hard phases, when this FCC element will start solidifying, you know, solidification front will be running like that. So these solidification front will be stopped by the hard phases. Because they are hard, they will stop it here, and they will allow the next solidification front to move. So because of that, if you will not be adding the FCC element, then maybe you are going to have the grains like that. I already told you about grains in the casting. But because of these hard phases, now they will be stopping everywhere. So they will be present everywhere, and wherever they will be present, they will be stopping. I am making still lesser, but wherever they are present, they will stop the solidification front. So because of that, solidification fronts would be more now, okay? Because of that, solidification front would be more now. Like that. Everywhere they will be stopping the solidification front to extend. And obviously other solidification front will be forming, but they will also be stopped, stuck by that. So can you feel more solidification front would be required? Can you feel more solidification front would be there? Can you feel more number of grains will be there? So when more grains would be there, everywhere they will be stopping the previously coming solidification front. So more number of grains. So in the same previously whatever grains are, now if they are increasing, we will say that grain size is smaller. So grain size is refined. So that's why they are said to be grain size refiner. And they are going to result into fine grain structure if they are going to be present in between. Is it clear for everyone? Please tell me, Akhil and everybody. So that's why they are said to be grain size refiners. But intentionally BCC elements are added to improve the properties because they are having some properties like I have already told you. So when they are forming the carbides, yes, they are increasing hardness and brittleness, but there are some other properties also getting improved. That is the advantage. So guys, do like and share the session. We have just started, and now we are moving to the A to R ratio for the FCC structure. So when you see the FCC structure, just imagine previously you were having the simple cubic. So in between the simple cubic structure, if in between these 4 atoms I will put 1 atom, then all these 4 atoms have to move like that. And because of that, their contact will not be there in FCC. You can see in the FCC structure, there is no contact between these 2 atoms. So once again, I cannot say A is equals to 2R. But you can see this atom and this atom are in contact. So that's why we would be making a line joining all the 3. So I would be making line joining all the 3 like that. And when I will be making that, this is the line. And you can see that one radius is covered here, one radius is covered here, and 2 radiuses are covered here. And this distance, if this is A, obviously this is root 2A. So we can say this distance as root 2A, but that is also equals to 4R. So we can equate it, and you can get A is equals to 2 root 2R. So my dear, this is the relation between A to R. And when we are talking about FCC elements, you can see this is also A to R ratio is coming out to be more than 2. So A to R ratio is coming out to be more than 2 for BCC and FCC elements. Okay. But in simple cubic, we found them to be equals to 2. And whenever we are talking about this A to R ratio, okay, the elements which generally are followed by FCC structures, aluminium, copper, iron in the range of 910 to 1450 degrees Celsius. Then we have gold, okay, generally ductile materials. Okay, I would also like to tell you here, when we are talking about BCC elements, they are found to be hard and brittle. They are found to be hard and brittle. And whenever we are talking about the FCC elements, they are found to be strong and ductile. FCC elements are found to be strong and ductile. They are found to be strong and ductile. Strong and ductile. Is it clear, guys, for everyone? Please tell me that. Is it clear, guys, for everyone? Please tell me that. Yes. Yes, wonderful, guys. Yes. Platinum is there, silver is there. Okay. So all these elements are going to have FCC structure. I feel everybody is okay, and sometimes they are asking this also. So now my dear, we are moving further. We have seen FCC, BCC, HCP, all of them, okay. Now we are going for HCP. This is very important. So when we are talking about HCP structure, so this is having different unit cell. So for HCP, you can see the unit cell is made. If I will make the unit cell by my own, I will be making it like this. Like this. So this is the HCP unit cell. So my dear, whenever we are talking about this HCP unit cell, which is said to be hexagonal closed packed structure. Here my dear, if you see, corner atoms are present at all the corners, like this. Here also at all the corners. And my dear, I would also be having the face center atom at top and bottom face. Up to this, everybody understand it, there is no problem. But my dear, then three alternate faces will be having the body inside atoms. Like let us say if I am taking this, then this, and then this. So these three faces would be having a touching atom. When I am saying touching atom, the center of the atom will not be lying on these planes. Only those atoms will be touching. So when these atoms would be touching, I am saying one atom on this plane, one atom on this plane. Okay, I have made it with the blue color. So then we would be having these three atoms, and they are like the body center atom. Means their center would be inside the body, and they will be just touching these three faces. So if you are asking me, I would say the number of corner atoms are 12, number of face center atom are 2, and number of inside atoms, body atoms are 3. So here this is how the unit cell is going to be defined. And my dear, this plane and this plane, they are very much same. So we are calling them as basal plane. And my dear, whenever we are talking about the basal plane, the gap between these two basal plane is C. And generally C is going to be more than A. It is nearly coming out to be 1.6 times of A. So A is this, the gap between two atoms. You know, here this is not gap between two atoms. A is nothing but A is the lattice parameter. So when we are talking about A and C here, first of all, when you will be finding out A to R ratio, you need to see the basal plane for that. And when you will be checking the basal plane will be coming like this. Like this is the basal plane I am making. It is a hexagon. And what you will find here, that atoms are like this. Okay, atoms are like this, and in between this face center atom. So you can see these atoms are touching with each other. So you can say A is equals to 2R. So the same relation as you have seen in the simple cubic is followed here. But when I am saying that body centered atoms are there, because of that, what is going to happen? The gap between the basal plane is going to be more than A. My dear, here I would like to tell you some basic principle of material science or chemistry. What is that? Just listen to me. You will get a wonderful idea from that. Whenever we are going to have two atoms, you know, in the atoms we have positively charged nucleus. Positively charged nucleus are there, and electrons are revolving around them. So when electrons are revolving around them like this, so you know that whenever we are having these two atoms, then same charges repel each other. So nucleuses will be repelling, same charges will be repel each other, electrons will be repelling. But at the same time, opposite charges will attract each other. So nucleus of one would be attracting electrons of others also, and the vice versa. So when we are going to have between two atoms some attractive, some repulsive forces, then my dear, it is been observed, whenever two atoms are coming closer to each other, then their repulsion increases, attraction reduces. And whenever two atoms are going away from each other, attraction increases, repulsion reduces. So my dear, two atoms wants to be at a distance which is said to be the bond length. There they are having total net force of attraction and repulsion together is 0. And where the net force is 0, that is said to be the minimum potential energy state. So atom wants to be present at that state. So when they will be going away, attraction increases. When they will be going towards, repulsion increases. And in both the cases you would be having instability. And when a person is unstable, he is ready to move. He wants to be stable. Like you have seen, whenever some person is feeling instability in its job, he try to switch, because instability is something which nobody wants. So whenever you find instability anywhere, you will try to switch, है ना? So likewise in the atoms also, whenever they will find instability, they would be having a tendency to become stable, for that they are ready to move. So if you see the HCP structure, here the gap between these atoms are going to be more than A. So when it is going to be more than A, you can say, my dear, attraction would be more in that. So here instability is there in the structure. Because of that, it would be very easy to move the basal planes. And when I am saying it is going to be very easy to move the basal planes, and my dear, that's why they are going to act like the solid lubricants. So that is why, my dear, HCP elements are going to be used like a solid lubricant. Can you tell me what are the various elements which are having this structure? Can you tell me what are the various elements which are following this structure? Yes, what are the elements which are showing this HCP structure? Abdul, because you have told about BCC, you have told about FCC, you have told about simple cubic. What are various HCP structure? Yes, graphite is there. What about others? Graphite, molybdenum sulfide, titanium, very good. Cadmium, yes or no? So we have titanium, cadmium, graphite, yes, magnesium, zinc, very good. Cobalt, very good. So these are the examples of HCP structure. Is it clear for everyone? Is it clear for everyone? Yes. So guys, let us move further. So let us move further. Now, my dear, we are going to have the second characteristic, that is average number of atoms. But first of all, I would like to tell you, actually, whenever we are saying A to R ratio, here A is somewhere telling you about the unit cell size, and R is somewhere telling you about the atomic size. So my dear, as we have defined the property allotropy. So allotropy is nothing but changing of crystal structure on change of temperature and pressure. So that is why you said like iron is allotropic iron. So when iron is allotropic, it will be showing different crystal structures. Sometime it is FCC, sometime it is BCC. So whenever it is FCC, A to R ratio is 2 root 2. And when it is this is A is 4 by root 3R. So when, my dear, ratio is going to change, definitely density will be changing. So density will be the property which will be depending on A to R ratio. So you must be aware of the properties which are depending on separate characteristics. Like why I am interested in A to R ratio? Because I know when A to R ratio will change, density will change. So to tell that effect, I am telling this. Then, my dear, moving to the second thing, average number of atoms. So when we are talking about average number of atoms are defined separately for cubic structures, separately for HCP. So first I would be writing for cubic structure. For cubic unit cell, average number of atom formula is n corner by 8 plus n face by 2 plus ni by 1. Why this is the formula? Because corner atom is shared by 8 unit cells. Then face center atom is shared by 2 unit cells. Then body center atom is not shared by any of the unit cells. So that's why. So whenever we are talking about the simple cubic, in the simple cubic we have corner atoms 8. There is no face center, there is no body center. So NF0, Ni0. So because of that, when you will be finding out the average number of atoms. Why average number of atoms? Because atom is not having the complete part inside the unit cell. So I want to see in one unit cell how much total atom is present. So if you want to find out that, it would be coming out to be 8 by 8 plus 0 plus 0. So answer will be 1 for simple cubic. Similarly, when you are going for body centered cubic, for body centered cubic, the NC is 8, face center atom is 0, body center atom is 1. So you would be saying the average number of atoms as 8 by 8 plus 0 plus 1 by 1. Answer will be 2. Now, my dear, we are having the FCC structure. For FCC structure, the number of corner atom is 8, number of face center atom is 6, body center atom is 0. So when you will be finding out the average number of atoms, you would be having 8 by 8 plus 6 by 2 plus 0. Answer will be 4. So this is about BCC. Now you can see BCC average number of atom is 1, 2 and 4. So when the average number of atom will increase, what is going to happen by that? So I would like to tell you, my dear, more atoms, more bonds. Atoms are there to make the bonds. Good morning, Akshay. So if we have more atoms, we will be having more bonds. And you know there is a basic rule of chemistry that whenever you are going to form a bond, energy is released. And whenever you are going to break the bond, you need to supply the energy. You need to spend the energy. So if more number of bonds would be present, more atoms, more bonds. More bonds, more energy is required to break them. So I would like to say that if the average number of atoms are more, then the strength of the material is more. That's why I said that FCC are found to be strong and ductile. Why they are strong? Because of more number of atoms. So whatever the things I have said, all things are getting proved here. So here you need to understand average number of atoms are telling us about the strength of the component, strength of the material. Okay. So now, my dear, if we are going to see the same for the HCP structure. So when we are going to have the same with the HCP structure, then for HCP structure, you already know there are basal planes, and then we are having the complete structure like this. So you know in the basal plane we have corner atoms. So total 12 corner atoms are there. But what is the formula for that? For HCP structure, the formula for average number of atom is here corner by 6, face by 2, body by 1. So my dear, you can see here corner atoms are 12. We already have seen face center atoms are 2 here and here. And then inside atoms are 3 on the alternate faces, like here, here and here, like this. So I would like to say apply the formula average number of atoms. 12 by 6, 2 by 2, 3 by 1. It would be coming out to be 2 plus 1 plus 3, 6. So my dear, whenever we are talking about all the three, first of all, before we go to the coordination number, I said BCC are found to be hard and brittle. Hard and brittle. I said FCC is found to be strong and ductile. Strong and ductile. Then I said HCP is found to be less strong and ductile. If we go by the rule, here the number of atoms are 2. Here the number of atoms are 4. Here the number of atoms are 6. So as per the rule, as the number of atoms are increasing, strength should increase. Then why HCP are found to be less stronger? Because the same rule can be applied to the same structure, where their crystal system is of different shape. We have HCP. So because of HCP instability of the basal planes, even though more number of atoms per unit cell is there, but still they are going to be lesser strong than the FCC. And that is why we are able to use them as the solid lubricants. Is it clear for everyone? Is it clear for everyone? So guys, these kind of things are coming in the paper. What are the average number of atoms in the aluminium? So you should be knowing aluminium is FCC and you would be answering like that. So guys, now we are moving to the next characteristic, that is coordination number. When we are talking about, we have already covered A to R ratio, we have covered average number of atoms. Now we are coming to the coordination number. Here I am telling you major time would be taken on crystal structure, and after that the time would be taken in the phase diagrams. And in between chapters are not going to take much time, because crystal imperfection I have figures with me. So just by looking at the figure you would be understanding very easily. So the point is whatever time would be required for first chapter and phase diagram, and questions are also coming from first chapter and phase diagram. Okay, and I feel like last year they have asked from the density calculation. This time they will enter more into that, and they can ask the question from Miller indices as well. So be ready for that. That's why first chapter, which will go for 2 to 2.5 hours, is going to be very important. Yes, Pawan Kumar Kota, hi, kaise hain aap? So guys, let us go for the coordination number. Now my dear, whenever we are talking about the coordination number, What is that? So I would like to tell you coordination number is defined as the neighboring atoms. Like one atom is in contact with the neighbors. So whatever be the neighboring atom which are in contact with this atom, we call that as the coordination number. Okay. So what is the importance of the neighbors actually? I already told you whenever two atoms are coming closer to each other, then my dear repulsion increases. Going away from each other, attraction increases. But that happens between all the atoms which are in contact. Like if one atom is in contact with the 6th atom. So if you are going to apply the force on the element like that, then this atom will be going away from the 6 atoms. Then 6 atom will be trying to attract it back. So my dear, what will happen because of that? Like whenever I am going to apply the force onto this material, like you have seen in strength of material. So you know, because of that atoms would be going away from their positions. In the SOM we are applying the load only up to elastic limit, so bonds are not breaking. And when this atom will be going away from the other atom will try to attract it back. So because of that, there is always some attraction force between the neighboring atoms and these atoms. So when the load will be removed, because of that the atom will be coming back to the original position because of those 5-6 atoms. And you know, if after removal of load body is regaining its shape and size, we call that property as elasticity. So the same things in the classes I go for wonderful example which will take 15-20 minutes. Here we will not go like that because it is a marathon session to revise the things. So I would like to say, if we are going to have coordination number more, then my dear, more chances of regaining the shape and size. So more chances of elasticity. So my dear, when we are saying elasticity is the property by which material regain its shape and size after removal of load. It will be more if coordination number is more. But my dear, if you are having too much attraction, maybe let us say you are having too much neighbors, then maybe it is going to be very difficult to remove the atom. Like whenever you are going to apply the force, if a large number of bonds are there, if this atom is having too much neighboring atoms, let us say infinite atoms are surrounding it, then you may not be able to even take it away, even displace it. So that condition is said to be rigidity. So as you know, coordination number cannot be infinite. That is why rigidity is not possible. That's why every element is a deformable only, and you don't have any material which is perfectly rigid body. So when we are talking about coordination number, it is nothing but the number of equidistant neighboring atoms. Number of equidistant neighboring atoms. So my dear, this is said to be the coordination number. So when we will be going for the coordination number, we need to see how much atoms are going to be in contact. Like if I will be making the simple cubic, I will show you for some of the unit cells. Like this is the unit cell. Okay, even I would be making the better diagram. You know, if I will be making like this. So whenever you will see this, let us say you are going to talk about this atom. Then this atom is going to be in contact. You know, in the simple cubic, atoms are touching with each other. So this atom will be in contact with this atom, coordination number 1. It would be in contact with this atom, coordination number 2. It would be in contact with this atom, coordination number 3. It would be in contact with the next atom here, okay, and next atom here. So what is the coordination number for simple cubic? Yes. What would be the coordination number for the simple cubic? Can I say coordination number for simple cubic is 6? Can I say coordination number would be 6 for the simple cubic? Yes, it is going to be 6. Then my dear, whenever we are talking about the body centered, okay, I am making the simple cubic for body centered. Like this. So if you are going to have corner atom, you know that you can see in this diagram also. Here you can see this corner atom. Okay, where is BCC? This corner atom and this corner atom will not be in contact because of this. But body center atom will be in contact with all the corner atom. So that is why as the body center atom will be in contact with all the corner atom, I can say for BCC the coordination number will be 8. Now you may be having a doubt, sir, you are saying that body center is having a coordination number of 8 because you are watching the body center atom. What if we watch the corner atom? So I already told you these lines are made by us. In reality, lines are not there. So whatever the atoms, like let us say you are saying this atom to be the corner atom. So lines are made by you. Even if you are going to start making line from somewhere else, like you are going to make line from the body center atom, then it will become the corner atom. Okay, if you will be starting making line from the body center atom, then it will become the corner atom, and the corner atom will become the body center atom. So the point is, whatever I am telling you with respect to one atom is valid for all the atoms. Okay, so in space the same is valid for all the atoms. So no doubt for BCC, no doubt for BCC, no doubt for BCC you would be having the coordination number to be 8. Is it clear for everyone? Please tell me that. Is it clear for everyone? Please tell me that. Clear for everyone? Please tell me that. बताइए भाई. Yes, tell me guys, tell me. Okay, wonderful guys. So when we are moving for the FCC structure, here let me see if I have that diagram. If I have that diagram, okay, okay, I have to make it. So don't worry, I will make it. But here you can see the field. This is a simple cubic structure. This atom is connected with 6. You can see that. Okay, this atom is connected with the 6. So this is how the coordination number is seen. Now I will show you the FCC. For FCC, the things are going to be very interesting. Let me show you that. So I am making a big unit cell. Why big unit cell? Because I want to show you 8 unit cells together. Just try to understand. This will give you the coordination number of FCC. So I am going to make it like this. So here this I have divided, this I have divided, and this I have divided. Now you can see we are having enough number of unit cells to show the coordination number. अरे यार अरित्रो तुम अभी ले लो ब्रेक, ठीक है, अभी ले लो. ये फालतू चीजें क्यों करते हो क्लास में यार तुम हमेशा? ब्रेक दे दूंगा जब देनी होगी. So when we are having this FCC, when this is FCC, face centered cubic, if we are talking about this corner atom, this corner atom will be in contact with this face center atom, with this face center atom, with this face center atom, with this face center atom. Because you can see in the face centered, whenever we are going to make, you know that this is the face center atom, these are the corner atom. So corner atoms are not in contact with each other, but they are in contact with the face center atom. So that is why this atom will be in contact with the 4 face center atom in this horizontal plane. It will also be in contact with the face center atoms which are available on these faces in the vertical plane. And also actually you are having three planes, 4 planes are these also, so it will also be in contact with this. Actually in the face centered cubic, if you want to understand, we have 3 types of plane like this. This is one of the atom, these 4 face centered atom will be in contact. Another plane is like this. These are 4 atoms, it will be in contact, and then next would be like that. Is it clear for everyone? Is it clear for everyone? Please tell me, is it clear for everyone? Okay, is it clear for everyone? So if you see, this atom will be in contact with these 4, with these 4, and with these 4. So in all the 3 plane, if you see, can you tell me what would be the coordination number for this? Can you tell me what would be the coordination number for this? Coordination number for this is going to be 12. Coordination number for this is going to be 12. 12 आएगा coordination number. Is it clear for everyone? Coordination number will be coming out to be 12. Yes, very good. Very good. So guys, likewise, if you see the HCP structure, if you just see this atom, then you know this atom is in contact with these 3, these 6, and similarly these 3 atoms would be at the top also. So when we are talking about the coordination number of HCP, it is coming out to be 3 plus 3 plus 6. 6 corner atoms, these 3 and these 3 are the body center atom at top and bottom. So total coordination number will be 12. So my dear, I told you coordination number is telling us about the elasticity. So we will be having FCC to be more elastic than BCC, because you know the coordination number whenever we are writing, for simple cubic is 6, for body centered cubic is 8, for face centered cubic is 12, for HCP is 12. Although you are having the same coordination number for FCC and HCP, but still whenever we are saying, they are found to be more and they are found to be less strong and ductile. But whenever we are talking about elasticity, yes, as more coordination number, they will be found to be more elastic as well. Is it clear for everyone? Please tell me. And whenever we are saying that this property is related to that is one of the parameters, that is not the all in total. Like some property may depend on more than 2-3 factors also. Okay, so this is about the coordination number. I feel everybody is understood that. Now we are entering into the atomic packing fraction, which is very important thing, APF, and this is also important for gate 24. Okay, we need no issues. Okay, it is fine. Okay guys, now let us see the atomic packing fraction. So when we are talking about atomic packing fraction, it is very important. Just listen to me properly. Atomic packing fraction actually is telling us that in a complete one unit cell, how much part of the unit cell is filled with the atoms. That is said to be atomic packing fraction. So if we are having a unit cell, in a unit cell, how much part is filled with atoms? You may be saying, sir, what you are saying? Entire part is filled with the atoms? The answer is no. Why? Because I have just shown you many times, like whenever we are going to have the atomic plane like this. So you are making one atom like this, other atom like this, other atom like this, other atom like this. So you know there is some gap present, and that gap is said to be void, and this gap is the area where there is no atom present. So my dear, because of the voids present in a unit cell, we are not having the entire area to be filled by the atom. Always some area is there which is empty in a unit cell. And my dear, if we would be having more empty area, what is the consequences of that we will see. But before that, let us see how the atomic packing fraction is defined. So APF is nothing but the ratio of volume of occupied by the atoms to the volume of the unit cell. So my dear, whenever we are going to see, I have already shown you, this is the, like HCP, I have already shown you these atoms and these atom. Okay, we have already seen that. Now if we are going to define the APF, I would like to say it is volume of average number of atoms. Why average number of atom? Because every atom not completely inside the unit cell. Some part of that is in the unit cell. So average volume of average number of atoms divided by volume of unit cell. So when we are talking about volume of unit cell, first of all we will be talking about volume of average number of atoms is N average into volume of one atom is 4 by 3 pi r cube. Okay, why 4 by 3 pi r cube? Because we are considering it as a sphere. When we say volume of unit cell, it is A cube in case of BCC, FCC and simple cubic, because this is the volume of a cube. So when we are going to apply this formula for simple cubic, face centered cubic, BCC and for HCP, then my dear, these calculations are very important. You may be saying, sir, how we can calculate? Because you know the A to R ratio. For simple cubic, A is equals to 2R. You will put and get the answer. For face centered cubic, you will put as A is equals to 2 root 2R. Here you would be putting A is equals to 4 by root 3R. Similarly, when you will be putting these relations, you would be getting the densities. And I am telling you, for face centered cubic, you would be getting the density to be 74%. Why I am saying density? It is atomic packing fraction. How much part is filled with the atoms? 74% for this, 68% for this, and once again 74% for HCP. Can you tell me for simple cubic, let us say, how many of you remember for simple cubic? Yes, Aniket, Ashray, Ajay, Pawan, Shreyas, Darshan, Akhil. Tell me, anybody remember for simple cubic? Yes, Akhil is saying 52%. Okay, yes. So guys, you can see the density is different, or the atomic packing fraction is different. So if 52% is atomic packing fraction, 48% is empty, 26% is empty, 32% is empty, and 26% is empty. So this much space is going to be empty. So if we are having a atomic packing fraction of 68%, 32% would be empty. So my dear, when we are talking about this empty space, it is just like if you have two homes. In one home, both are same homes, both are same. Everything is same. Same number of rooms, same number of kitchen, same number of bed and everything. If in one home, 6 people are living. In other home, 7 people are living. So you know that where more space is there. More space is available in the home where less number of people are living. So you can say more space is available in BCC than that of FCC. Where more space is available, their effect of alloying element should be more, because we can add more alloying elements. So my dear, that is why whenever you are going to see the effect of alloying elements, obviously for that the good situations, the positive situations are there for BCC, because more number of space is available. But at the same time, whenever a crack will be traveled in a material, atom would be resisting the crack. Empty space will not resist the crack. Like let us say we are having a war with some of the country, like you know India, Pakistan is always having war. Let us say this is our boundary and India, this is Pakistan. So let us say when our army is going to enter, so where Pakistani soldiers will be there, their resistance will be there to the Indian army. So to cross that area, they will take more time. And where there is no person, there is no enemy, it would be very easily crossed. So the point is, if we are saying that in BCC, only 68% is atom, 32% is empty. And in FCC, we are having 74% is atom and 26% is empty. Don't you feel whenever a crack will be traveling in BCC or FCC, in FCC it would be having more resistance and in BCC it would be having lesser resistance. So when the crack will be moving, atoms are not there, there it would be passing very fastly. Because there is no resistance, no atom, no resistance. So my dear, that is why whenever we are talking about BCC, they are found to be brittle, because they are getting failed fast, because crack propagation is going to be faster. And FCC are found to be ductile. They take more time for the travel of crack because more atoms are there, more atomic places there. So that is why FCC is found to be ductile and BCC is found to be brittle. Is it clear? There are many factors. One of them is this. Everybody is getting it. Very good, Kunal. Please tell me everybody is getting it. So here this factor is also going to be very, very important. Is it clear for everyone? Please tell me that. Is it clear for everyone? Please tell me that. बोलो भाई आया कि नहीं? This is very important. This is very important. Yes, very good. Fine guys, so this is about the atomic packing fraction, and I would like to enter into now the next thing, that is nothing but, I already told you that whenever we are talking about ductility and brittle, they are relative terms and that is depending on the APF, and as if we are writing APF, then first thing is ductility or brittleness depending on this, and second thing is effect of alloying element. Effect of alloying element. All these things are written here, and also the notes are shared for the material science in my Telegram channel. There also all these things are there in detail. I feel everybody is clear. Now we are moving to the next thing, and the next thing is nothing but allotropy. I feel everybody know allotropy is the property by virtue of which a component or a material can be there in more than one crystal structure. Sometime it will be BCC, sometime it will be FCC, sometime maybe some other as well. So when it is following different crystal structure at different temperature and pressure, we call it as allotropy. So iron is said to be allotropic iron. Now my dear, when we are talking about the other things, okay, one mock test is still left in the mega mock challenge, which would be live from 27 January to 3rd of February. Do appear in that just before gate. It will give you where you lie between the gate candidates. Okay. Then my dear, now we are going to have the density calculations. Great, Arithro. Structure change with this, yes, very good. Now my dear, whenever we are talking about the density calculation, this is the first type of density from which GATE 2023 asked for the first time. And if you see my last year marathon of material science, you will find I strongly recommended this for the GATE. Ki this time it may ask, because till date there was no question from volume density. So this year I will say, if last year they have asked volume density, this year they can also enter into planar or linear density. So just be there with me. Next 1 hour we will do all the calculations of this, okay, and we would be having break around 2 p.m. okay. So when we are talking about the volume density, what is that? So as the name suggests, density, you know, mass per unit volume generally we say. So volume density is defined as the ratio of, it is the weight of average number of atoms per unit volume. So my dear, I would like to say the weight of average number of atoms, then divided by volume of unit cell. Volume of unit cell. And when we are talking about this, APF and density are different things. In the APF, we are taking volume to the volume ratio. Volume of atom by volume of unit cell. Here this is the weight of atom to the volume of unit cell. So when we are talking about the weight of average number of atoms, we would be writing first of all the average number of atoms. And you know the units for this is atoms per unit cell. Okay. Then my dear, you will be multiplying it with the atomic weight. But you know atomic weight is in gram per mole. Gram per mole. Like you say carbon have 12 gram per mole. So my dear, now volume of unit cell, you know volume is in centimeter cube. I need the final answer in gram per centimeter cube. Gram is there, but mole we need to remove. So I would be saying Avogadro number. Avogadro number is nothing but 6.023 into 10 to the power 23. This is atoms per mole. So from here, if you see mole will get cancelled out. Okay. and you would be getting the answer to be atoms will also get cancelled out. So you would be getting this centimeter cube per unit cell. This is the volume. Unit cell will also get cancelled out. Answer will be coming out to be in gram per centimeter cube. So you need to remember this formula for the volume density, which is nothing but average number of atoms into atomic weight divided by volume of unit cell into Avogadro number. Remember this formula, last time numerical was there from this direct straightforward. Okay, so you may get the question from this. Yes, definitely Shobik. So is it clear for everyone? Everybody is clear for the volume density. Shall we move to the second density calculation? Please tell me. Is it clear for everyone? Is it clear for everyone? Shall we move to the second density calculations? Very good, guys. So now we are going to have the second density calculation is planar density. So planar density is denoted by rho p. Planar density is denoted by rho p. So rho p is defined as nothing but average number of atoms whose centers are intercepted. Whose centers are intercepted. Average number of atoms whose centers are intercepted by the plane divided by the area of plane. So guys, whatever now I am going to start teaching you this, nobody is teaching generally, but I feel this time you may get question from this area, planar density calculation, because last time already they entered into volume density. So they can ask definitely this time from the planar density calculation. And everybody know na that tomorrow we have vibrations marathon, okay? So we are going to have this planar density, and this time units will be gram, or not gram actually, it is going to be atoms per centimeter square. So whenever we are talking about, bilkul Ashray, we will take that. So whenever we are talking about, I need to make a unit cell for that. So if I am going to make a unit cell, just try to listen now. Don't worry guys, everything we will go for. Whatever till now I have promised, I have fulfilled that. Calculator video is there in front of you. Scribble pad video will be coming on Wednesday or Thursday. So be ready for that. So whenever we are having this as x-axis, this as y-axis, this is z. You know this x, y, z always follows the right hand thumb rule. Put your finger towards x, rotate them towards y, this will give you z. So when we are having this, my dear, if I ask you what is the area of plane ABCD? What is the area of plane ABCD? Great Shobik. What is the area of this plane ABCD? Area of plane ABCD. What is the area of plane ABCD? You know that for cubic unit cell all the sides are A, and A. Yes. Very good. You know the area is A square. That's fine. You know that there is one more plane, EFGH. If I ask you a non-conventional type of plane, like if I say what is the area of plane AFGD? What is the area of plane AFGD? Area of plane AFGD. If you see, if this is A, this is A, this will be root 2A. This is root 2A, this is A. What is the area? What is the area? Root 2A square. Yes or no? The area will be root 2A square. So what I want to say from here is, we can also take another area. Let us say I am taking one more area is this, showing with red color. Third area, let us say, is plane EDG. For that area will be different, maybe root 3 by 2A square. So you can see all the planes have different areas. And when these planes have different areas, obviously in the density calculation, this denominator will be changing for different planes. And even when you will go for the number of atoms will also be changing. So if numerator is changing, denominator is changing, obviously the density will be changing. So can I say that planar density would be different for different plane? Like volume density is a one quantity, we have seen one formula, it's fine. But when we are talking about the planar density, it is going to change with the plane. So you know there are many infinite types, infinite planes are possible. But out of those infinite planes, you will find only three types of plane. One is the plane with area a square, other is the plane with area root 2 a square, other is the plane with area root 3 by 2 a square. So majorly our concentration will be on these three types of area. And if you are talking about these three types of area, if we know the density on the area a square, then my dear, you will find there are many planes with the same area. Like if you say plane A, E, F, B, if you say plane B, F, G, C, if you see plane D, H, G, C, all these planes have the same area a square. Like I have made A, F, G, D, the same way is E, B, C, H. So likewise many areas are having root 2 a square. So once if you find out the density for these three areas, I can tell the density at any plane in this unit cell. So that is why I need to concentrate on these three planes, but here it was a need required to identify the plane first. Okay, let us say I know the density on this plane is something, density of this plane is something, density of this plane is something. But for that I need to identify the plane, na? Which plane it is. And for identification Miller came and he said, I will be telling you how to identify the plane. And for that he have given something known as Miller indices of planes, which will help you to identify whether this plane is of this type or of this type or of this type. So for that we are entering into the Miller indices of plane. And when we are talking about Miller indices of plane, for that first of all I am making a unit cell. Okay, I will be making the unit cell where? Let me make this extra slide to make it. Let me add an extra slide to make it. We are here right now. Let me add another slide. Okay. So I would be making a unit cell here where we will be going for the density calculation. Just try to understand, guys, we are entering into a wonderful thing here. This is a unit cell, let us say. This is a unit cell. I am saying x-axis, y-axis, z-axis. Any doubt you can ask me, guys, whenever you find, you need to ask. This is A, B, C, D, E, F, G, H. So when we are going to have this unit cell, and let us say I want to talk about the plane A, B, C, D. So when we are talking about the plane ABCD, you know the area of this plane is A square. It's fine. How the Miller indices are defined? They are rationalized reciprocals of intercept of a plane on all the crystallographic axes. So my dear, this is the table. Just look at it what I said to remember the definition. It is the rationalized reciprocal of fractional intercept on three crystallographic axes. This is how you can remember. So in the reverse order, rationalized reciprocal intercept of crystallographic axis. So you need to see that if we have the plane ABCD, so ABCD is intersecting the x-axis where? Where it is intersecting the x-axis? Can you tell me that? Where it is intersecting the x-axis? The plane ABCD is intersecting the x-axis where? Can you tell me that? That ABCD is intersecting x-axis where? It is going parallel to the x-axis. Where it will intersect the x-axis? At infinity. The thing which is impossible, we consider it is possible at infinity. So you will say that it would be intersecting at infinity. Let me take with the dark color at infinity. Can you tell me the same plane is intersecting the y-axis where? Same plane is intersecting y-axis where? Same plane is intersecting y-axis where? Tell me. Once again infinity. Because it is going parallel to the y-axis as well. So here also I would be saying infinity. And where it is intersecting the z-axis, you will say A. And my dear, here to make calculations or things easier, I would be considering A as 1. Okay, because A is coming out to be a very big number in angstrom. So rather than writing that, we will be assuming A to be 1. So I will say on z-axis it is intersecting at 1. When you will be going for reciprocating this, then you would be getting here, this is 0, this is 0, this is 1. It is already rationalized, so no need to rationalize 0, 0, 1. And you are getting the Miller indices as 0, 0, 1. And Miller indices are represented without a separating comma like this, 0, 0, 1. And Miller said that, like in my index number, you are getting 3 numbers. So if out of these 3 you have 2 zeros and single 1, if you are having 2 zeros and single 1, the position of 1 may change. If you are getting 2 zeros and single 1, then this is the plane for which the area is A square. Means this is this type of plane. So for this you would be having Miller indices with single 1 and 2 zeros. Okay, you can have it like this, 1 0 0. You can have it like this, 0 1 0. You can have it like this, 0 0 1. All these 3 would be having the same conditions. But still I will be showing you one more plane. Let us say we are having this time plane AEFB. So if we are going to have the plane AEFB, it is parallel to z-axis, parallel to x-axis, parallel to x, parallel to z. It is parallel to x, parallel to z. So if I am going to write once again, you know what we are writing. It is rationalized reciprocal of fractional intercept on 3 crystallographic axes. So when you will write the 3 crystallographic axes x, y, z, and when you are going to find out the fractional intercept, it is very easy to say that this plane, whenever we are talking about, is parallel to x and z. So you will say infinite, infinite. And at y it is touching at A, so I can write it as 1. So you will say reciprocal. You will find 0 1 0. So you can say Miller indices for this plane is 0 1 0. And you can see here the area of this plane is also A square. So whatever Miller have said, that was correct only. So whatever plane you are going to have the area to be A square will be represented by a Miller index number where you will have 2 zeros and single 1. Is it clear? Then when Miller was giving presentation over this, at that time some of the person have asked, sir, tell us something about this plane EFGH. This is a wonderful plane EFGH. So when you will be watching for plane EFGH, it is very interesting. Plane EFGH is very interesting. How it is interesting, you can see. This EFGH is touching or cutting at all the points from G to H. So from 0 to 1, every point is intercept. On y-axis also from 0 to 1, every point is intercept. And it is intersecting the z-axis at 0. So what you would be writing here? You would be writing here intercept for x is nothing but 0 to 1 all the points. Okay, I would write from the dark color. 0 to 1 all the points. Here also 0 to 1 all the points. Here it is 0. This time when you will go for reciprocal of 0 will be infinity, reciprocal of 1 will be 1. So you would be getting infinite to 1 all the points. Here also infinite to 1 all the points. And here it is infinite. Infinite to 1 means many points. We call it as indeterminate. And these cannot be rationalized. So Miller indices are coming out to be very bad. Indeterminate, infinity. Here how we will see the number of zeros and number of ones. So when this condition arrives, Miller said that my number is not telling you any technical things, any chemical things. My number is just telling you that which plane it is. So if you want to find that, if there is some plane where you are unable to find out, parallel to that plane will also be same. So he said just do one thing. You just shift your origin in such a way that the same condition should not be there. So if you are going to shift your origin here for this case, only for one case when you are discussing, for any case you are discussing, once you can shift the origin. He have given that power. So once you will be shifting the origin to this will be x-axis, this will be y-axis, this will be z-axis. This time you can see on x intercept is infinity, on y intercept is infinity, on z intercept is -1. So this time if you will write for the same plane EFGH, parallel to x-axis, parallel to y-axis and -1 for z. So you would be writing this time parallel means infinity at x, infinity at y and -1 at z. So you know reciprocal of infinity will be 0, infinity will be 0, it would be -1. So Miller indices would be coming out to be 0, 0, 1 bar. -1 can be written as 1 bar. Once again you can say 2 zeros and single 1. So whenever you find any such issue, you can definitely shift the origin once, but one shift is allowed for one case. Okay, and it is not permanent shifting, it is just a temporary shifting to get the Miller indices. Once again the original origin will be at that point only. Is it clear for everyone or not? Please tell me that. Is it clear for everyone or not? Please tell me that. Is it clear for everyone or not? Please tell me that. बोलो भाई सभी को आया कि नहीं? Do like and share the session guys. We are going for all the details required in this topic because you may get the question directly from this. Okay, so guys, this is how we can find out. Now we will be going for the other cases. Now we will be going for the other cases. Now we will be going for the other cases which are related to the other planes. Okay, so once again I will be making a plane. For that I am going for the extra slide. Okay, so once again I am making for you the unit cell again. Very good, Shovik. So I am making the unit cell again. X-axis, y-axis, z-axis. So whenever we have x-axis, Akhil, first of all I would like to tell you that questions will not be there from shifting, because if shifting will be done, everybody will be giving different answers. So I have just told you shifting, but shifting will not be asked in paper, because if you will go for different shifting, I will be going for different shifting, everybody will give different answer. So in GATE, MCQ, they cannot ask that. Okay, so that is why whenever we are talking about shifting, shifting should be such that the same problem should not appear again. Okay, but don't worry, if required I will show you again. So when we are talking about this, once again a unit cell, you know, once again this is ABCD, this is EFGH. So this time, my dear, let us concentrate on some other plane. What is that plane? This time we are concentrating on a plane that is AFGD. This time we are talking about a plane AFGD. AFGD. So when we are talking about this plane AFGD, so can you tell me what is the intercept on x-axis, y-axis and z-axis? Can you tell me the intercept on x-axis, y-axis and z-axis? You can see intercept on x-axis is 1. Intercept on y-axis is infinite, never. Here it is once again 1. So can we write intercept on x-axis is 1, infinite 1. So 1 by 1, 1 by infinity, 1 by 1. Answer will be 1, 0, 1. Can you see this time we are getting 2 1s and single 0. When you are getting 2 1s and single 0, then you will find the area of plane to be √2a square. You will be finding the area to be √2a square. You will be finding the area to be √2a square. Clear for everyone? Clear for everyone? Please tell me that. Clear for everyone? Please tell me that. Clear for everyone? Please tell me that. Okay guys, so Miller indices would be 101. That is the answer for this. Then my dear, we are going to see one more plane. Let us say we have a plane like this. We are having a plane DEG. If we are having the plane DEG, you can see here also one, here also one, here also one. So we can write intercept as 1, 1, 1. Reciprocal also 1, 1, 1. Rationalize also 1, 1, 1. So Miller indices also will be coming out to be 1, 1, 1. So for plane EGD, Miller indices will be 1, 1, 1. Whenever you have this, you can see this is a equilateral triangle. All the sides are root 2a, root 2a, root 2a. You know the area of this type of triangle is root 3 by 2 side ka square. So you would be getting it to be, what is the area we are getting? What is the area we are getting? Yes. I feel some mistake. Root 3 by 4. So answer will be root 3 by 2a square. Clear for everyone? Clear for everyone? Yes, Ashray. Very good. So guys, if you have 3 ones, the area will be root 3 by 2a square. Root 3 by 2a square. Yes. So guys, now we have seen all the areas. Now we will see the density calculation once again. And you know Miller indices we have completed. Now there are some characteristics of Miller indices. Like when a plane is parallel to an axis, its Miller indices are 0 on that axis. You can see with the example. Here you can see, like we were getting 0, 0, 1 for this. Like we were getting 0, 0, 1 for this. What is 0, 0, 1? If we are going to have any plane like ABCD, it is parallel to Y and Z. And if it is parallel to Y and Z, you will be knowing that Miller indices are coming at 1, 0, 0. So if a plane is parallel to some of the axis, if a plane is parallel to some of the axis, its Miller indices on that axis will be 0. Then my dear, the two parallel planes have similar Miller indices. Like if we are having the unit cell like this, you have just seen that Miller indice for this plane was coming out to be what? For this it was coming out to be 0, 0, 1. It was coming out to be 0, 0, 1. And for this plane, which is at the back side, for this plane Miller indices came 0, 0, 1 bar. So you can see they are similar. 2, 0, single 1, 2, 0, single 1. The position of 1 is also same. So that is why I said if two planes are parallel to each other, they will be having the quantitatively same Miller indices. Means even the position of one will remain the same. Then we have the angle between two planes. If we have one plane denoted by H1, K1, L1, second plane denoted by H2, K2, L2, then you will be writing the angle between these two planes with the cos theta. Cos theta would be coming out to be H1, H2, K1, K2, L1, L2. Then in between the bracket square root of H1 square plus K1 square plus L1 square, H2 square plus K2 square plus L2 square. Actually outside some sound is coming, don't worry. It is for 1 minute only. Okay. Is it clear guys? This is how you can find out the angle between two planes. And if this H1, H2, K1, K2, L1, L2 will become 0, then those two planes are perpendicular to each other. Because when you are going to have cos theta 0, it will be giving you theta to be 90 degree. Okay. Like we have two planes, one is 1, 0, 0, other is 0, 1, 0. They are going to be perpendicular to each other because their product would be coming out to be 0. Clear for everyone? Clear for everyone? If any point you find any doubt, you can ask me. As it is marathon session, I am going in that way only. Okay. So I feel these points are very much understood. Next, my dear, if you want to find out the distance between two planes, out of which one is lying at the origin. Yes, Shobik. So when we are talking about interplanar distance, if you want to find out the distance of a plane from the origin, or you can say distance of a plane from other plane which is lying at the origin. So if you want to find out the distance of a plane from the origin, it is said to be interplanar distance. And the formula for that is D is equals to A by square root of H square plus K square plus L square. Like you have a plane, you want to find out for 1, 0, 0. So for 1, 0, 0, it will be coming out to be A divided by 1 ka square plus 0 ka square plus 0 ka square. Answer will be coming out to be 1. Is it clear for everyone? Now I am going to show you 1 to 2 calculations on that, because we can have question from this formula also. Be ready. Very good, Vinay. So I am showing you that. Okay. Before we go to the calculations, let me show you some wonderful things. Let us see. So guys, I am making a unit cell like this. Like this. You already know, if I want to write the Miller indices of plane ABCD, can you tell me the Miller indices of plane ABCD? If you are saying about plane ABCD, you can see this plane is parallel to X and Z, or X and Y axis. This plane is parallel to X and Y axis. So if this is parallel to X and Y axis, Miller indices on that will be 0, we know that. So 0, 0, 1. Okay, and if I want to find out for the plane, a new plane is coming into picture now. PQRS. In such a way that this distance is A by 2. So this time when you will be going for intercept, you would be writing infinity, infinity and 1 by 2. When you will be going for reciprocal, 0, 0 and 2. It is already rationalized, so Miller indices is 0, 0, 2. So ABCD is 0, 0, 1, PQRS is 0, 0, 2. If you are going to find out the distance of this from the origin, it will be coming out to be A by square root of 0 ka square plus 0 ka square plus 1 ka square. It would be coming out to be A. If you are going to find out the distance of this, it would be A by square root of 0 ka square plus 0 ka square plus 2 ka square. It is A by 2. So can you tell me which plane is away from the origin? 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 You know this plane is away from the origin. But who is having the more index number? This is 2, this is 1. So can I say more index number means near to the origin? Can I say more index number means near to the origin? Can I say more index number means near to the origin? So if a plane is having more Miller index number, it is near to the origin. Yes. So my dear, this point is very important. The plane with low index number are far away from the origin than that of those planes which are having high index number. So everything is written here, don't worry. Okay guys, now we are finally coming to the planar density calculations, and I am telling you, after these calculations we will enter into linear density, and once this will be over, in next 1 hour we are going to complete this chapter, and next 1 hour will be of crystal imperfections. So after crystal imperfection we will take the break, and then phase diagram and iron carbon diagram we will see after the break. Okay, and I feel most probably we would be able to complete it by 4 PM for sure when we are talking about material size, and at that time we will decide. अगर आप में जान होगी तो अगला टॉपिक पे जाएंगे, जान नहीं होगी तो आप डिसाइड करेंगे अगला टॉपिक कब करना है, ठीक है, बट मटेरियल साइंस आज पूरा होगा. So when we are talking about, my dear, planar density calculation, first let us go for the body centered cubic structure. First let us go for the body centered cubic structure. So my dear, whenever we are talking about BCC and FCC, we need to consider a plane. We are talking about a plane with single 1 and 2 zeros, single 1 or 2 zeros. These types of plane we will be talking about first. Okay, and you know, when we are going to make the unit cell like this, okay, this is unit cell, and for BCC everybody is aware that atoms are present at the corners like this, and body center atom is there. So when we are talking about the plane, these types whose area is a square, so I feel I can take plane ABCD. If you are going to consider the plane ABCD, you know that here one atom, two atom, they are not touching atom because they are touching with body center atom, and the density of planar density says that the number of atoms whose centers are intercepted by the plane. So you know that body center atom will not be having the center on this plane ABCD, so that will not be counted here. So you can see this atom is having 1/4 part. Why 1/4 part? You were knowing that every atom is having 1/8, corner atom is having 1/8 part. But when we are going for planar density, we will be considering atom not as a sphere but as a circle. So if you will consider it a circle, 1/4 part will be coming in a unit cell. Every circle will be having 1/4 part. So when you are going to find out the planar density, average number of atoms whose centers are intercepted by the plane divided by the area of the plane. So you can see here 1/4, average number of atom is 1/4 into 4. Area is a square. So density is 1 by a square. Please tell me everybody understood or not, then we are moving further. Do like and share the session, guys. Now we are entering into wonderful part. This will be coming in GATE 2024 for sure. Be ready. So density is 1 by a square. Now if we are going for the same for FCC, you know, for FCC unit cell we would be having the atomic arrangement different than BCC. We will be calculating for FCC BCC only, and we are having all the corner atoms like that, and also we have the face centered atoms at all the faces. So when we are talking about the same plane ABCD, when we are talking about the same plane ABCD, so you know corner atoms would be like this, and face center atom will also be touching them like this. So you will consider atom as a circle, then you will find entire circle is inside the plane, and here 1/4, here 1/4, here 1/4, here 1/4. So what is the average number of atoms? 1/4 into 4 plus 1, 2. So density will be coming out to be 2 by a square. Please tell me everybody understood about this or not. Then we are moving further. Very good, Ashray, Vinay, Prakash, Shovik, Kunal, Akhil, Shreyas, Ajay. Yes, Akhil, very good. So moving further, guys, we are going to see now the second plane. When we are talking about the second plane, now we will say this is EFGH. Now we will be going for AFGH. AFGH. When we are talking about AFGH, then you know for BCC this time entire body center atom will be lying here, and obviously the corner atoms like that only will be present, and we need to consider them as the circle. So 1/4 of this, 1/4 of this, entire part of this, entire part of this, 1/4 of this, and 1/4 of this. So when you will be going for the average number of atom for this case, it would be 1/4 into 4 plus 1. It will be 2. And density will be coming out to be what? 2 by root 2a square. Please tell me, is it clear or not? Please tell me it is clear or not. Please tell me it is clear or not. Very good, Malesh. So now, my dear, we will be going to the third plane, that is DEG. So when we are going to have DEG, this plane, then, my dear, here there is a confusion between the students that, sir, whether the body center atom will be lying on this plane or not. So the answer is body center atom will not be lying on this plane. Body center atom will not be lying on this plane. Body center atom will not be lying on this plane. Why? Because this plane is having the Miller index number as 111. When you will find out the interplanar distance, it will be coming out to be A by 1 ka square plus 1 ka square plus 1 ka square. It would be A by root 3. It would be A by root 3. And if you are going to make the origin like this, you know, one atom is at corner like this, other atom is going to be body center atom. So the gap between these two atoms is coming out to be 2r. Okay, and you know that A is equals to 4r by root 3. So A is equals to 4r by root 3. It would be coming out to be 4r by 3. 4r by 3 is nothing but 1.33r. So you can see, my dear, this plane will be passing from somewhere here, which is at a distance of 1.33r. So plane will be passing from somewhere 1.33r. Plane will be passing from somewhere 1.33r. And this center of the atom is at 2r. And I told you only those atoms will be counted whose centers will be lying on that plane. So that is why, my dear, body center atom will not be lying on the plane 111. So that is why if center is not lying, we will consider atom is not lying. Only those atoms are considered whose centers will be lying on the plane. So when we are going to calculate for that, you know, it is equilateral triangle. So angle is 60 degree. So this time you can say only 1/6 of every atom is there. 60 into 6 is 360. So 1/6 of every atom is 1 by 2. And when you will be going for planar density calculation, average number of atom is 1 by 2. Area is root 3 by 2a square. Answer will be coming out to be 1 by root 3a square. I feel everybody is clear with this. Any doubt any student is having, please ask, because this question can be asked from this slide. This slide is very important for gate 24. Gate 24, yes. You may get direct question from here. Is it clear for everyone? Please tell me that. Anybody have any doubt? Please ask. Okay. Moving to the FCC now. For FCC, we have already calculated this one density. Now we are going for the plane. Now you need to be very, very concentrated. We are going to find out the density for AFGD. Here, no doubt, we would be having, you know, this plane. In this plane, corner atom, everybody know, there is no problem. But students are forgetting about the face center atom. This face center atom, half is lying on this, half is lying on this, like this. So this time 1/4, 1/4, 1/4, 1/4, half, half. So when we are going to find out the average number of atoms here, that would be coming out to be 1 by 4 into 4 plus 1 by 2 into 2. It will be coming out to be 2 only. So density will be nothing but 2 by root 2a square. Wonderful, guys, wonderful. Now we are going to have the same thing for the third plane, this time DEG. If you are going for the plane DEG, DEG. This time if you will say once again, this is the plane with the red color I will show, DEG. So on DEG we would be having these corner atoms for sure and also these face center atoms. So when I will be making it like this, you know that I would be having corner atoms and face center atoms. Corner atoms 1/6, 1/6, 1/6. Face center atom 1, 2, 1, 2, 1, 2. So you would be finding out the average number of atom. It would be coming out to be 1/2 into 3 plus 1/6 into 3. It is coming out to be 2, and the density would be coming out to be 2 by root 3 by 2a square, 4 by root 3a square. We have completed all the density calculation. Here I am writing the plane, here I am writing the FCC, here I am writing the BCC. We have calculated for 3 types of planes. When you will see the FCC we have calculated here. Sorry, BCC. BCC is having 1 by a square, 2 by root 2a square, 1 by root 3a square. So 1 by a square, 2 by root 3a square, 1 by root 3a square. For FCC we have 1 by a square, sorry, 2 by a square, 2 by root 2a square, 4 by root 3a square. Now my dear, if you will be just looking at where we are getting the maximum density, I am not saying you can remember these value, choice is yours. You can remember or you can calculate based on the question coming. Choice is yours. So when you have these data, can you tell me for FCC where we are getting the maximum density? For FCC where we are getting the maximum density? Within next 15-20 minutes chapter will be over, and then we will enter into crystal imperfections. Tell me. So guys, which of these 3 will be having the maximum density? You can see this is the maximum value, 4 by root 3a square, and here this is the maximum value. So my dear, for BCC, this is for BCC and this is for FCC. They are found to be the plane with the highest density. You may be saying, sir, why we are interested in these planes? Because if these planes are having maximum density, you know, more number of atoms are present here. And if more number of atoms are present here, the gap between the atoms will be lesser. And if gap between the atom will be lesser, the distance, the stability required for 2 atoms is nothing but the bond length. So atoms are coming closer to each other, they will be feeling instability. And because of instability, it will be very easy to move these atoms. So that's why whenever you are going to apply the forces on a material, the atoms which are starting moving or slipping, that is happening at these planes only. That's why these planes are said to be slip planes. And if slip planes are more, the tendency of slip is more, material is going to be more ductile. Is it clear for everyone or not why I have done this density calculation? Because ductility is depending on this. You may be saying, sir, ductility was depending on APF. Yes, it is also depending on APF, it is also depending on this. Some properties are depending on more than one things. So guys, this was the consideration of the planar density calculation. Now within next 15-20 minutes we will see linear density calculation, and next we will go for 1 hour, 1.25 hours for imperfections. Then we will go for break, and after 30-40 minutes break we will require 20 minutes for strengthening mechanism, 1 hour for phase diagram, 30 minutes for heat treatments. So likewise we are going to move ahead, 4:35 maximum. Okay, and then we will decide if we will be having more energy, we will go for one more topic. Okay, so moving further guys, for linear density calculations. Now my dear, this is the third type of calculation. This is easier, this is not taking much time. So when we are talking about the linear density calculation, you would be making a unit cell like this. you would be making a unit cell like this. X-axis, Y-axis, Z-axis. I am calling this plane as ABCD, EFGH. So when we are talking about AF, ABCD, EFGH, now we are going for the linear density calculation, and it is defined as, once again, average number of atoms. It will be average number of atoms whose centers are intercepted by the vector divided by length of the vector. So previously we were saying divided by area of vector, now we will see the length of the vector. So when we are talking about this linear density calculations, we are having three types of vectors. And for that, like if I ask you what is the length of CD vector, you will say the length is A. If I ask you what is the length of HC vector, you will say it is root 2A. If I ask you what is the length of HB vector, you will say length is root 3A. So if the length of every vector is different, for sure the density will be different. So my dear, that is why once again we would be having three types of vector. One vector with length A, other vector with length root 2A, other vector with length root 3A. And you know, we are having such large number of vectors. Like this is also having A, this is also having A, this is also having A, this is also having A. So there are many vectors with A, root 2A and root 3A. So that is why once again Miller came into picture and he said, I will be giving the Miller indices for direction. And when Miller indices for directions are given, they are helping us in identifying that whether this vector is with length A, with length root 2A and with length root 3A. So it is going to help us in identification of the vector. And for that purpose, what is the procedure? It is very simple this time. This time he is saying it is nothing but the rationalized component of coordinate. What do you mean by that? I am telling you. Let us say you want to talk about a vector which is nothing but vector DC vector. So when you are considering vector DC, you will be considering D to be origin. This is the vector DC, na? D would be origin. And if D is origin, what is the coordinate of C? Coordinate of C is nothing but, this is in X direction. So 1, 0, 0. So nothing, it is already rationalized. So you would be writing vector DC have a Miller indices of, in the body bracket, it is 1, 0, 0 without a separating comma. If you are saying, I am interested in some other vector, sir, why DC? I am interested in a vector which is nothing but, let us say EF. So if you are interested in vector EF, what you will do? Assume E to be origin, it is once again 1, 0, 0. So you would be saying 1, 0, 0. So coordinate is already rationalized, so you will be saying 1, 0, 0. You can see these directions are parallel, they have same Miller indices. Similarly, we can go for one more vector. Let us say we are having the vector this HC. H is origin. What is the coordinate of C with respect to H? You would be writing this H is origin. So if this is origin, you know we are traveling this much in X, this much in Z. So 1, 0, 1. So you would be writing for HC as 1, 0, 1. If you want to write for HB, H is the origin, you know it is 1, 1, 1. So for HB vector, Miller indices will be 1, 1, 1. And if Miller indices are coming single 1 and 2 zeros, the length is A. If it is having 2, 1 and single 0, the length is root 2a. If it is having all three ones, the length is root 3a. You can tell me any other vector if you want to ask. Yes, Arithro, do you want any other specific vector to be described here? Any vector if you want me to describe here. Lemon, Ajay, Kunal, Akhil, Ashray, Akshay, Shreyas, Darshan, Vinay, Shovik. Any vector if you particularly want me to write Miller indices. Any vector. Okay, like if you are saying, sir, what about this vector Fg? Then I will consider this vector F to be origin. Then what will be this? You are going in the negative y. So the coordinate of this will become what? In x direction 0, y direction -1, z direction 0. So you would write 0, 1 bar 0. This is for Fg. So one point will become origin. Okay. So if you want to write about HA, H is origin. H is origin, then H is origin, you are moving in this direction and this direction, Y, Z, 0, 1, 1. So you would be writing for HA 0, 1, 1, as it is already rationalized. If it is not rationalized, you will be going for rationalization. For AB it is simple, Akhil. For AB, A will become origin, B would become 1, 0, 0. So Miller indices will be 1, 0, 0. Ha, Akhil, yes, here there is no problem. Here there is no problem of intersecting. Because here what we are doing, we are not going for intercepts. What we are doing, we are writing the coordinate assuming one tail end as origin. So here that problem will not come which was coming in the planes. Okay, like if you are talking about AG, there is no problem with AG. This is AG now. So A will become origin. What is G? You are going in positive x direction, negative y direction, negative z direction. So if you are talking about AG, the coordinates of G would be coming out to be what? It would be in x, you are going +1. In y, -1. In z, you are going -1. So it would be 1, 1 bar, 1 bar. Clear, Kunal? अरे भाई कोई भी बना लो. Here the good thing is that origin is every time changing. So every time origin is not the fixed one. That's why here that problem will not arrive. Okay. So as origin is in your hand, then there is no problem. Previously problem was origin was fixed. Okay. So now we are going for the linear density calculations like we have done the planar density calculation. So we have already defined it, rationalized component of the given direction vector. Okay. So you just need to put the coordinate in terms of rationalized format. Now my dear, we are going for FCC and BCC. Okay. So we have already written many coordinates. Now we are going for the directions, characteristic of Miller indices of direction. If you remember, when a plane was parallel to some of the axes, Miller indices on that axis was 0. Here it is opposite. When a direction is perpendicular to an axis, Miller indices on that axis is 0. I am showing you that. You can see, when you see this vector DC, it was perpendicular to Z. It was perpendicular to Z. So you can see it was perpendicular to Z, perpendicular to Y. So Miller indices were having 2 zeros. If you are talking about EF is perpendicular to Y, it is perpendicular to Z. So you can have 0. If you are talking about HC is this is perpendicular to Y only, perpendicular to Y only. So you have 0 here. If you are talking about HB is not perpendicular to anyone, so there is no 0. Okay, so every characteristic can be felt like that. Two parallel directions will have same Miller indices, we have seen that. Two direction U1, V1, W, U2, V2, W, the angle between them is given by that, the same formula again. If one direction vector and a plane, you know that if you are going to have U1, V1, U1, U2 plus V1, V2 plus W1, W2, if this is coming out to be 0, angle between those will be 0. If you are having a vector UVW, vector is represented in this bracket, and a plane HKL in such a way that H is equals to U, V is equals to K, L is equals to W, means they are same, then they are perpendicular to each other. If a direction vector and a plane are having same Miller indices, it means they are perpendicular to each other. I can show you that as well. Like if you remember, when we have written about this plane A, B, C, D. So when you have written A, B, C, D, it was coming out to be 0, 0, 1. This was the Miller indices. And now if you are going to write about a direction, let us say DH. If you want to write about DH, for DH, you will be writing DH as this is origin. You are going in negative Z. So it would be having 0, 0, -1. So Miller indices will be coming out to be 0, 0, 1 bar. So you can see 0, 0, 1 bar and 0, 0, 1 are same. So they are perpendicular to each other. हाँ भाई, most probably it should come. ME, it should come definitely. So don't worry about that. Is it clear? Yes, Shobik, you can say that. Now my dear, we are going for the density calculation. Okay, this is the last part of chapter number 1. After this density calculation, I would be saying that crystal structure is over. So just listen to me properly. Okay, and then we will enter into crystal imperfections. Okay, and after imperfection, Aditro, we will give break. Okay, you wanted to know about break, na? So I am telling you. So we are having linear density calculation. So for linear density calculation, we would be going for, once again, first of all, unit cell like this. Okay, ABCD, EFGH. Here we are talking about FCC. In the next slide, we will see about BCC. Okay, first of all, I am making the FCC, you know, all the corners atoms, all the face centered atoms, like that. Now we will be talking about three directions. One we will be talking about of this DC. So when we are talking about DC direction, this would be a direction with 0, 0, 1, 0, 0. Sorry. 1, 0, 0. You tell me about DC. This is DC. This is origin. What is the coordinate? In X direction you are moving. 1, 0, 0. So am I correct? The direction vector for this is 1, 0, 0. Even whatever density I will calculate, that will be valid for 0, 0, 1. That will be valid for 0, 1, 0. So it will be valid for all these types of vectors. If you are talking about this, on this only and only corner atoms will be coming. So you can see this is the distance and this is 1 radius, this is 2 radius. So the linear density will be coming out to be, this is half atom, half atom. Average number of atom will be 1 divided by A. Is it clear? Clear for everyone? Any doubt? Any doubt anybody is having? Please tell me that. Any doubt anybody is having? Please tell me that. Then my dear, we can also talk about a vector which is, let us say, HC. So when we are talking about this HC vector, here you would be having corner atom, face center atom and corner atom. You know the length is root 2a. The length is root 2a. And you can see this is the type of vector which would be having 1, 0, 1, 0, 1, 1, 1, 1, 0. For this you can see the average number of atom is half atom this, this is complete. So 1 by 2 into 2 plus 1. Total is 2. So the density will be coming out to be 2 by root 2a. Then we would be having the third vector with the different color. This will be HB. HB. So when we are talking about HB, on HB only corner atoms will be coming because there is no body center atom in this. So HB will be having only 2 atoms. Average number of atom is 1 by 2 into 2. Length is root 3a. You know that. This is root 3a. If any doubt you have, please ask. If you find I am going faster, you can stop me there. This is going to be 1 by root 3a. So we have done all the calculation for FCC. Any doubt you can ask me. Ashray, Shreyas, Akhil, Shovik, Aritro, Emi, Ajay, Kunal. Yes. So we have done it in this slide only. For this year, calculations are important. We are going for the BCC now. So when we are going for the BCC, the same calculations once again. You know here corner atoms and the body center atom. So when we are talking about this is A, B, C, D, E, F, G, H. So first of all we will be going for the vectors with 0, 0, 1, 0, 1, 0. So let us say we are talking about CD vector. For CD, only corner atoms will be coming like this. So average number of atoms is nothing but 1 by 2 into 2. And length is A. So density will be 1 upon A over. Second type of vector is 1, 0, 0. Sorry, 1, 0, 1, 0, 1, 1, 1, 1, 0. For this I am taking the example of HD. So on HD, you would be having once again only corner atoms. So average number of atoms is nothing but 1 by 2 into 2. So density will be 1 by root 2a. Here comes the most interesting and the last calculations, which are having this HB. This time this is a diagonal. So you would be having corner atoms, body center atom, corner atom. So average number of atoms will be 1 by 2 into 2 plus 1. And density will be 2 by root 3a. Root 3 by root 3a. 2 by root 3a. Clear for everyone? We have completed all the calculations, guys. Shovik, GATE is always asking numerical only. GATE is not asking from theory. That's why I said whatever I am telling you, today's marathon is a subset of ESC syllabus. Okay, it is, you can say, the 50-60% of ESC syllabus. Okay, rest ESC is having ceramic, polymer, then ferrous material, non-ferrous materials, then nanomaterials. So ESC is having quite big syllabus. GATE is asking from these things only. Okay, so last time you can see previously they were asking from phase diagrams. For the first time, last time they have asked one question from volume density. So they can also enter into planar and linear density calculations. So my dear, now I am making the tables. Here I am telling you about the vector. Then I am telling you about the FCC calculations and BCC calculations. For vector 0, 0, 1, you have seen FCC was having 1 by A, it was also having 1 by A. For the vector 0, 1, 0, sorry 0, 1, 1, 2 ones and single 0. Here for BCC we are having the calculation as 1 by root 2. For FCC we have calculation of 2 by root 2. 2 by root 2A, 1 by root 2A. For 1, 1, 1, here we have 1 by root 3a, here we have 2 by root 3a. Can you tell me where we are getting the maximum densities? Can you tell me where we are having the maximum densities? Can you tell me where we are having maximum densities? Maximum densities. You can see here the maximum density will be coming here. Here maximum will be coming here, just opposite. Previously this was for BCC, this was for FCC. This time this is for BCC, this is for FCC. Is it clear or not? Please tell me. Is it clear? Is it clear? And when I say 0, 1, 1 means all those planes where 2 1s and single 0 is there. So my dear, I would like to tell you here one important thing, that these directions where density is found to be maximum, we are calling it as closely packed direction, or we also call it as slip direction. So these are the direction where we are finding out the maximum density. So the number of atoms as the density is maximum, as the density is maximum, as the density is maximum. So my dear, I would like to say atoms will be closer to each other. So as atoms are closer to each other, the gap between atoms is very less. So it would be very easy to move the atoms because they are feeling instability. So that's why we would be having that more slip, more ductility. So whenever we are going to define here, we are having something called as number of slip systems. So number of slip system is defined as a product of number of closely packed planes into number of closely packed direction. If you will download the notes of material size from my Telegram channel, there I have even mentioned the total number of planes and directions in different cases. But here I will just tell you which one is bigger. So when we go for the number of slip system, so number of slip systems are found to be more for FCC than that of HCP. As the number of slip systems are more for FCC, less for HCP, so we are calling FCC to be more ductile and HCP to be less ductile. So now I feel you are understanding why HCP is less ductile than FCC. But when we are finding out for BCC, the trend reverses. For BCC you are going to have the highest, but still it is brittle. Okay, I already told you that whenever we are going for material science, its nature is similar to chemistry. Exceptional things are there. So if the number of slip system is the criteria, then BCC should be more ductile. But here BCC is coming out to be brittle. What is the problem actually? So my dear, whenever slip is what? Slip is movement of atoms. So when atoms are moving, let us say you are moving somewhere. Okay, let us say there is a classroom and you guys are going to appear in the exam, and you know I am going to be the examiner. So you know sir is very strict. Sir will not allow us to cheat. Okay, if normally you will see the number of seats, the seats are arranged like that. This is the gap for movement of the teacher or examiner. But let us say the school peoples or the college peoples are saying that students' choice it is how they want to sit. So what you will be doing, you will be making the arrangement in such a way that my movement will be difficult. You will be putting one bench here, other bench here, other bench here, other bench here, one bench here, other bench here, other bench here, other bench here, other bench here, like that. So when you will be putting randomly the bench, now if I see this student is going for cheating, it would be very difficult for me to reach here. Until I will reach, that student will do whatever he want to do. So for me it is going to be very difficult to move because of this randomness. And here we have the clear path. I can very easily move and catch the cheating. So my dear, in BCC, yes, more number of slip planes and directions are there. But they are randomly oriented. Like if one is there, second is there. So if atoms are moving here, they are not getting the path further. Because this is not in the continuation. You are going to have random paths. So when paths are random, it is going to be difficult for the slip to move. So because of the randomness, although it is having more number of slip system, but because of randomness, it is not ductile. That is why BCC are found to be brittle, FCC is found to be more ductile, HCP is found to be less ductile. With this, crystal structure is over. Is it clear for everyone? Please tell me that. That kind of explanation you will not find anywhere else. Crystal structure is over, guys. First chapter is over. Now we are moving to some of the questions, then we will go for crystal imperfections. I told you na, in material science we will also see some questions. What is the volume of FCC in terms of atomic radius? You know volume is nothing but A cube, and you know that A is 2 root 2r for FCC. So can you tell me the answer? This type of questions will be there from material science. Very good, Malesh. So do like and share the session, guys. I hope you guys are getting it. What would be the answer for this question? Arithro is saying A, Abhi is saying B. When you will be putting this 2 root 2 r ka cube. 2 ka cube will be 8. Root 2 ka cube will be 2 root 2 r cube. I feel B is the right answer. B is the right answer. Very good, Ritik Kulavi. Very good, Mahesh. Wonderful answer will be B for this. Very good, Ashray. Moving to the second question. Very good, Malesh, Bora Prakash. Second question. What is the linear density for FCC 100 in terms of the atomic radius? So what is the, first of all, you know 100. 100 is this. For FCC only corner atoms are there. So 1 by 2 into 2 is the average number of atom. Density is 1 by A. You need to write in the form of radius. What would be the answer? Very good question. This is how questions will be coming in GATE this time. You will find. B is the answer. 2 root 2r, because you know it is 2 root 2r. Okay. If you have attended the part clearly, every question you can answer. Okay. Defect we have not studied yet. The coordination number. Coordination number. The correct order of coordination number of simple cubic, BCC, FCC, HCP. Simple cubic, BCC, FCC, HCP. Six for simple cubic, 8 for BCC, 12 for FCC, 12 for HCP. B is the right answer. Every question answer is B. Moving to the next question, guys. Yes, this is the next question. In a simple cubic lattice, D is the interplanar distance. D100, D110, D111. Interplanar spacing. The ratio you need to find out. Solve it, guys. So crystal imperfection we will be completing by 2 p.m. and then we will have the break of 30-40 minutes. After that we will have strengthening mechanism, phase diagram, iron carbon diagram, and then we will be having at the end nothing but the last part, that is heat treatments. So journey will go till heat treatments today. Okay, Ajay is saying A is the answer. Very good, Bora Prakash. So when you will be going for D100, answer will be A by 1 ka square, 0 ka square, 0 ka square, it will be A. D110. D111. So if you will be taking the ratio, A is to A by root 2 is to A by root 3. Multiplied with root 6. Answer is A. Nahi Shovik, till now we have completed casting, welding, sheet metal operation. This is material science going on. So we are left with metal forming, metal cutting, metrology and sim. Okay. Atomic packing factor for copper. Atomic packing factor for copper. Atomic packing factor for copper. Try to solve it. Yes, 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 solve it. Very good. As you know, copper is FCC structure. For FCC it is 0.74. Very good. Okay, effective number of lattice point is the average number of atoms. 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 Okay, very good guys. So answer for this is effective number of lattice points. Simple cubic 1, BCC 2, FCC 3. Sorry, 4. So 1 to 4. B is the right answer. 1 to 3 nahi Ajay, 1 to 4. Okay, FCC is having 4. Okay, fine guys. Now let us move planar density. Planar density for this, I feel we have already seen this. Planar density for 100. Planar density for 100. Planar density for 100. Very good, Abhishek. For 100, you know, it would be having corner atoms and face center atom. So planar density will be 2 by a square. B is the right answer. 2 by a square. Arey bhai, it is for FCC na? 1 by a square is for BCC Strayers. C is for BCC bhai. Make corrections. Okay, very good. So answer is B only. So fine guys, likewise there are many questions we can go. Okay, there is no limitations on the questions. So you can see we have completed the crystal structure in last less than 3 hours. You won't believe, when I teach in the paid course, it takes 8 to 10 hours. Crystal structure I teach for 8 to 10 hours. Now we have completed in before 3 hours because we are revising the things. So you can say 10 hours means 1/4 of the material science is over. No more than 1/4. Okay, because 35 hours are the maximum for ESC part. So when we are talking about the next thing is structural imperfection. We also call this as crystal defect. So when we are talking about the crystal defects or crystal imperfection or structural defect or structural imperfection, here many students are having the doubts. Sir, if we are not having a perfectly crystalline structure, we are thinking it is amorphous. So having amorphous structure is said to be crystalline defect? No. Actually, whenever we are having crystalline means 3D long range periodicity of atoms, molecules and ions is giving us crystalline structure. And if that is not there, it is amorphous. But if we have 3D long range periodicity, but in between some short range deviations are there. Like let us say I have a class of 5,000 students. Every chair is having a student. But out of these 5,000, 3 students are absent. So in 5,000 chairs, 3 chairs will be empty. So because of those 3 chairs, I will not say this is amorphous structure. This is crystalline only, but with some short range deviations. So whenever short range deviations are there, we call them defects. Long range deviation, we call them amorphous. So this is how amorphous structure is different than the crystalline defect. Now my dear, whenever we are talking about the crystal defects, they are always present even at room temperature. Because whatever the calculation we have done in the first chapter, we have assumed the atom to be present fixed at their position. But in reality, atoms are always vibrating even at the room temperature, and that vibrations are said to be phononical vibrations. So even at room temperature, you would be having atoms to be vibrating like that. To be vibrating like that. So atoms are vibrating even at room temperature. So when they are vibrating at room temperature, you cannot have the distance between the atom to be fixed. And if the distance between the atoms is not going to be fixed, it means my dear, as they are vibrating like that, it means my dear, you can never have the perfect line, perfect crystals. So you will never be getting the perfect crystalline structure. Always the structure you would be having some short range deviation. So even at room temperature, short range deviations would be present. So even at room temperature, short range deviations would be present. So even if they are present at room temperature, we cannot get the perfect crystalline structure, that is for sure. Okay. So my dear, if we cannot have, the point is, if a perfectly crystalline structure would be there, according to Dieter, its strength will be 1000 times than the presently available material. So if presently available material is having this much strength, then 1000 times strength would be there for a perfectly crystalline structure. That was said by none other than Sir Dieter. Now practically we cannot see that, because you would be having those vibrations to be 0 at 0 Kelvin, which is unachievable. So that is why, as we cannot get the perfect crystalline structure, we will try to control the imperfection in such a way that we get somehow better properties than the presently available material. And for that we are going for alloy formations. So when you are saying the alloys are stronger than the metals, they are from the available metal, not from the perfectly crystalline structures. Okay, so that is why when we cannot perfectly or completely remove the structural imperfection, we will try to control them, because if we will be controlling them, we can at least adjust some things from that. So my dear, when we are talking about these structural imperfection, they are divided into four categories. One is said to be point defect, other is said to be line defect, third is said to be surface defect, fourth is said to be volume defect. Volume defect will be casting, welding and forming defect, that we have already studied. Casting defect, welding defect. Okay. Then my dear, when we are talking about point defect, they are also said to be zero dimensional defect. Then we are talking about line defect is also said to be 1D defect. Surface defects are also said to be 2D defect. If question will be coming from the theory part, 99% will be coming from this part. So when we are talking about the point defect, then my dear, point or 0D defect, they are classified in further categories. Like the very first one is vacancy here. Second is self-interstitialcy here. Third is we would be having impurity here. Fourth is we would be having the Frankel defect. Fifth is we would be having the Schottky defect. So my dear, first we will see these defects. After that we will come on to the line defect. Line defect is also said to be dislocation. There are two types of dislocation, edge and screw dislocation. Then surface defect, we are having grain boundary, low angle tilt and twist boundary, twin boundary and stacking fault. With that the chapter will be over. So we are going for one by one. More important are line defect and 0D defect for the gate examination. So when we are talking about the perfect structure, you can see here atoms are present at all the places. This is the perfect structure. Okay. What is vacancy? If any of these, let us say this atom is going to leave the space, then here some vacancy will be there. That is said to be the vacancy defect. So if one atom from the crystal structure is leaving its space, and where it will go actually, when it will leave this space, where it will go? You know, this is not the real picture. Real picture is atoms are always in contact like this. This is like this. Atoms are in contact like this. You know that. And whenever we are saying atoms are in contact like this, so you know, as atoms are considered to be sphere, you will always be having some void space. My dear, this void space is said to be interstitial site. So when we are going to talk about the interstitial site, generally whenever a atom is leaving its place, it is trying to enter into some of the interstitial site. And you know, this gap is smaller than the atom size. So when that atom will try to enter into that, it would definitely be putting other atoms to move by some distance. Because of that, randomness will be coming nearby regions. So whenever the defects are coming, they are going to increase the randomness. And as I said, if the randomness will increase, movement of slip will become difficult. And if that is happening, strength of the material will be improving. So whenever we are talking about the very first defect, that is vacancy, whenever this vacancy is going to be there, atom will be leaving, atom will be going into some of the interstitial site. And when the atom is going into some interstitial site, we call that defect as self-interstitialcy. So if vacancy is happening, obviously self-interstitialcy will be happening. But the condition for self-interstitialcy is, if let us say this atom is leaving its place and it is going to be in the self-interstitial site in its neighborhood. It is like you are leaving your room and you are going to live in the hole of any other neighbor. So that is said to be, whenever this atom is leaving the place, it is vacancy. Moving to the interstitial site of the neighborhood, it is said to be self-interstitialcy. Okay, is it clear or not? Please tell me. Yes, Arithro. If you remember, that's great. I will show you with the diagrams, don't worry. Like this is the case. This is the perfect crystal. Here this atom is not present. So that is said to be vacancy defect. That is said to be vacancy defect. Now my dear, here all the defects are shown. You can see here the atom is not present, it is vacancy. Now my dear, whenever this atom is going to enter into the interstitial site, we call it as self-interstitialcy. You can see this atom is moving to this interstitial site, we call it as self-interstitialcy. Self-interstitialcy. If you are having the iron crystal, then this is the same iron atom which is going into the interstitial site. And my dear, whenever you are going to have vacancy and interstitialcy together, whenever you are having the vacancy and self-interstitialcy together, we call it as Frankel defect. So I feel previously I have said something which you may be getting confused. So I am telling you that vacancy can be anywhere, self-interstitialcy can be anywhere, but when they are coming together, we call them as Frankel defect. Here you can see this atom is moving to the neighborhood of others. We call it as Frankel defect. So whenever atom is leaving its place, it is vacancy. It is moving into some interstitial site, it is self-interstitialcy. If they are together, it is Frankel defect. 3 defects I have explained. Now my dear, the next defect is the impurity. Impurity is very important. So whenever I am telling you impurity, so I will be giving you an example of your home. Like in your home, if 8 people are living, 2 your parents, 2 your grandparents, 4, and 2 your brother sister, okay, they are 3 your brother sister, 7, and let us say 1 servant is there. So if 8 people are living in a home, any 9th person is assumed as the guest, and guest in material science is referred as impurity, because that house or home is related to those 8 peoples. If any 9th person is coming, that is acting as guest, and in the material science language we call it as impurity. Now my dear, whenever guests are coming into your home, guests are of 2 types. One type of guest where you need to give respect plus love, like your mama ji, your chacha ji, your tau ji, your uncle, your auntie, whatever. And there are some kind of guests where you just need to have love, there is no respect for them, like your friends. So when you have only love, no respect, then my dear, let us say you are living in such a way that you are having one room with your 2 parents, one with the grandparents, one with the brother sister, one is yours, you are special, and one is servant room. This is the common area. Here also some arrangements are there. So if this person is coming, your friend, where you have love but no respect, if that is coming to your home, and your father will say, beta, today your friend is living here, so you do one thing, you live in the hall and your friend will be living in your room. You will say, why? If he is my friend, he can also sleep in the common area. Why? Because you don't have any respect for him. Okay? But if you are talking about the Mamaji, if Mamaji is coming, then you would be by default going to the common area and you will say, Mamaji will sleep in my room, because you have respect also. So the same behavior is shown by the materials. But material don't have any Mamaji or friend. Material have simple criteria: more power, more respect. And power is related to size here. If in the iron lattice you are putting carbon atom is smaller in size, then iron will say, I will not leave my space, sorry, you go to the interstitial site. So as carbon is smaller than iron, it will be going to the interstitial sites. And when it is going to interstitial site, such impurities are said to be interstitial impurities. Interstitial impurities. And whenever a atom is coming with the bigger size, then my dear, iron have to leave its space. Like you can see here, iron have left its space for the bigger atom, and this is said to be substitutional impurity. Like Mama ji have substituted you from your room, here this bigger atom has substituted the iron from the iron place. And here you can see when the small size impurity is coming, it is trying to adjust in between the interstitial sites. That's why here you can see the randomness increased, because it is entering into the interstitial size of these 4 atoms. So when it is entering, all atoms have to displace by some amount. Because of that, here you can see some randomness increases. So my dear, this is about the impurity defect. Please tell me, everybody understood about these defects or not till now, whatever we have discussed? So we have discussed all the defects. Point defect, only one is left. I already told you that point defect, this defect chapter will not take much time. Okay. So now my dear, we are going for the next defect. I already told you this is vacancy, this is self-interstitialcy, okay, and you can see this is substitutional impurity, this is interstitial impurity. I feel these diagrams are explaining everything to you. This is vacancy, self-interstitialcy. This is substitutional impurity, interstitial impurity. Now my dear, we are entering into the last defect, that is said to be Schottky defect. So when we are talking about the Schottky defect, it is happening in the ionic solids. Like we have NaCl. So you know, whenever we are talking about NaCl, Na is having 281 electrons, Cl is having 287 electrons. So chlorine require 1 electron in the outer shell, and sodium wants to leave it to have the octet rule. So my dear, because of that, sodium leaves this, chlorine accept this, and they make the ionic bond between them. But whenever some energy is coming to sodium and chlorine, sodium have given the electron and it is going to leave the site, and chlorine also leave the site. So this pair, after taking the energy, because when energy is coming, bonds will break. So when you are going to heat the crystal, you are going to provide the energy to the crystal, the bond between NaCl will be breaking. Na positive will be getting smaller in size because 1 electron have gone, and chlorine is also having the negative charge. Overall charge neutrality is maintained because the number of positive and negative charges are equal. So entire crystal, entire material will be having neutral charges only. But when we are talking about Na and Cl, they will be leaving their space. It is just like vacancy in the ionic solids. Okay, so this is said to be the Schottky defect when it is vacancy happening in the ionic solids. And here a formula is also defined whenever we are talking about the number of vacant site by number of the total site is given as e to the power minus Ea by RT. Okay, by KT actually, not R, we are using KT. So what is that actually? I am telling you. So here you are talking about NV is the number of vacant site. When we are saying number of vacant site, it means one vacant site means one Na and Cl. One vacant site means one Na and Cl. And this is the number of total sites. Total Na and Cl. Ea is the energy required to break one bond between Na and Cl. K is the Boltzmann constant, T is the absolute temperature. So my dear, whenever we are saying all these defects, vacancy, self-interstitialcy, Frankel defect, Schottky defect and impurity, all these defects whenever we have studied, they are formed because of the thermal excitation caused by external heating. Because for all these, breaking of bond is required. And when we are going for breaking of bond, energy is required. So when you will provide energy, then only these things are going to happen. Is it clear for everyone? Then my dear, whenever we are talking about impurity, impurity defect is happening because of the impurity added to the components. Sometimes we are adding the impurities, let us say, with our concern, like intentionally. Sometimes they are coming by default. So here we are talking about the intentionally added impurities. Okay. So when we are talking about this is going to improve the effect of alloying element. If you are talking about the effect of these impurities, generally they are increasing the strength of the material because they are increasing the randomness. When randomness increases, strength of the material increases because it is difficult for the slip to move. So that is why they are good for the strength. Okay. Moving further, guys, we have completed this. Moving to the second defect, that is dislocation. Clear for everyone? Clear for everyone? Are we ready for the second defect, guys? Okay, now my dear, second defect we are calling it as line defect. So my dear, whenever we are talking about the line defect, they are also known as dislocations. They are also known as dislocations. And dislocations are categorized in two types. One we are calling it as edge dislocation, other we are calling it as screw dislocation. So we would be saying one as edge dislocation, other as screw dislocation. So my dear, it is the general philosophy that whenever we are going to have the point defect present more than once at one place, if we are having point defect present more than one time at one space, it will result into line defect. Like I am showing you. Let us say I am going to put the atoms like this. Just try to understand, this is important for gate. Okay, but I will not be making like that. I would be making it in different way. I would be making like this. Because I need to make you understand the diagram. So we are having atoms like this. Like this. Like this. So guys, first of all, you can see in this diagram whatever I have made. Here can you see that we are having one vacancy here, other vacancy here, other vacancy here. So we are having three vacancies present together. So we are having three vacancies present together. Whenever we are going to have more than one vacancy present together, vacancy is a point defect. So more than one vacancy means we are having this as a line defect. So we are having this as a line defect, and my dear, what will happen because of that? In 3D, if I will show you, in backside also atoms will be present like that. You can feel it. Okay, like that. And if you see this line, below this, we are having this atom absence. Above this, everything is fine. So because here atom is not there, the gap between this atom and this atom will be quite more. So whenever two atoms are away too much, attraction is more between them. So because of that attraction forces, they will have a tendency to move in this way. They will also have a tendency to move in this way. They will also have a tendency to move in this way. And movement of such atoms, we are calling it as nothing but what? We are calling it as what? We are calling it as what? This is nothing but the slip. So that's why this part is said to be the slipped part. And this part is said to be the unslipped part. And the line which is going to separate these two parts, we call it as dislocation line. Dislocation line. And you can see dislocation is going to happen in this way, in this way, in this way. So if you see the direction of dislocation and you can say the direction of slip is perpendicular to the dislocation line. So direction of slip is defined with a vector known as Berger vector. and here we can say Berger vector is perpendicular to dislocation line. This is the question which is coming in the gate, and it is, you can say, in upper plane atoms are present and lower plane atoms are not present. So this is represented like this, and we are calling it as positive edge dislocation. Positive edge dislocation. And if you would be having the opposite case, like atoms are present here and not present in the top, then we will be making it like this, and this is said to be negative edge dislocation. Everybody is clear about this or not? Please tell me that. Everybody is clear about this or not? Please tell me that. So this is how we are talking about positive and negative edge dislocations. Now my dear, whenever we are talking about edge dislocations, you can see like this is the atoms are there, this is the atoms are not present. So in a crystal lattice there are more than one edge dislocations are possible. So I would like to tell you, like here also two positive edge dislocations are repelling each other, positive and negative will attract each other, and negative will repel each other. So here the same type of edge dislocation repelling each other, opposite are attracting each other. And my dear, whenever they are moving we call them as slip. So this is about the edge dislocation. So my dear, when we are talking about the screw dislocation, I am explaining it with a normal example, but that is just to explain, that is not the reality. Okay, let us say we are having some cylindrical plane of atoms present like this. Let us say we are having some cylindrical plane of atoms present like this. And in that cylindrical plane of atoms, obviously atoms would be there. Like atoms are there everywhere, you can say. So why I am making it in the cylindrical format? Just to explain you. You know, here if you are going to move one round, after one round you will reach to the same place. So my dear, if I am going to apply some shear distortion here, because of shear distortion, this cylinder may get converted into the surface of helix like this. And you can see it was the level. So this part is going above. So this is said to be slipped part. And this part is said to be unslipped part. And this time slipped and unslipped part are separated by this line. This line is said to be dislocation line. And you can see movement of atoms are happening perpendicular to that, sorry, parallel to that. So we will say this time Berger vector is parallel to the dislocation line. I am showing it a very simplified manner. Okay, if I will go by atom to atom, it would be very difficult and time taking. For gate, they will never be asking you to make the diagram. So that is why we can directly remember that in edge dislocation, Berger vector is perpendicular to the dislocation line. And in screw dislocation, Berger vector is parallel to dislocation line. Sir, please make a session on how attempt test like virtual. How to attempt okay. How to attempt test. Now I feel the exam is coming. So how to attempt the exam it should be. Okay. So everybody have seen the virtual calculator session. Everybody find it useful or not? Please tell me. So this is the one point from where question will be coming. Okay. Now my dear, we are having one more important point. What is that? The other important point is, great. Other important point is कि for edge dislocation you have seen some atoms were moving, but for screw dislocation entire planes of atoms were moving. So when entire planes of atoms were moving, here I said planes of atoms were moving, here I said atoms were moving. So where you need more energy, obviously here you need more energy. So this defect is occurring at high temperature and this defect is occurring at low temperature. This is one more thing related to dislocations. Is it clear for everyone? Please tell me that. Is it clear for everyone? Please tell me that. Is it clear for everyone? Please tell me that. Clear for everyone? Please tell me that. Yes. Wonderful, Lemon. Fine. Is it clear, guys, for everyone? So these are the points from which questions can come from you in the gate. With this, we have completed the dislocations. You can see the reality. Okay, from 9 January already, marathons are going on. They are about to complete in 1-2 days. This is the example of edge dislocation, and this is the example of screw dislocation. You can see the shifting of plane, entirely shifting of plane. So when this plane is moving, entire planes are moving, na? So all the atoms are getting moved. Here some atoms are moving. You can see here. Okay, so this is said to be the edge and screw dislocation. Edge dislocation. Okay, this is what we have seen. So they have already shifted. So you can see some atoms are shifting like that. But in the screw dislocation, entire planes are shifting like that. Okay. So next we are moving for the surface defects. So guys, we are entering into the last type of defects. Okay, I feel we are having the time even to complete some strengthening mechanism before break. Okay, so let us see if possible. That it will be wonderful thing that after break we will go for phase diagrams only. Then my dear, whenever we are talking about the surface defect, the very first surface defect we are talking about is the grain boundary defect. So whenever we are talking about the grain boundary defect, what it is, as you already know, if we are having the liquid molten metal here, I am making a bigger diagram for that. It is a very important for the conceptual point of view, for understanding point of view. So whenever we are going to have the molten metal present here, it can be any molten metal, let us say, and this is the casting happening, and in the casting you are looking for the solidification now. So you know that these are the mold walls. They will be cooler. Molten metal is the hot. So that is why the solidification front will be starting from the surface. From here solidification will start. Here solidification will start. Solidification will start. Solidification will start. Solidification will start like that. So if you have taken the water someday into the refrigerator and you are going to make that ice, you must have seen whenever that ice is not completely formed and electricity gone in between. You take that bowl of water outside and you put the finger in that, you will find in between water is there, outside ice is there. Why? Because solidification front is coming from here. So if in between it is coming towards the center. So if you are not going to allow the complete solidification, in between it will be liquid, outside it will be solid. That is what you see. So when the solidification front are coming, actually let us say the unit cells are starting forming like that. So this is the direction of orientation of crystals, which we call as orientation of grain orientation. Similarly here crystal will be solidifying in this way. This is the direction of grain orientation. Here let us say crystals will be start forming in this way. This is the direction of grain orientation. Here grain orientation is in this direction. Here grain orientation is in this direction. So like when this solidification will be happening, after some time you will see this type of grains have been formed. So grain is nothing but this region in which you have the crystal of one orientation. It is like we have the countries and states in India. Let us say the states in India. In Gujarat, Gujarati language is spoken. है ना? Likewise, we have Andhra Pradesh, Tamil Nadu. In Tamil Nadu, Tamil is spoken. In Andhra Pradesh, Telugu is spoken. Yes or no? So everywhere different language. Like let us say the example of Haryana, Punjab. In Haryana, Haryanvi. In Punjab, Punjabi. Let us say. So like there we are saying it in that way. You can also understand it in this way. Ki we are having one type of orientation of grain, orientation of crystal in one grain. So wherever two grains will be touching each other, there you will be getting the grain boundaries. Why we are considering the grain boundaries as the defect actually? Because defect we are considering here where the things are not three-dimensional long-range periodicity, where periodicity is not maintained. So you are running in Punjab everywhere you are finding Punjabi language is getting used. Suddenly you reach to Punjab Haryana border, you found there people are speaking Haryanvi also. So there you will find some mix. You will not be having the same orientation people. So that will be considered as defect, because that is not the continuation maintained. When continuation is broken, defect is there. There we are not considering it as defect, but here it is defect because the reasons are there, because when we are not having 3-dimensional long range periodicity, we call that is as a crystal defect. So where like you have the boundary between the states, similarly there is a boundary between the grain, and we call it as grain boundary. So my dear, there you will get the mismatch of language, like in the Haryana Punjab border, mismatch of language, Haryanvi and Punjabi. When you will be talking about Rajasthan and Gujarat, there would be Rajasthani, Marwadi language and Gujarati language. Then you will be having Gujarat and Maharashtra, Gujarati language, Marathi language. So you would be having at the junctions, at the boundaries, there would be language mismatch. Likewise here we will say grain boundaries are the region of orientation mismatch, because here orientation is changing. Now my dear, where there are boundaries, you know, like we have a boundary with Bangladesh, we have boundary with Pakistan, we have boundary with China. So where the boundaries are there we are always having some problem. What is the problem? Like Pakistan, China want to extend their boundary and we want to save our boundary. So in that case they are always having the fight. So we have to keep the army there. So that is why I will say in the grain boundary also, when the grains are getting solidified, this grain will try to go in this direction, other grain is try to move in this direction. So when grains are going to expand, they will be having a compressive influence. So that's why as they will be having the compressive influence, that's why we call it as the region of high energy. So grain boundaries are found to be the region of high energy. They are the region of high energy. Why? Because there they would be having extension of boundaries, that's why they will be having compression on each other, they will be applying force onto each other. So we are saying them as the high energy region, because their atoms will be coming closer to each other. Because of that, the gap between them will be lesser, atoms will be feeling instability, so energy is not lower, energy is higher. Then my dear, you know, where the border between India, Pakistan, India, Bangladesh is there, you know, Ghuspaitiye are coming from there only. Why? Because at the orientation mismatch, like whenever we go to the marriages, you have seen in the BTech you must have gone, if you are doing your BTech from the metro cities, you must be going to the marriages uninvitedly, without invitation. I also went 2 to 3 times during my BTech. One of my friend have made the record in that, went more than 50 times. So when they were going to the marriages, there was a good thing. There are two peoples. One is groom side, boy side, girl side. So whenever you are going there uninvitedly, then boy side people are thinking you are from the girl side. Girl side people are thinking you are from the boy side. So you are going, eating and coming back, nobody is going to identify you. So the same is happening at those regions, because one side people are thinking they are from the second side people are thinking they are from the first side. So it is very easy for them to enter here. So that's why we are going to say the region of grain boundaries are nothing but the heavy impurity or inclusion concentration region. Now my dear, as you know, if we are going to have a grain and grain boundary, this is having less energy, this is having high energy. So whenever some energy will be provided to this, high energy region will start melting first. So that's why the melting point temperature is always lower for the grain boundaries. So we will say they are the region of low melting point temperatures. Please tell me all the 4 characteristics are clear to you or not. Just like and share the session, guys. We are about to complete this chapter also. Is it clear or not? Please tell me that. Is it clear or not? Please tell me that. So when we are talking about grain boundaries are the region of orientation mismatch, they are the high energy regions, they are the low melting point region, they are high impurity or inclusion concentration. These are, my dear, the characteristics of a grain boundary. Now my dear, when we are talking about the grain boundary, we need to also understand which is weaker, which is stronger. So for that I am taking a slide here. Let us say you are going to have 2 same things, same component. but the only difference is one is having more grain boundary, other is having less grain boundary. Here you are having less grain boundaries, and we are having another one with more grain boundaries. More grain boundary, lesser grain, less grain boundary, like this. So this is said to be fine grain structure. This is said to be fine grain structure, and this is said to be coarse grain structure. This is said to be coarse grain structure. So my dear, whenever we are talking about grains, first of all I would like to tell you that as grain boundaries are the high melting point, low melting point temperature region. So when we are talking about normal condition, in normal conditions grain boundaries are always stronger than grains because they are high energy region. So it would be very difficult for the slip to move. So when we are talking about normal condition, grain boundaries are stronger than grains. So failure will be happening across the grains. Okay? Failure will be happening across the grains. Failure will be happening across the grains. So failure will be happening like this, across the grains. But when we are talking about high temperature, when temperature is higher, at that time grain boundary will melt out because they are having low melting point temperature. Grain boundaries are weaker, and in that case you will find the failure to happen. At that time you will find the failure to happen across the grain boundaries like this. The failure will be happening like this. Is it clear for everyone? Is it clear for everyone? So it is said to be intergranular. Intergranular. It is said to be transgranular. Now whenever we are talking about this fine grain structure and coarse grain structure. So my dear, whenever you are going to have high temperature condition, you know, at high temperature grain boundaries are weaker. So if more grain boundary, more weakness is there. Less grain boundary, less weakness is there. So it means at high temperature always coarse grain structure is better. You know, corrosion will be happening at grain boundary because that is the region of high impurity concentration. So if you have corrosive environment, we would be preferring the coarse grain material rather than fine grain structure. But under the normal conditions, fine grain structures are said to be the best one, because more grains, more grain boundaries, it will be difficult for the slip to move, because when the slip will start moving here, that slip would be arrested by the grain boundaries, and more grain boundary, more arrest. So I would like to tell you that always in the normal condition we will be preferring the fine grain structure. In the high temperature or corrosive environment, we will be going for coarse grain structure. Even whenever we are talking about the turbine blades, where turbine blade is very, very costly, we don't take any risk. We are going for single grain structure. Single grain structure, or you can say zero grain boundary structure, or you can say single crystal structure. Okay, so whenever we are going to have seawater, ship building, ship plates, we are going to make with the single grain material, so that there is no grain boundary where corrosion can happen. So depending on the application, we will be going for fine or coarse grain materials. So guys, this was about the grain boundaries. Now we are moving to the second surface defect, that is the twin boundaries. Let us say previously you were having a structure like that. 1, 2, 3, 4, 5, 6, 7, 8. Let us say 9, 10, like that. Previously you were having the structure like that. But when you are going to apply the shear distortion, then my dear, you will see some slip will be happening like this. And you would be getting, let us say I am showing on to my figure only, you will see that from here this part is getting slip. Like this. So this yellow part is getting converted into this white part. So when this is happening, this is said to be twin boundary. Why? Because this part is the mirror image of this part about these two boundaries. So we call these two boundaries as twin boundaries. Like here, about these two boundaries, we are having this and this to be mirror image of each other. So we call them as twin boundaries. Okay, with that, obviously the strength of the material will be getting reduced. Okay, so we are talking about this twin boundaries. Now my dear, the second last type of defect is surface defect, which is nothing but low angle boundaries. Low angle boundaries. So there are two types of low angle boundaries: low angle tilt and low angle twist boundaries. This is happening where more than one edge dislocation is there. This is happening where more than one screw dislocation is there. You can see here, this is positive edge dislocation. Atoms are not present below this. Okay, if I make this, that will give you better idea. So guys, just be ready. We are about to complete this, so don't worry about that. Just be there because it is important. Your presence will make energy in me, and I will go for all the topics like that. Otherwise, it is very easy to complete the syllabus by saying this is completed. So we are going to have, let us say, atoms here like that. You can see that here this is one edge dislocation, another edge dislocation. When more than one edge dislocation are coming at one place, we call it as surface defect. And when I am saying low angle tilt boundaries, what is the meaning of that? Because you can see the gap between this atom and this atom is more, so they will be getting attracted towards each other like that. Similarly, they will also be getting attracted towards each other. So because of that, there will be a shift. Like you can see here, this line was coming straight, here it is shifted. Okay, here it is shifted like that. So when they are shifting, they are making the angle that is said to be low angle. And as they are tilted, we call it as tilt boundaries. If the same will be happening because of screw dislocation, we call it as low angle twist boundaries. Is it clear for everyone or not? So these defects are said to be low angle tilt and twist boundaries, and last you can see this is the twist boundaries. Okay, so whenever we are talking about the last defect, that is nothing but the stacking sequence or stacking fault. So to understand the stacking fault, we need to understand the stacking sequence. This is the last defect we are going with. So first we need to understand the stacking sequence, then we will be understanding the stacking defect. So my dear, stacking sequence is the arrangement of atomic planes in the space. Like if you are talking about simple cubic structure, in the simple cubic structure you can see every plane. If you are going to consider it, if you are considering these planes like that, this is one plane which is having 4 corner atoms, we are calling this plane as A. Then this is the same plane A. So the stacking sequence for simple cubic is A, 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 A. Stacking fault cannot happen generally where we have only one type of plane. Then my dear, if we are going to have the second type of is BCC. Here we have BCC. So in the BCC we have 8 corner atoms and 1 body center atom. Here if you consider that there is a plane A with the corner atoms, then there is a plane with the body center atom, that is B. Once again plane with the corner atom is A. So the stacking sequence is A, B, A, B, A, B like that. Similarly for FCC it is coming out to be A, B, C, A, B, C like that. Similarly for HCP it is coming out to be AB, AB, like you have basal plane A, and plane with the 3 atoms B. So these are the stacking sequence followed by different material. And my dear, whenever we are talking about the stacking sequence, if any of the plane of atom is absent, then stacking sequence is getting disturbed, and that is said to be stacking fault. Like in FCC, I should have ABC, ABC, ABC. Let us say if in FCC I am getting ABC, AB, ABC. So you can see here C is absent. So when C is absent, it is said to be stacking fault. As you all are from mechanical, I can tell you this is going to happen if you are not going to put the chills at the proper positions. If the chills positioning is improper, then this defect will be coming into picture as per Dr. P.N. Rao. Okay, so with this we have completed the crystal imperfection. Now my dear, you tell me, is it clear for everyone? Now shall we go for the next chapter first, or shall we go for the break first? With this we have completed 2 chapters. I already told you second chapter is smaller. Now you want break or third chapter? Third chapter is also smaller. Okay, other than erythro, because erythro is starting from break from the starting. For others, do you want a break? Let us see the majority. Okay. So dear, next chapter will be taking, actually I want to take break after 2 p.m. because if it is a 6-7 hour session, so we should take the first session always bigger. So that's why I want to go for the third chapter. It will take 30 more minutes and we will take the break around 2 p.m. Okay, because once the third chapter will be over, at least 4 hour session we will go for. Second session will be smaller, you know that. So first session we have more energy. After taking lunch, some people would be having in the sleeping mode. So that's why I want to cover more in the first session. So Erythro, don't worry, 30 more minutes and I will go as per the gate point of view. So all stupid things which are not coming in gate, we will not go for that. So let us see 30 more minutes. The third chapter is strengthening mechanism. As the name suggests, we are looking for increasing the strength of the material. Okay. So in the strengthening mechanism, the thing to increase the strength of the material, the first thing is go for fine grain structure rather than coarse grain structure, because there is a formula given, that is sigma y is equals to sigma I plus kd to the power minus half. Here sigma y is the yield strength of a polycrystalline material which is having so much grains. Sigma I is the strength of a material with single grain. K is the hole patch constant, because this equation is hole patch equation. And you know D is the average grain size. You can also write this equation as sigma y is equals to sigma I plus K by D to the power half. Just imagine if you are going to have fine grain structure. Fine grain means grain size will be smaller. Smaller the grain size, bigger will be this and bigger will be this. That's why the strength is more for the fine grain structure. It is less. It is less. Shovik, I discussed in the last practice session, you can check that. I discussed in the last practice session, you can check that. Yesterday was the practice session at 9 p.m. You can check that. There I have done that question. Ha, Shovik, I was giving reply to your query only. Okay. So when we are talking about when the grain size will be reducing, the strength of the material will be increasing. Okay. So that is why fine grain is preferred. And how you can get the fine grain structure? By 2 ways. Either by adding the BCC element, because they are fine grain, they are grain size refiners, or by providing high cooling rates. Okay. So this is the first way. Second way is to do the cold working. As you know, whenever we are going for the cold working, the strength of the material increases. And that is also explained by Frank-Reed source mechanism, that is not required for our syllabus. Then we are going to do the third way, that is said to be solid solution strengthening. This is the major important thing which is going to give you the base for the phase diagram. So solid solution strengthening is the thing which we are going to see here. Okay. Thanks Arithro. So when we are talking about the strengthening mechanism, solid solution strengthening, first of all we need to understand what is LOA actually, because solid solution is a kind of LOA. So my dear, whenever we are talking about LOA, there are two terms which are creating some confusion. One is LOA, other is composite. So when we are talking about both, in both we are having more than two elements, two or more than two elements. In both we are having two or more than two elements, two or more elements. But my dear, there is a difference. LOA is nahi Shovik, till date there is no question in the PYQs from the slush casting. I said it can come in the next year gate. So when we are talking about alloys, alloys are meant for their metallic characteristic. Alloys are meant for their metallic characteristic, whereas composite need not to have metallic characteristic. Need not to have metallic characteristic. Okay, so that is why whenever we are making alloy, generally at least one element is found to be metal. Second can be non-metal, but composite can be made by two non-metals also. If you are going for other difference, alloy can be a single phase or multi-phase. Alloy can be single or multi-phase. But composite is always multi-phase. And when we are talking about multi-phase, one phase is the continuous phase, other is the discontinuous phase. Continuous phase is said to be matrix. Discontinuous phase is said to be reinforcement, and discontinuous phase is added to improve the properties of the composite. So when we are talking about composites and alloys, first concentration will be on alloy. Here I have used the word single or multi-phase. What is phase? If you have taken the laddu is having all the yellow particles, in between some orange particles are there. So yellow particle is one phase, orange particle is another. So whenever we are talking about phase, it is going to be chemically homogeneous, microstructurally distinct, and also physically separable, mechanically separable. If you are going to put a hand over the laddu like that, laddu will break into parts. So you can take orange particle separate from yellow particle. That is mechanically separable. When we are going to see orange particle, yellow particle, they are having some chemical compositions, they are having some microstructural differences. So that is how we are defining the phases. So when we are talking about the alloys, alloys specifically we are talking about the binary alloys, means two elements will be there. They can be classified as homogeneous alloys and mixtures. Homogeneous means single phase and mixture means multi-phase. Homogeneous alloys are either solid solution or compound. But when we are talking about the mixtures, they are either made up of two solid solutions, or made up of solid solution or compound, or made up of two compounds. So mixtures can be made up of two solid solution, two alloys, one solid solution and one compound. But you may be thinking, sir, what is the difference between solid solution and compound? Yes, that also we are going to see. When we are talking about solid solution and compound, then my dear, there is a brief discussion between them, solid solution and compound. Before we go to this discussion, I would like to tell you that solid solution example is steel and cast iron. Steel and cast iron are solid solution, and Fe3C, which is cementite, that is a compound. So when I say steel and cast iron, you know there is no chemical formula for steel, there is no chemical formula for cast iron. And when I am saying Fe3C, Fe3C is cementite, iron carbide, it is having the chemical formula. So first difference is solid solution don't have any chemical formula, whereas compound are having the chemical formula. Then my dear, second point I would like to say, when we are going for the solid solutions, solid solutions are made on percentage weight basis. Because you say na, if carbon is less than 2% added in the iron, we call it as steel. So it is on percentage weight basis. But when we are talking about the Compound, they are made on molar volume basis. Like when you have 2H2 plus O2, you will get 2H2O. If you are having H2 plus O2, you will having H2O2. You know H2O2 is hydrogen peroxide, H2O is water. Both are different. So you can see they are made on molar volume ratio. And second thing is, if you are changing the concentration, like if you are having 2 mole of hydrogen, 1 mole of oxygen, you are getting water. If you are having 1 mole of hydrogen, 1 mole of oxygen, you are getting hydrogen peroxide. So they are having only one fixed composition. If you are changing the composition, the compound will change. But steel will remain steel even if it is 1%, 1.5%, 1.6%, 1.4%, 1.3%, 2%. Cast iron will remain cast iron, 3.5%, carbon 4%, carbon 4.2%, carbon whatever. So solid solutions have variable concentration, compound have fixed composition. So you can see first is made on percentage weight basis, made on molar volume basis, or sometimes valency basis like NaCl. Concentration of solute is variable, molar volume ratio remains constant. Cannot given by the formula, but given by the Greek letters like alpha, beta, gamma. They are given by the formula. When you are going to make their cooling curves, cooling curve is between temperature and time. My dear, solid solutions are getting solidified over a variable range of temperature. They are not solidified at the constant temperature. In thermodynamics, you studied that isothermal phase difference, phase change is always isothermal process. But that is true for the pure substances. That is true for the metals. That is true for the compounds, not true for the solid solutions. For compound, yes, they are solidifying isothermally. But for solid solutions, temperature time curve is going to be like that. Ki phase change is not an isothermal process. Is it clear, guys? Everybody is getting? And I am telling you, this is really very important. Because in GATE, major questions are coming from the phase diagrams till date. Okay? Then my dear, whenever we are going to compare their properties, solid solutions are made by mutual dissolution. So they are found to be relatively ductile as compared to the compound. Like if you compare steel, that is relatively ductile than Fe3C, cementite. Okay? Then my dear, in the solid solution, we are calling it as, like steel is a solid solution of carbon in iron. So we are calling it as solute in solvent. But when we are talking about the compound, it is referred as, like water is a compound of oxygen and hydrogen. So in solid solution, we are saying minor element into major element. And in compound, we are calling major element and minor element. So this is how we address a solid solution and compound. So I feel everybody understood the differences. Okay. Now my dear, we are coming to the most important things, and within next 10 minutes this chapter will be over. When we are talking about solid solutions, actually what are they? Like you are going to take a glass of water, in between you are going to put the lime and sugar. It is a solution of sugar, water and lime. You put it in the refrigerator, make them solidified, it will become solid solution. So solution in the solid state is said to be solid solution. Solid solution is generally a single phase alloy. And my dear, whenever we are talking about here, we are going to add solute in solvent. So this solute is acting like an impurity. And you already have studied, impurity can be smaller in size, impurity can be bigger in size. When smaller in size, it will be going into interstitial site. Then we will be calling that solid solution as interstitial solid solution. And if it is bigger in size, we will be calling it as substitutional solid solution. You already have seen, whenever impurity atom is coming, because of that, the parent atoms have to move somewhere. Why? Because if you have these 4 atoms like this, and if some atom will try to enter into interstitial space, these have to move. Because of that, entire crystal will have randomness, because it is happening at many places. So because of that randomness, slip will be arrested. Movement of slip will be difficult, so the strength of the component will increase. So if someone will ask you how the strength is increasing in solid solution, it is not because of the solute you are adding, because of that composition. No, it is because of the randomness, and that randomness we are calling it as that the entire crystal is getting distorted. So we will say that strength is increasing because of lattice distortion. Okay, strength is increasing because of lattice distortion. Shovik, I feel I have given the example first, then I explain. Steel is a solid solution, cast iron is a solid solution. So the reason for increase in property is nothing but the lattice distortion. Reason for increase in property is nothing but the lattice distortion. Clear for everyone? Now my dear, as we know that lattice distortion is the reason for increase in the strength. So some people have said, if lattice distortion से strength बढ़ रहा है, we should add more and more impurities. When you will add more and more solute, more and more distortion will happen, which will improve the properties more and more. But the problem was, whenever you are adding sugar into water, it is having some limited solubility. You cannot add any amount of sugar into water. Like you start dissolving 1 spoon, 2 spoon, after that it will start coming out in the form of precipitation. So you may be saying, sir, but when we make jalebi and gulab jamun, we are making so much sugar to be added in small amount of water. That's why we are getting the sweet water. Yes, you are correct. But for that you need to increase the temperature. And when you are making the jalebi, it is good when you are eating it hot, because when after some time it will cool down, sugar particles will come out, because at low temperature solubility is less. So here also, if you will increase the solubility at high temperature, at room temperature precipitations will form. So the problem is solubility is not in our hand, and as the temperature will reduce, solubility will reduce. So that's why we were thinking what we should do, because we wanted more lattice distortion. So my dear, at that condition we were stuck. So some suggestions were कि we need to add more solute, we need to add more solute concentration, and second suggestion was there should be more size differences between solute and solvent, because they said if you are going to do these two things, you may get better strength, better distortion. But the problem was we were not having solubility in our hand. So at that time some researchers came, they have done a lot of research and they have given some rules to get the maximum solubility. Because if you want the maximum lattice distortion, you want maximum solubility, and that is given by Hume-Rodri. It is very important for GATE this time. Rutvik, I already said from the starting, don't worry about the hours. You see whether we are covering it complete or not. Okay, like in the strength of material, you know, session went till 10 p.m. In theory of machines, if it is not over, I am taking the second part. So the point is things would be completed. Don't bother about the time, but most probably you would be having 2 to 2.5 hours daily. Okay, that is the target. So when we are talking about the solid solution, we are looking for the better properties. For better properties, we wanted the more, you can say, more solubility. So at that time, researcher came, name was Hume-Rodri. So Hume-Rodri said that we will tell you when you will be getting the maximum solubility. Hume-Rodri did not said that we would be increasing the solubility. No. Hume-Rodri never says we will increase the solubility. They said we will tell you when you will get the maximum solubility. You cannot get any amount of solubility, but you will be getting the maximum possible solubility. It is like Carnot. Carnot did not say my engine is having 100% efficiency. He said my engine is having maximum. No one can give better than this. So the same things were said by Hume Rodri, that if you will follow our rule, you will get the maximum possible solubility. More than that, solubility is not possible. And this is important for gate this time I am telling you. So my dear, the very first factor was crystal structure factor. They said if you want more solubility, always dissolve BCC into BCC, FCC into FCC. If you will go for BCC into FCC, FCC into BCC, then you will be getting less solubility. Here many students saying, sir, in the starting you said that we should add BCC into FCC to increase the strength, but that was by grain size refinement. If you want to increase the strength by grain size refinement, yes, BCC should be added into FCC. But if you want to increase the strength by solid solution strengthening, then you need to add BCC into BCC, FCC into FCC. Second is, their relative size factor should be like that, their atomic radius should not be differ by more than 15%. Because if they will be of nearby sizes, then my dear, the void is smaller. When that bigger atom will try to enter into void, more distortion will happen. So you should have the difference in the atomic radius between two elements to be less than 15%, so that the atoms are of nearly same size, and when they enter into the void, more distortion will happen. Third is, they should not have any chemical affinity, because if they will be having chemical affinity, they are going to react with each other and they will make compound. Fourth is relative valency factor. They said if you are going to have two elements, out of which one is having more valency, other is lesser, then the element with lesser valency will be absorbing the more amount of more valency element. Like whenever we are talking about A and B, let us say A is having valency 1, B is having valency 2. Then the element of lower valency can dissolve more amount of another element. So A will become solvent, B will become solute, to give you the better solubility. Is it clear for everyone? Please tell me that. This is very important slide for GATE 24 exam. Clear for everyone or not? Please tell me that. So guys, here we have completed the strengthening mechanism. Now we will be taking the lunch break, and after lunch break we would be starting the phase diagrams. Phase diagrams plus iron carbon diagrams plus triple T diagram plus heat treatment. This much we will study after the break, and at the end we will be also discussing about the other marathons pending and the formula series coming and the math safety coming. Okay, so now we are taking the break. Composite also we will see after the break only. So I already told you that we will be taking the breaks approximately 2 p.m. Tell me how much time break is required. Tell me how much time break is required. Yes. Okay, so 40 minutes break we are taking. We will be meeting at 2:40. I feel you enjoyed the session till now. Do like the session also. Okay, so we are meeting at 2:40. So take the lunch lightly so that you can sit more, and by I feel 5 p.m. we would be completing. Okay, so let us meet after 40 minutes. Everybody is ready? Shall we start, guys? आवाज आ रही है? Am I properly audible and visible to all of you? Please tell me yes. Aritro, Vinay, good afternoon. Aniket, are we ready? Sorry for slightly long break. Yes, just wait, guys, for one more minute. So guys, actually I was having call from Abhinav sir only for a wonderful announcement for all of you. Now voice is coming, please tell me. Now voice is coming, please tell me. So there is a wonderful announcement that from Monday we are starting the last war for civil versus mechanical before GATE 2024. So the last war before 2024, civil versus mechanical, where we would be having 10 sessions for strength of materials. And guys, the students who would be attempting these all quizzes, total marks would be counted, and top 3 students would be getting a sum of total prizes of rupees 2100. Okay, this is the highest in the entire year we are going to give to top 3 students from that entire list. Okay, so you can join us 4:30 p.m. daily from Monday onwards. Okay, so we would be starting, and tomorrow would be the starting of that series. Okay, so everybody is fine with that. Now voice is coming. Ashray, Vinay, Lemon, Aniket, please tell me, and do like and share the session, guys. Do like and share the session. We are starting again. Be ready. Be ready, then we are starting. So before break we have already completed, guys, up to strengthening mechanism. Okay, nahi Aritro, this is not for all the subjects, this is for SOM only, because it is civil versus mechanical war. How we can have for all the subjects? Civil versus mechanical war can happen only for the strength of materials. Okay, the common subject. So be ready for that. And guys, now we are starting. Just let me share this so that we can start the session. If any student is going for the break, he get to know that yes, the session is restarting again. Okay, so let us move further. Okay, on app Darshan, it will be on app. On app, every day we would be having, okay, Abhinav sir and me, one day Abhinav sir, one day me, will be coming like that, 10 quizzes, and out of 10, overall 3 toppers will be getting up to 2100 rupees maximum price. So we are starting, guys. So before we go into the next topic, that is phase diagram, let us have Ashray, but it will be for SOM only, because me and Abhinav sir, we take SOM only, we don't take FM. Okay, that's why for SOM only. So before we go into phase diagram, let us have a quick discussion on the composites as well. And after this 5-minute discussion, we will enter into phase diagram. Then 4 types of phase diagram we will see, and after that we will see iron carbon diagram, and overall we will complete with the heat treatments. So guys, when we are talking about composites, composites are always 2-phase material. Like you have seen, the solid solution can be single phase, can be multi-phase, but when we are talking about composite, it is always multi-phase, and these 2 phases are called as matrix phase and reinforcement phase. So my dear, the more continuous phase is said to be matrix, and the discontinuous form is said to be the reinforcement phase. And my dear, there are 3 types of composite: particulate, fiber reinforced, and laminated. So let us see first of all particulate composite. So like, let us say you are having here molten you are having molten aluminium or copper. Here you are having molten aluminium or copper, and in this what we are going to do, we are going to add some hard phases. We are going to add some hard phases of like tungsten carbide. you are putting the tungsten carbide. Everybody know that when we are talking about aluminium and copper, their melting point temperature is less than 1000 degrees Celsius. For tungsten carbide, it is going to be more than 3000 degrees Celsius. So when you would be putting the tungsten carbide particle, they would be remaining in the solid state, in the molten aluminium or copper. So my dear, when they would be in the solid state only, but when you will allow it to cool, copper or aluminium, whatever, it is also getting solidified. And when it will be solidified, you are knowing that after solidification, what you will get? You would be getting those solid particle like this. And other than that, you are having either copper or aluminium, whatever you have solidified like this. So what is going to happen with that? Here these are available in the form of particles. We are calling it as particulate composite. Actually, whenever some crack will be propagated, let us say crack is coming, that crack will be getting resistance from the tungsten carbide, which is a hard phase. Once again some crack is coming from here, it will be resisted by the tungsten carbide, which is hard phase. So hard phases are going to resist. So in that way you can say the strength is increases. Now this aluminium and copper part, we call it as nothing but the matrix phase. These green particles are the reinforcement phase. So when we are going to say this here, what we have done is the phenomena of increase of strength is said to be dispersion strengthening. We call it that this phenomena is dispersion strengthening. Okay, so by dispersion we have increased the strength. So my dear, this is said to be the particulate composite. Now we will enter into the fiber reinforcement. When we are talking about the fiber reinforcement, what is that? You would be having a continuous phase like this. In this continuous phase, we would be having a fiber. Okay, this is the fiber. In this continuous phase, we would be having this fiber. So when we are talking about the fiber, when we are talking about this fiber, so my dear, whenever we are talking about the fiber is something which is having better properties. Why better properties? Because if you are adding something, we are adding it for improving the properties, not to reduce the properties. So if we want to improve the properties, we are adding the fibers here. So when we are adding the fiber here, then if we are adding the fiber here, fibers are always having the better properties. So we are calling this as the reinforcement phase, and rest is nothing but the matrix phase. So my dear, whenever we are talking about this fiber reinforcement, this fiber is always having the better properties. This fiber is always having the better properties. Fiber is always having the better properties. So my dear, if you want to know that how much strength it will increase, this will be depending on the aspect ratio. Now what is aspect ratio? Like you are having the length of the fiber as L, D is the diameter, then L by D is said to be the aspect ratio. So it will be depending on the aspect ratio. Okay, it will be depending on by which adhesive you are going to join the fiber onto the matrix phase, and also it will be depending upon, also it would be depending on the loading. Like if the loading is going to be like this, we call it as longitudinal loading. If the loading is like this, we call it as transverse. You can see this loading is perpendicular to the fiber, this is parallel to the fiber. So my dear, when we are talking about the formula, E of composite is given as E of matrix, V of matrix, E of reinforced, F, V of reinforced. When we are talking about for the transverse, it is EM, EF, EM, VF plus EF, VM. Here what is EM? Young's modulus of composite. Sorry, EC is Young's modulus of composite. EF is Young's modulus of fiber. EM is Young's modulus of matrix. When we are talking about small VF is the volume fraction. It is the volume of fiber by volume of matrix plus volume of fiber. Similarly, small Vm is volume of matrix divided by volume of matrix plus volume of fiber. So my dear, this is the small v. Small v is nothing but the volume fraction. So if you are talking about this, this is the formula for transverse, this is the formula for longitudinal. So it depends on loading, it depends on the strength of the fiber, it depends on the aspect ratio, it depends on the adhesive by which you are doing this all. Everybody understood this? Please tell me, guys. Everybody understood this? Please tell me that. Everybody understood this or not? Please tell me that. Yes, very good. So guys, moving to the last type is laminating composite, which is said to be cladding process. So laminated composite means when we are going to have one layer onto the other layer. Like let us say when we are talking about the kitchen utensils. When we are going to have kitchen, let us say in that utensils you want more conductivity. So you can go for the layer of copper over the aluminium. So because copper is having good conductivity. So my dear, they are manufactured by diffusion bonding process or explosive welding. And what they are doing, if you want to improve the surface property, you want to improve corrosion resistance, wear resistance, fatigue resistance, creep resistance, or surface electrical, magnetic and heat properties, then we are going to make one layer of material onto the other. Like you can go for copper clad steel for improving the heat conduction. You can also go for aluminium clad aluminium. Here my dear, first aluminium is the normal one. This is the high quality aluminium on which oxide layer will not be there. Okay, so that's the way we are going to do the claddings and all. With this we have completed this chapter and we are now entering into the next chapter, that is phase diagram. So guys, we have completed 3 chapters: crystal structures, imperfections and strengthening mechanism. Now the 4th chapter is phase diagram and 5th will be heat treatment, the last one. Okay, so we are on the 2nd last chapter. And here my dear, when we are talking about the phase diagrams, first of all we need to understand what is cooling curve, because whenever we want to make a phase diagram, then my dear, we need to first make the cooling curve. Not one cooling curve, actually thousands of cooling curves together are going to result into one phase diagram. So when we are going to plot thousands of cooling curves, then it results into one phase diagram, my dear. So when we are talking about the phase diagram and cooling curve, we need to understand the difference between them as well. So whenever we are going to make temperature on the y-axis and time on the x-axis, this is said to be the cooling curve. This is said to be the cooling curve. Okay, so when we are going to talk about y-axis temperature, x-axis percentage composition, okay, then this is said to be, my dear, nothing but the phase diagram. We call this as phase diagram. So my dear, the point is, for all the percentage of composition, we want the cooling curves. Because from the cooling curves we will get to know the temperatures. We will get to know at what temperature we are getting liquid, at what temperature we are getting liquid converting into solid, at what temperature we are getting complete solid. So if we are getting those temperature from the cooling curve, then my dear, that can be made very helpful to make the phase diagram. So without cooling curve, phase diagram cannot be plotted, and they are the experimental curves, because cooling curves you would be making in the labs only. And from the labs, after getting the cooling curves, you will be able to make the phase diagrams. And my dear, whenever we are going to make the phase diagrams, they are very helpful because they will help us to get a lot of the things. And phase diagram actually are telling us the you can say key, like which composition would be having the stable phases. Like let us say some composition A 60%, B 40%, then that composition would be remaining in solid state after which temperature, will be remaining in solid plus liquid state at what temperature range. So these kind of things you will get to know. We will get to know the cooling behavior of the material from the diagram. We will get to know there are some other factors also, like if I am having a solid plus liquid phase mushy zone, then in that how much amount is liquid, how much amount is solid. In that, whatever is the composition of liquid, whatever is the composition of solid. So all these answers will be coming from this wonderful diagram plotted known as phase diagram. So first I am telling you how the phase diagrams are plotted, and then we will be entering into other things. So let us say I want to make a cooling curves, and for those cooling curves I am going to plot temperature on the y-axis and time on the x-axis. And if I want to make a phase diagram, for that I need to make a large number of cooling curves. Let us say I am having a material A whose melting point temperature is M, a material B whose melting point temperature is N, and M is less than N. So let us say initially I am having 100% A. So when I am having 100% A, then my dear, the cooling curve for that will be coming like this. As it is 100% A, it is pure material, pure metal. Pure metal will be having isothermal phase change process. So if we are going to have the isothermal phase change process, you know that at this point it is converted from liquid to solid, and here it is liquid plus solid. So my dear, this point is said to be L0, this point is said to be S0. And my dear, both of them are coming at one temperature only. Both of them are coming at one temperature only. So this, because this is isothermal, 100% A. So this temperature is M, we know that. Then my dear, when you will be adding some B into that, okay, let us say 100% B. So curve for 100% B will be coming like this. And at that point, let us take the temperature is N. So you know this also liquid, liquid plus solid and solid. And I am saying this point is Ln, this point is Sn. Okay. Now my dear, when you are going to add, when we are going to add some B into A, then my dear, when you are going to add B into A, it will become solid solution and they will be solidifying in the range of temperature. So the curves will be coming like this. Curves will be coming like this. Curves will be coming like this. Like this. So you are going to get this point as L1, this point as S1, this point as L2, this point as S2, this point as L3, this point as S3, like that, and so on. Okay, so here we get liquid, solid, liquid plus solid, liquid, solid, liquid plus solid, liquid, liquid plus solid, and solid. This is how we are going to have that. And when you are getting this L0, L1, S, what you are getting here? You are getting two temperatures. One is this, other is this. You are getting two temperatures. One is this, other is this. So every curve is giving you two temperatures except these two. And whatever I have shown you, such thousands of curves are plotted. Thousands of curves. Okay, and these thousands of curves will be giving you thousands of points. And my dear, when you will be joining all the points from L1 to L1 to, I am showing you. Now we are going to join all the points. So I am adding one slide here. So if I am adding one slide here and you want to make the phase diagram, so what you would be doing in the phase diagram, we are having temperature on the y-axis, percentage composition on the x-axis. So we would be saying here temperature. And here percentage of B. So here B is 100%, here B is 0%. So B is 0%, A is 100% here. Here A is 0%. So you would be having 10, 20, 30, 40, 50, 60, 70, 80, 90, 100, whatever. Okay. So you have one point here M, other point here N. Now my dear, for every composition, like for 0 degree, you know L0 and S0 are coming at one point. Now for this composition, when we have 10% B and 90% A, you go two temperatures. One is L1, other is S1, like that. So like for other composition also you have 2 points, other composition also you have 2 points. So when you will be plotting all the L points and all the S point and you will be joining them, after joining you would be getting a beautiful diagram. Beautiful diagram. This beautiful diagram is said to be the phase diagram. So you can see this point will be L1 S1, L2 S2, L3 S3, and so on. Anybody have any doubt, you can ask. Everybody understood this? L0, L1, S1, S2, S3. So when we got this, this line is said to be liquidus. And above this everything is liquid. This is said to be solidus. And every point on this S1, S2, all those are going to be. So above this is liquid, below this is solid. And in between is liquid plus solid. In between is liquid plus solid. Is it clear for everyone? Is it clear for everyone? Clear for everyone? This is how a phase diagram is going to be plotted. And my dear, this zone where liquid plus solid are coexisting, this type of zone are said to be the mushy zones. Okay, so I feel everybody is understanding. So whatever this phase diagram I have plotted in front of you, this type of diagram is not coming all the times. This type of diagram is coming for a particular type of system which is said to be isomorphous system. Isomorphous system. Now you may be thinking, what is isomorphous system? So I would like to tell you, first of all, in our syllabus we are going for binary phase diagram. Binary means you would be having only two components, A and B. So my dear, if A and B are completely soluble in liquid state and completely soluble in solid state, we call such system as isomorphous system. So you may be thinking, sir, every material not show this? No. So I am telling you some of the example. For isomorphous system, you will get copper nickel, you will get Ag copper, silver copper, you will get molybdenum tungsten, and if I am not correct, they are following Hume-Rodri rule. You know, both these are FCC, both these are FCC, both these are BCC. So FCC into FCC, BCC into BCC are giving the extreme solubilities. So my dear, but every BCC into BCC will not give you isomorphous, okay? Because I said this is the maximum possible it will give. Now maximum possible can be 100%, can be 60%, can be 20% only. So that is the first type of system. Then my dear, we are having such three more systems. We will see one by one. But first, this is the first type of system in front of you. And in this phase diagram, I told you majorly three characteristics we are going to deal with. One is said to be the tie line rule, other is said to be the lever rule, and third one is said to be the cooling behavior. So from lever rule and from tie line rule, you can get numerical in the paper. From lever rule, last year also one numerical was there. Before that also in 2022 numerical was there. In 2018 also numerical was there. So here the numericals are coming a large number of times. So my dear, first of all, I would like to tell you here. First of all, I would like to tell you here as tie line rule. First of all, we would be discussing here tie line rule. Tie line rule. So when we are talking about the tie line rule, for that we would be having a constant temperature line. We would be having a constant temperature line, and obviously we would be talking about the points M and N. So when we are talking about these 2 points, this is the constant temperature line. This line is said to be the tie line. We call this line as tie line. We call this line as tie line. And my dear, if that is the case, you already can see this is the liquidus, this is the solidus. This is the solidus. So my dear, when we are talking about tie line rule, actually what this tie line rule is saying, you know that this tie line is passes from this region, and this part of tie line is there in the mushy zone. And you know, here we would be having a combination of liquid and solid. So tie line do not tell us that if you are talking about in this region, at which point we would be having how much liquid and how much solid. But it gives a wonderful thing. It says that you just take the projection of this and projection of this. These two projection will give you two composition. Let us say here we are going to get 92%, sorry, 88% A, 12% B. And here you can say, sorry, this is the point. So we are going to have 57% A, 43% B. So this point I am showing it at C dash, this point I am showing this at D dash. So you know, projection of C is C dash, projection of D is D dash. So my dear, if you are going to talk about any particular composition, let us say this, where we are going to have, let us say, some 68% of A and 32% of B. and this composition I am calling it as F. So if you are talking about at this composition, you would be having solid plus liquid. We don't know how much solid, we don't know how much liquid, but whatever liquid will be, so you can see the C dash point. This will be the composition of liquid phase. This will be the composition of liquid phase, and this would be the composition of solid phase. So guys, I am giving you some seconds, please to look at it, and if you have any doubt, please ask. Everybody understood what I said? Everybody understood what I said? So whatever the C dash, D dash I am giving, these two are the composition of liquid and solid, whatever be the amount of theirs. Okay? From this, chances of questions are very, very less. But the question is coming from the second rule, which we call it as lever rule. And my dear, when we are talking about the lever rule, like here the phases are liquid and solid. Maybe in the iron carbon diagram, the phases will be alpha, beta, gamma, Fe3, C and all. So phases, don't think it is for liquid solid, it is valid for any two phases. So when we are talking about lever rule, the lever rule is saying, like you have a line CD and this is the F. So here you can consider liquid, here you can consider solid, because it is with the liquid, it is with the solid, and you know whenever you are going to balance the moment, like in the strength of material, you write the support reaction. So the same principle you need to apply. So you would be writing the percentage of liquid. Here we are finding out the amount of liquid. So you know whenever you are having a support reaction RA, when you are finding out RA or RB because of load W, you take the distance from opposite end. If you want to find out liquid, you will be taking the distance from opposite end. You will write FD by CD into 100. Here what will be FD? The distance between these 2 points. What will be CD? Distance between these 2 points. Then what is the percentage of solid? What is the percentage of solid? For that you will write CF by CD into 100. Please tell me everybody understood or not, whatever time is required for this section only. If this you understood in the first time, then phase diagram is nothing. Then it will be completing very fast. Is it clear for everyone? Very good, Abhi. Very good, Dhanesh. Yes, Ashray, Akhil, Abhi, Dhanesh, Aritro, Lemon. Everybody understood? Very good. So guys, this is about the lever rule. Now my dear, we are going for the cooling behavior. Tie line rule we have done, lever rule we have done. Now we are going for the cooling behavior. So my dear, when we are talking about the cooling behavior, this can also be asked in the gate paper by giving you some options. So for cooling behavior, I need to take a particular temperature line, particular composition line. So I am considering this composition line, let us say. This is 1, A, B and 2. So I have 1 to A to B, B to 2. So when you will say 1 to A, when you have A to B, when you have B to 2. So I would like to say whenever we are talking about 1 to A, you know it is liquid. 1 to A we have everything liquid, and you know it is isomorphous system. In liquid state we cannot separate A and B. Whatever liquid you see there, it would be A plus B. So you would be saying this is going to be liquid and we cannot separate them in the liquid state. So it is liquid A plus B. Now it will be starting solidifying. So when it will be starting solidifying, so we would be getting some dendrites, and when you know A and B are making some solid solution, they are denoted by alpha, beta, gamma. So let us say those dendrites or solid solutions are alpha, but still some liquid is left out because everything is not solid. It is liquid plus solid. Liquid is once again liquid of A plus B. And when everything would be solidified, it would be making everywhere alpha, 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 alpha. Every alpha can have different composition because you know solid solutions are meant for variable compositions. Is it clear for everyone? Please tell me that. 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 So guys, then we are moving to the second system. Then we are moving to the second system. Then we are moving to the second system. So when we are going to the second system, my dear, second system is eutectic system. So when we are talking about type 2 and type 3 eutectic and partial eutectic system, they are following one rule only, that is said to be Rolle's law. First of all, we need to understand what is eutectic. So my dear, if in the liquid state we are getting complete solubility, and in the solid state we are having partial solubility, sorry, we are having zero solubility, we have insoluble. So when we are talking about complete solubility in the liquid state and complete insolubility in the solid state, then we call such systems as the eutectic systems. And my dear, the example of such systems are these. You can say lead arsenic, then we have tin arsenic, bismuth cadmium, gold silicon. All these are the eutectic compositions. Liquid state you will not be able to identify, solid state you will be able to identify, because in solid state they can never mix with each other, in liquid state they can never separate from each other. Like in the liquid state or solid state, when you have milk, you cannot separate milk and water. Okay, so my dear, when we have this here, how and what type of diagram will be coming, that also we will see. What type of diagram will be coming, let me see. Okay. So my dear, whenever we are talking about the eutectic system, here diagram will be coming like that. Actually there is a rule known as Rolle's law. That law is followed by all the systems, eutectic and partial eutectic, type 2 and type 3. Type 1 and type 4 do not follow this rule. Rolle's law you must have studied in 11th class of solutions as well. This law states that whenever you are going to add an impurity into a pure metal, its solubility reduces. Sorry, its melting point temperature reduces. Like initially you have 100% A. If you are going to add B into this, its melting point temperature will reduce. So when we make the diagram, we have, let us say, M as the melting point temperature of A and N as the melting point temperature of B. As you will be adding B into A, melting point temperature will reduce. As you add A into B, melting point temperature will reduce. And finally they will reach to a minimum temperature, and that minimum temperature, at the minimum temperature, the composition where we get this minimum temperature is said to be eutectic composition. And what is the beautiful thing happening at the eutectic point is, at eutectic point, my dear, the liquid is directly converting into two solids. So at eutectic point, liquid is directly converted into two solids. And this conversion of liquid into solid 1 and solid 2, my dear, this is said to be eutectic reaction. And when we are talking about the eutectic reaction which is happening at the eutectic point, I would like to tell you one thing. When liquid is converting into two solids, here liquid plus solid state is not coming. Liquid is directly converting into solids. But when we are talking about this, here we have hypoeutectic, and here we have hypereutectic. In hypoeutectic and hypereutectic, mushy zone will be there, but at eutectic composition there is no mushy zone. So my dear, here as I said, liquid state you will not be able to separate them, solid state you will be able to separate them. Here also, if the students of classroom remember, I go for wonderful stories here of your childhood, then the student of the year, then the college stories. Here I will not go for the stories, because here our target is to revise, not to enjoy. Okay, so when we are talking about this, here whenever you are going for the rules of lever rule, tie line, they are going to remain the same. Only the cooling behavior will be getting changed. So when you will be going for the cooling behavior of this part, eutectic point. So at eutectic composition, when you are going for that, you would be having two phases, 0, 1, 2. So when we are going to make 0 to 1, I am making here only 0 to 1, 1 to 2, 0 to 1, 1 to 2. So when we are going to talk about 0 to 1, you know 0 to 1 everything is going to be liquid. Here you would be getting liquid A plus B. And as they are insoluble, so my dear, wherever they are present, when the solidification will happen, as liquid is directly converting into solid, all A's and B will separate from each other, and you will be getting alternate layer of A and B. You will be getting alternate layer of A and B. You will be getting alternate layer of A and B. Alternate layer of A and B, which we call it as interlaminar A and B. Okay, so blue layer is A, green layer is B. So you can separately say these are interlaminar A and B. Interlaminar A and B. This is about the eutectic composition. Now my dear, if you see the same for the hypoeutectic, if you are going to see for hypoeutectic 0 to 1, 1 to 2, 2 to 3, then my dear, for hypoeutectic, what you will be getting? Here my dear, you know that the melting point temperature of A is getting reduced. Everybody can understand here, if I make the solidus and liquidus, this MEN is the liquidus here. And if we are talking about the solidus here is M, P, E, Q, N. Why this? Because whenever, okay, I am showing with the different color other than purple, I will show it with the white color. So you know from M, P, E, Q, N, this is the solidus. So why it is solidus? Because whenever you are going to get even 1 degree lower than M, you will be getting solid. And as here M is the melting point temperature of A, so when we are coming here, we have reduced the melting point temperature of A by addition of B. So that is why when you will be going from 0 to 1, you would be getting liquid, 1 to 2 something different, 2 to 3 something different. So I am saying it as 0, 1, 2, 3. So 0 to 1, 1 to 2, 2 to 3. So when we are talking about 0 to 1, you would be having entirely liquid. And you know this is going to be liquid AB, because in liquid state we cannot separate them. Are bhai, everybody is getting it or not? Please tell me that. Yes, Lemon, Shreyas, Akhil, Ashray, Abhi, Dhanesh, Malesh. So we are going to have liquid A plus B. And then my dear, when we are talking about here, you know the melting point temperature of A is getting reduced. So A will start solidifying below this. So you would be getting some dendrites of A. Some dendrites of A. Other than some dendrites of A, you will be having the liquid A plus B as it is, because solidification is not completed yet. But you know, when the complete solidification happens, then you know they would be already present dendrites of A, they cannot liquefy again, but all other liquid will become solid, and you would be getting some alternate A and B. So these are interlaminar of A and B. So can you tell me what changes will happen for hypereutectic? Can you tell me what changes will happen for hypereutectic? Yes, are you asking something, Dhanesh? Can you tell me what changes will happen for hypereutectic? Can you tell me what changes will happen for hypereutectic? What changes will happen for hypereutectic? Tell me, guys. A will be replaced by B. Yes. For hypereutectic, A will be replaced by B. For hypereutectic, A will be replaced by B. Only that change will happen. Yes, very good, guys. So now we are moving to the third type of system. which is nothing but partial eutectic system. So when we are talking about partial eutectic system, first of all, what are the example of this? So we have mentioned here partial eutectic system. If in the liquid state A and B are completely soluble, if in the liquid state A and B are completely soluble, but in the solid state they are partially soluble. Liquid state completely soluble, solid state partially soluble. Then we call it as partial eutectic system. And the example for that is lead arsenic. Okay. So when we are talking about the partial eutectic system, here also Rolle's law is followed. Rolle's law is followed. If you will take the material size handwritten notes from my Telegram channel, there you will see more examples are written for every system, which will help you in the exam if they are coming. So when we are talking about partial eutectic system, we are getting this type of phase diagram. Once again, the same thing will be happening as per the Rolle's law. You know that. Okay. This will be the same. But here some surprising element will be coming. We will see that. But first of all, you can write MEN is nothing but liquidus. Above this, everything is liquid. Then my dear, if you will be talking about the solidus, then I would like to say MPEQN. MPEQN. That is said to be solidus. That is said to be solidus. Is it clear? Is it clear? Fine. Oh, don't mind guys, sometimes some spammers are coming. Who is selling courses here? Okay. Fine guys. Shall we move on now? Shall we move on now? Yes. So don't bother about these spammers. They are coming in between sometimes. Okay. Who is selling course here? I am teaching you guys. So they are coming from different platforms to do all this nonsense. So when we are talking about this MEN, it is the liquidus. MPEQN is the solidus. So when we are talking about this liquidus and solidus, we are going to have this point once again, the eutectic point, but this time there is some difference. The difference is we are talking that one is eutectic, other is partial eutectic. In eutectic, in liquid state they are completely soluble. In solid state they are completely soluble. Completely insoluble. So in eutectic, you can say in liquid state, liquid A plus B. You don't know what is A, what is B. In solid state, you will clearly say this is A, this is B. But in partial eutectic, A and B cannot be A and B, because here partial solubility is allowed. Like if partially solubility is there, then this will definitely happens. Is it clear? So when we are talking about that, when we are talking about the partial eutectic system, it means there some solubility is allowed. And if some solubility is allowed, like if I say milk and water, as they are soluble, can you separate them? Can you avoid their mixing? If you are adding sugar or salt into water, you know they are soluble. Can you stop that mixing? You cannot stop. So that is why where solubility is allowed, solubility will happen. And my dear, let us say when we are saying the solid solution of B in A, we are calling it as alpha, and when we are talking about A in B, we call it as beta. And I would also like to tell you, these solid solution have some limited solubility, like maybe B in A cannot solve more than 5%, A in B cannot solve more than 3%. So my dear, definitely you would be having some maximum percentage, after that solubility will not be possible. So these curves will be coming like that. Why these curves are coming like that? Because you know, when the temperature will be reducing, solubility is reducing. When the temperature is reducing, solubility is reducing. And these lines are said to be the solvus line. These are said to be the solvus lines. Rest all the things will remain same. Thanks, Ashray. Is it clear for everyone? Is it clear for everyone? So now, my dear, we are going to have once again, like here you have beta, here you have alpha. So if you are talking about here we have liquid plus beta. Like here we have this solid, but you know that all other things are going to remain the same. But the only difference is this time A will not remain A, B will not remain B. A will become alpha, B will become beta. So that is why when you are going to make the diagrams, for that I need to take the extra slide. And I am showing you now once again the behavior. First behavior is for eutectic composition. When you are talking about the eutectic composition, I am making three cases. Because in the eutectic, you would be having this line 1, A, 2. So we are talking about 1 to A to 2. Only 2 are required. Okay. So here you would be having completely liquid. This is liquid A plus B. In liquid state, they are together completely soluble. So you cannot separate A and B. And when we are talking about A to 2, here whatever, my dear, liquid is, that is going to convert into solid, and they will be making the interlaminar. But this time we will not be having interlaminar of A and B. This time you would be having the interlaminar of alpha and beta, because A will be not present alone, B will be not present alone. So you would be getting interlaminar of alpha and beta. So everything is going to be same, only A is replaced by alpha, B is replaced by beta. Now, my dear, we will be talking about the hypoeutectic. So when we are talking about hypoeutectic this time, you know, once again, this time we will be having 3. Previously we were having only 2. So we are going to have first of all liquid A plus B as usual. But this time already some dendrite of alpha will form, because A can have some solidification with B, B can have some solidification with A. So we will never be getting AB, we will be getting alpha and beta. So you know, these alpha dendrites are forming, and rest we would be having liquid A plus B. So this and this are liquid A plus B. Now whatever dendrites are formed, they are formed. Rest will be converting into interlaminar. So interlaminar of alpha and beta you would be getting. This is interlaminar of alpha and beta. Clear for everyone? Clear for everyone? Next is hypereutectic. This time if I have, this is liquid A plus B. Now alpha will be replaced by beta. Okay, so alpha will be replaced by beta, rest everything will remain the same. Please tell me everybody is clear about this or not. After this we are entering into iron carbon diagram. So I feel by 4 PM we will complete this chapter, then 1 hour for heat treatment. Is it clear for everyone? Please tell me that. So this is about the 3 systems, entering into the two-layer systems. When we are talking about the two-layer system, these are the system for which neither two elements are soluble in the liquid state nor in the solid state. So we are having this. Neither they are soluble in liquid state nor solid state. Example is copper, molybdenum, copper, tungsten, silver, tungsten. You can see they all are BCC, FCC combinations. Solubility is going to be the minimum one there. So when we are talking about this type of system, then my dear, out of A and B, one can be heavier, other can be lighter. One can be heavier, other can be lighter. One can be heavier, other can be lighter. So heavier will be in the bottom part, lighter will be at the top part. Is it clear? So we can have this to be liquid A, this to be liquid B. So A is lighter, B is heavier. So when solidification will happen, then also you would be having, let us say, melting point temperature of A is M, B is N. So if this is M, after this, we would be having A is converting into solid. So you will be having A to be in the solid state. A to be in the solid state. A to be in the solid state. So A will be in the solid state, B will be in the liquid state. This is B, this is A. And then after some time, you would be having both A and B will be in the solid state. So you can see here liquid B is converting into solid B, here liquid A is converting into solid A. Clear for everyone? Ashray, Lemon, Danish, everybody is clear? Please tell me that. With this we have completed all the four systems. Let me take some water, because we have completed all the four systems now. We will go into the iron carbon diagram. Okay? Everybody is ready for that? Slowly we are moving towards the heat treatments. Just let me take some water. Yes guys, you will get this PDF on the Telegram channel after the session. We are going for the cooling curve for pure iron. We are going for cooling curve of pure iron, and finally that will be resulting into the diagram of iron carbon. So we are about to complete our 6 hours. So my dear, when we are talking about the cooling curve of iron, 1539 or in some books 1535 is the melting point temperature given. So before or up to that temperature everything is liquid. In liquid there is no crystal structure. Crystal structure is defined for solid only. बहुत important आश्रय इंटरव्यू के लिए, तो it is most important subject. Even engineering services, when some student will give, this is treated not as a topic but as a subject. Only GATE was having lesser weightage, but previous 2 years GATE also have increased the weightage. Previously GATE was asking alternate years, now GATE is asking every year, and last year 4 marks were given to material science. So slowly it is becoming important. So my dear, when you are going to make this cooling curve of pure iron, initially it is liquid. Then at 1539 there is a transformation take place, and liquid is getting converting into delta iron. Liquid is getting converting into delta iron. Now my dear, this first phase of iron which we are getting, it is a BCC structure and non-magnetic in nature. So my dear, this is said to be delta iron, and after that at around 1450 degrees Celsius, one more transformation happens and this is getting converted into gamma iron. Gamma iron is FCC structure, which is also non-magnetic in nature. After that, one more transformation happens and we are getting the alpha iron. Alpha iron, it is also non-magnetic in nature, but it is BCC structure. You may be thinking, sir, what is the difference between delta iron and alpha iron? Only difference is the range of temperature. Both have BCC structure, both are non-magnetic, but the only difference is the range of temperature. And when you are going for one more transformation at 768 degrees Celsius, here this alpha iron becomes magnetic. From non-magnetic to magnetic. Here if you can see, there are 4 horizontal lines. 1, 2, 3, 4. And every horizontal line is showing us isothermal transformation. When we are saying isothermal, because isothermal is extremely slow process. So when we are going for this, it is going to be a kind of you can say equilibrium is achieved. Means if on heating you are getting this, on cooling you are getting this. So it is going to be isothermal, and every horizontal line is giving us one transformation. Okay, and this 768 degrees Celsius, where magnetic to non-magnetic, non-magnetic to magnetic conversion is going to happen, we call it as Curie point temperature. We call it as Curie point temperature. So Curie point temperature is the temperature below which we have magnetic characteristics. Ashraf, for that you need to study material science of electrical part. Okay, actually in ESC paper 1 we have 2 parts of material science. How these magnetic behaviors are converting diamagnetic, paramagnetic, those things are not in the mechanical syllabus. Those things are in electrical syllabus. Okay, so for that you need to go for electrical material science part. Because for us magnetic properties are not there in syllabus. They are not important. They are not in syllabus. Okay. So in the ESC paper 1 they are there. So when you will prepare for ESC paper 1, you need to go for electrical part of material science. Okay. But right now we need not to go. Actually what happens is with that temperature, there are some orientations. They are getting changed. Because of that the conversion of paramagnetic, ferromagnetic, diamagnetic happens. And because of that magnetic characteristics are getting changed. So we cannot go into detail of that because this is the part not of mechanical, it is for electrical material science. Okay. So my dear, when we are talking about iron, as you can see, it is changing the crystal structure. Sometime it is BCC, sometime it is FCC. Okay. So our discussion is between BCC, FCC, not between magnetic and non-magnetic. So when we are talking about BCC, it is BCC throughout except 910 to 1450, and as it is 910 to 1450. So my dears, if an element is changing its crystal structure from BCC to FCC, FCC to BCC on change of temperature and pressure, then we call such property as allotropy, and we call iron as allotropic iron. And the property of showing different crystal structure at different temperature and pressure, we call it as allotropy. Is it clear for everyone? Yes, I feel everybody is getting it. So guys, when we are going to add the carbon into that, let me show you now something beautiful. Like I have shown you to make a phase diagram. Like I already told you to make a phase diagram. we need to make cooling curves. So when we are going to make the cooling curves between temperature and time, for other materials it was having the conversion of solid plus liquid. But you have seen in iron how many conversions have been there. 1, 2, 3, 4, 4 horizontal line. So in the previous phase diagram we were getting 2 points. One is L, other is S. So we were getting two curves. One is liquidus, other is solidus. Similarly, if you are going to make, this is the pure iron. When you will be adding carbon into that, you know, horizontal lines will become inclined lines. Horizontal lines will become inclined lines like that. And this time you would be getting 2 points here, 2 points here, 2 points here, 2 points here. 8 points you will be getting. So as here you are going to get 8 points, 6 points, 4 points like that. More number of points are there. So when you would be going for thousands of such cooling curves, you will get 8 points for all cooling curves. And my dear, when you will be joining them, a very complicated curve will be coming in front of us. And that complicated curve is nothing but the iron carbon diagram. But when we are talking about iron carbon, if you are going to have 100% iron here and 100% carbon here, we call it as iron carbon phase diagram. But my dear, when we are going up to 6.67% of carbon, after that we are not going to make it, we are not interested, because here we get Fe3C. After that all the structures are very hard and brittle, which are of no use for us. So majorly our concentration is only in this part of the diagram. So as you are talking about this part of the diagram, this is a part of phase diagram, so we call it as partial phase diagram. I would like to tell you that phase diagrams can be considered as the equilibrium diagram. Sometimes they are asking, is phase diagram an equilibrium diagram? Yes, because it tells the stability of various phases. So when we are talking about this, now there are two ways. Either you will show it like this. Either you will show it like this. When you are showing here, iron 100%, carbon 6.67%. Then it is the partial iron carbon phase diagram. But if you are showing here iron 100%, here Fe3C 100%, then it is iron carbide phase diagram. So the choice is yours how you are going to treat it. Please tell me everybody understood or not. Do like and share the session. From the morning 10 AM we are doing this all, and we have completed major chapters. Now after this topic we are left with only one chapter, that is heat treatment of steels. Clear for everyone, guys? Clear for everyone, guys? Very good, Ashray. So guys, this is that wonderful dangerous diagram in front of you. This is that wonderful dangerous diagram in front of you. Now like we have studied all others diagram, it is very difficult to understand in that way. So that is why I have given you how this diagram is plotted, and now I will tell you some important points, reactions, phases and lines. Only that we need to understand here. Like my dear, in this entire diagram we are having some very important point. Like you can see in this diagram, first of all, this all is liquid. Obviously it should be. Then my dear, you know, first phase of iron you were getting delta. So here my dear, we are going to have delta. So if here we have delta, you know, in between you will be having liquid plus delta. So here we have liquid plus delta. Then you know, after delta we were having gamma. So obviously the common region between gamma and delta, here you would be having gamma plus delta. Then my dear, if you are going to see this, here it is gamma, here it is liquid. So in between will be liquid plus gamma. Okay, so here you are taking Fe3C 100%. So that is why when you are going to be like that, here it is the last phase alpha. So when here it is alpha, here it is Fe3C. So overall it is going to be alpha plus Fe3C, alpha plus Fe3C, alpha plus Fe3C. So here my dear, I would like to tell you about the three important points. One point is here, which is showing us the conversion of liquid plus delta ferrite, liquid plus delta ferrite into gamma. This is the one reaction. Second reaction is at eutectic point, where liquid is converting into two solid, Fe3C plus gamma. And the third reaction is eutectoid reaction, which is converting gamma into alpha plus Fe3C. So when I have shown you these 3 points, I am showing it in the other slide. Actually, we have 3 reactions. One is peritectic reaction occurring at 1492 degrees Celsius for 0.16% of carbon. Here delta, which is a solid, plus liquid is converting into gamma. Gamma is austenite. You may be saying, sir, you were saying delta iron, you were saying gamma iron. Why you are saying now delta ferrite? Why you are saying now gamma austenite? Because my dear, now it is not pure form of iron. Now carbon is added into that. And carbon is smaller in size than iron, so it is said to be interstitial solid solution. So we will say delta ferrite is an interstitial solid solution of carbon in delta iron, where delta iron was the pure form of iron which was lying above 1450 degrees Celsius. Then my dear, this reaction is said to be peritectic. So when one liquid and one solid is converting into other solid, we call this reaction as peritectic. So peritectic is a generalized word for such reaction, where one liquid and one solid gets converted into other solid. Okay. Similarly, my dear, we have second reaction as eutectic reaction, that you already know. When liquid is directly converting into two solids, gamma plus Fe3C. This is gamma austenite. Okay. And this Fe3C is a compound because you are showing them with the chemical formula. Okay. So as you are saying, gamma austenite is a solid solution of interstitial solid solution of carbon in gamma iron, where gamma iron is the pure form of iron. You will be getting between 910 to 1450 degrees Celsius with FCC structure, average number of atom 4, and non-magnetic in nature. And when we are talking about Fe3C, as the formula is represented, it is a compound, and we call it as cementite. And you know, it is iron is in more amount, carbon is in less, so we call it as a compound of iron and carbon. This is carbon is smaller, so it is a interstitial compound of iron and carbon. Okay, and the combination of these two solid, we call it as lead-aborite. We call it as lead-aborite. Then my dear, third reaction is eutectoid reaction, where gamma alone is getting converted into alpha plus Fe3C. One solid converted into two solid. Liquid converting into two solid is eutectic. Solid converting into two solid is eutectoid. And my dear, this is nothing but alpha ferrite. Like gamma ferrite, it is alpha ferrite. The difference is only in the temperature range. Alpha ferrite is the solid solution of carbon in alpha iron, which is a pure form of iron having BCC structure, becomes magnetic below 768 degrees Celsius. And Fe3C is a compound, you know that. Fe3C is a compound, you know that. Is it clear for everyone? Is it clear for everyone? Now my dear, if you see the various solubilities of various phases, for delta phase 0.1%, for gamma phase up to 2%, for alpha phase, this is telling us the maximum solubility possible, because I told you with temperature solubility reduces. At room temperature solubility is this much. In cementite, yes, 6.67%, because at room temperature Fe3C is there, we can get that. Okay, but in alpha phase at room temperature you cannot get more than this carbon content. That's why we say the steel is going to be there from 0.008% to 2%. That's why we call it as up to this, because below this is the maximum solubility of carbon in iron at room temperature. So my dear, whenever you are talking about the composition, steel is a eutectoid composition. So up to 2% we are getting the steel. After that we are getting the cast iron. So in the steel also it is divided into two parts, hypoeutectoid, hypereutectoid. Cast iron also is hypoeutectic and hypereutectic. Okay, I feel everybody understand these things. So this diagram you cannot mug up. You need to just see the reactions, you need to see the phases, you need to see the important lines. Only that can be done. Okay, so my dear, we have already seen various points, we have already seen various temperature points, we have already seen various reaction, we have already seen the solubilities. Now only we are left with the important lines. That's great, Chandan. So we are left with the important lines. What are those important lines? So my dear, if you see, we are having a line which is at 727 degrees Celsius. If you see the dark red line, it is said to be the 727 degrees Celsius. It is said to be lower critical temperature line. If you see the lower critical temperature line, this is the temperature at which eutectoid composition is converting into gamma. So my dear, when this eutectoid composition, which is alpha ferrite plus Fe3C, is converting into gamma on heating, so this line we are calling it as lower critical temperature line. Okay. Then my dear, we are having another line slightly above this, that is 768 degrees Celsius, which is Curie point temperature, below which the composition will be remaining magnetic in nature. So that is said to be Curie point temperature line. So we have seen lower critical temperature and Curie point temperature. Now my dear, there are two very, very important curves, which is this and this. They are said to be upper critical temperature line. So my dear, this is upper critical temperature line for hypoeutectoid steel. And this is first line is A1, second line is A2, this line is represented as A3, and this fourth line is represented as ACM. ACM is nothing but upper critical temperature line for hypereutectoid. What is going to happen in these lines I am showing you when we are talking about this. Here you are having below this curve, what you are having above is gamma. Here we are having alpha plus gamma. So when alpha plus gamma is converting into gamma, can I say alpha is converting into gamma? Yes. So upper critical temperature for hypoeutectoid line is the line above which if you are going to heat the hypoeutectoid composition, then my dear, we will be getting a conversion of alpha into gamma on heating. Similarly, here if you see, you have gamma plus Fe3C, but on conversion you are getting gamma. So Fe3C is converting into gamma along this line. That's why we call it as ACM, CM representing the cementite. So here cementite transformation into gamma austenite happening. That's why this is becoming the important line. So guys, please tell me whatever discussion I have done till now, everybody is getting it or not, because I have given you all the points, all the line. Okay. So I feel everybody understood. If anybody have any doubt, please tell me. Then we are entering into the heat treatment of steels. Tell me guys. This is the equilibrium diagram which shows the stability of all the phases. Yes, Ashray, Shreyas, Lemon, Vinay, Ajay, Aritro. Please tell me. And do like and share the session if you have not done yet. Moving to the last topic, heat treatment of steels now. Very good. So my dear, when we are talking about the heat treatment of steels, before we go into that, I would like to tell you that this gamma is having wonderful property as it is FCC. You know, FCC is found to be strong and ductile. BCC is found to be hard and brittle. So my dear, I already told you, whenever we are having that alpha plus Fe3C, that is said to be perlite, and Fe3C plus gamma is said to be ledaborite. So ledaborite, perlite, these are mixtures. One solid solution plus one compound is a mixture. So my dear, whenever we are talking about gamma, it is FCC, which is desirous structure. Gamma is something said to be gamma austenite. It is FCC, so that is why it is having desirable properties. You know that FCC elements are found to be strong and ductile. Whenever we are going for metal forming operation, we need a structure which should be ductile in nature. So we are always referring the ductile materials for such cases. Okay, so for metal forming operation, for other operations, the properties we are looking for are there with the ductile materials, but not are there with the brittle materials. So that is why we always want those properties actually. So my dear, we want gamma, but gamma we cannot get at room temperature, because you can see gamma is getting converting into cementite and alpha. It is not remaining the gamma. So we wanted gamma at room temperature. For that we tried some things which later on we have given the name of heat treatment operations. So my dear, first of all, what we have done, we have taken the alpha plus Fe3C. We started slowly heating it. We reached into the gamma zone. Then this alpha plus cementite will convert into gamma. And if we want that to be uniform gamma, we have to hold it at some time. We need to hold it for some time at that temperature. So when you will be holding it for some time at that temperature, this conversion will happen into gamma. And my dear, now that gamma is the complete austenite structure, complete austenization will happen. Now my dear, when the complete austenization have already happened, now we wanted that to be at room temperature. So we thought if we will be going for a very slow rate of cooling, so that gamma do not get to know when it come at room temperature. It is like when two friends are going together, speaking with each other. They are doing some kind of conversation where how the path is crossed they don't get to know. So we thought, let's do that kind of thing with gamma. Let's have friendship with gamma. So in the furnace you were heating, you have not given any cooling. You have just closed the furnace heating. So when you will not provide the heating to the furnace, slowly furnace will cool down. And along with that, as you know, the gamma is also there. It will also cool down. So we thought with the slow cooling we will be getting the gamma at room temperature. But when we have done that, gamma coming, when these lines comes, gamma once again converting into alpha plus Fe3C. But as you were going to provide very slow rate of cooling, because of this, fast rate provide us the fine grain structure, and this will provide us the coarse grain structure. So as cooling rate was very slow, we would be getting the coarse perlite, but we will not get gamma at room temperature. So when we are getting coarse perlite, this process was given the name of annealing. This process where cooling is done in the furnace, we call it as annealing. Then my dear, we have once again tried, okay, this time we will try not with the love, this time we will go for force. इस बार जबरदस्ती करेंगे ऑस्टेनाइट के साथ. पिछली बार बहुत समय दिया था, शायद पता नहीं लगे. This time we will go very fast. This time we heated. We got gamma. For uniform austenization, we stop there, hold there for some time. Then we have taken that specimen and put it into the air, so that cooling will happen so fast that gamma will not get the time to get convert. But gamma is clever than you. Actually, nature have kept something with it. It have not given everything in the hand of human. Like you can make, the constituent of cell, but you cannot make a cell. Living cell you cannot make. Similarly, we know that in nuclear fission and fusion you can convert one element into other, like uranium is converting into barium and krypton, but you cannot convert iron into gold. If that kind of conversions are going to happen, my dear, you know what human will be doing. Okay, so we have that tendency to make the life easier. We don't think about others. We do anything to any extent. So that is why here also we tried the same. But when we are going for the high cooling rates, this time because of high cooling rates, we did not get gamma, but gamma gets converted into perlite, but this time we will get fine perlite. This process is said to be normalizing. Third and the last, when we went once again to heat and do the same thing, this time we kept it and put it with the super cooling. We have put it into the brine solutions. Then my dear, that process will give you very bad structure, because this time you have just tried to kidnap gamma. So gamma will also angry on you. So gamma will say, okay, you want me, I will come. This time you will get 95% Martensine structure, which is very hard. 5% you will be getting retained austenite, which is going to make dimensionally unstable, because of which you need to go for the tempering process to take it away. Means we don't want the retained austenite. We will convert it into martensite only again. So all these procedures are said to be the heat treatments, but we were not succeeded in that, कि we will get the gamma at room temperature. But whatever we are getting, we will try to use them: coarse perlite, fine perlite, martensite. Okay, and the last process which I define is said to be hardening by quenching. So I have not put it the any heading of heat treatment, but still we have discussed three processes very easily. So guys, we have done all the basic things. Now what is heat treatment? First of all, heat treatment is a process where we are going for heating the component up to some temperature. Then we are going to hold it depending on the thickness it have. Then we are going to cool it on the desired cooling rate to get the desired structure. And this we are going to do to get the desired property. Sometimes we want toughness, sometimes we want ductility, sometimes we want hardness, sometimes we want brittleness. Based on the demand, we will be going for it. Okay. So my dear, when we are talking about the heat treatment, first of all you need to understand that steel are of two types. One is said to be the plain carbon steel. Other is said to be the alloy steel. So if you are going to have less than 10%, more than 10%, this is said to be low alloy steel, this is said to be high alloy steel. Alloy steels are having wonderful properties because we are adding the elements as per the requirement. They are having excellent properties, but they are very costly. So we don't want costly material, we want cheap material. But we want cheap material with good properties. So for that, an idea was given that plain carbon steel plus heat treatment will give you nearby same properties and cheaper. So for that we have three categories of steel. You know, one is low carbon steel, other is medium carbon steel, other is high carbon steel. If carbon percent is more than 0.6%, if carbon percent is 0.3 to 0.6%, if carbon percent is less than 0.3%. And low carbon steel is not giving much improvement in properties with the heat treatments. Only surface hardening processes we can go with low carbon steel. So because of its mild response, it is said to be mild steel. So my dear, generally we are going to heat treat the medium and high carbon steels. Is it clear for everyone? And my dear, this with the heat treatment is getting good properties, and I would like to say alloy steels are costlier and they are becoming cheaper. So now my dear, we are entering into the properties which we can improve. You can improve ductility, you can remove the stresses, refinement of grain is possible, increasing the hardness, machinability, alteration of magnetic and electric properties, improvement in toughness. All these can be done in the heat treatment. I already told you, first of all we go for heating. The specimen is heated up to the certain temperature. Initially some stresses are relieved, okay. Then they are also saying heat treatment temperature for steel determined from the iron carbon diagram. So as I said, you will be going into the gamma austenitic range. So whether it is medium carbon steel, low carbon steel, high carbon steel, we would be having based on that some upper critical temperatures, and you would be heating them, holding it for that for some time, then you will be cooling. So this is how the heat treatment process is done. I already defined it. Okay. So when we are going for the slow cooling rate, what you are doing in annealing, then the properties like ductility and machinability improves, strength and hardness gets reduced, and residual stresses are getting removed. Okay. Then my dear, if you are talking about the cooling, here it is shown that when you are going for the slow cooling, you will get coarse grains. Fast cooling will give you fine grains. Okay. And heating will definitely enlarge the grains. Heating will enlarge the grains. Okay. So my dear, when we are talking about the fast cooling, it increases strength and hardness. It reduces ductility and machinability. And high residual stresses will be present here, because residual stresses are removed in the slow cooling, but they are not removed in the fast cooling. Okay, so this is about the fast cooling. Quenching medium which we are using in the quenching process can be brine with cold water plus 5 to 10% salt, or can be the cold water, or can be the water plus soluble, can be oil, can be fused salt, can be air. Air in case of normalizing. Air in case of normalizing. Okay guys, so now whatever I have explained, all these things are mentioned here. Like hardening process, I already told you how to perform. So my dear, when we are going for hardening, hardening can be performed on all the steels. Low carbon, medium carbon and high carbon. All the steels it can be done. Okay, so when we are talking about this, it is done for all the type of steel to increase the strength and hardness. So in hardening, object is heated 50 degrees Celsius above the upper critical temperature. Why this heating is done? To get the gamma austenite structure. And after that we are going to cool it in the quenching medium, which will be directly converting that structure into martensite plus retained austenite. That I already told you. And this retained austenite is having dimensional instability, so we need to convert it once again into either martensite or some other structure, going for the tempering process. Tempering also we will see what it is. Okay, so now my dear, we are going for something extra. This. Now there is something called as hardenability. This part I am telling you is going to be theoretical. So if you want, I can stop here also, because whatever theory is there written in the PPT, you can read it also. Last time also I taught this theory, okay? But if you want me to teach this, you need to be there, listen to me properly, because listening is always giving us long time memories. If you will be listening to me properly, it would be there in your memory for longer duration. If you will be reading, you need to read maybe 2 to 3 times to get the same memory level. So always listening is a better thing. So listen to me properly, you will be able to answer very easily the theory questions. Although heat treatment is very important, as I already told you, but questions are coming from some specific areas here. Sir, what temperature range for cold working of steels and its crystal structure alpha FCC? I did not get this. When you are talking about cold working is done below recrystallization temperature. And for that, in the metal forming, I told you that recrystallization temperature is generally 0.4 to 0.6 times of melting point temperature. So if you are working below 0.4 times of melting point temperature, it is cold working. And melting point temperature is 1539 degrees Celsius. Okay. So when we are talking about hardenability, it is ability to get hardened. So let us say I am having two materials. Let us say this is one material, this is the second material. If I am going to make both of them hard, so for doing that, I will be going for heat treatment in both the cases. I have given the same range of temperature for heating, the same time for holding, the same rate for cooling. And when I have done all these things, I found this material get hardness up to 5 mm depth. This get hardness up to 3 mm depth. So as this is getting less, this is getting more depth, I will say it was having more hardenability. So hardenability is measured by the depth of hardness. So my dear, if you are talking about this test name is Jomini hardenability test. So when you are going to check, it is the depth from the surface of specimen up to which martensite formation take place. Like here, if you see up to this much depth, martensite is formed. So this much depth is becoming hard. So I will be just measuring this depth. If this depth is more, hardenability will be more. Okay. So if you will be asking me, sir, do we get question from here? Yes. They have asked the test done for hardenability. That question was asked in 2019 for 1 mark. and the answer for that was Jomini hardenability test. Okay, so guys, now we are talking about tempering. Tempering generally is performed. Tempering generally is performed after quenching and hardening process, because we are getting retained austenite and martensite structure. Retained austenite structure is dimensionally unstable. We don't want that. So sometime we want the tempering procedures to get some useful structures. Tempering can be done as low temperature tempering, medium temperature tempering, and high temperature tempering. So when we are talking about tempering, so you know that when we are going for tempering process is applicable for mild, medium carbon steel and high carbon steel to relieve the internal stresses developed due to rapid cooling of steel. It is done to reduce hardness and to increase the ductility and toughness. It also eliminates the hardness and also increase the ductility and eliminate the retained austenite. This is the major reason, okay, retained austenite ko remove karna. So my dear, here you can see some structures are shown. This is martensite, this is truesite, this is sorbite, this is ferrodite. So when you see these properties are improving when we are moving from here to here. Okay, so I will show you based on the tempering temperature limits. We have low temperature tempering, we have medium temperature tempering, we have high temperature tempering. From 100 to 200, 200 to 500, 500 to 700. These are the limits given. Okay, these are the limits given. These are the limits given. Just wait. Yes, so these are the limits given. So my dear, when we are going for low temperature tempering, then I already told you the temperature range was 100 to 200 degrees Celsius. So we are going to have 100 to 200 degrees Celsius heating. So when we are going for that much heating, my dear, then your martensite will be converting. Your martensite will be converting and some transformation will be happening. Like you would be having the carbon percentage would be getting reduced in the martensite. And if that is going to happen, obviously you know hardness will be getting reduced because carbon increases the hardness. Okay, so you can see we would be having 100 to 200 degrees Celsius and martensite decomposing into low carbon martensite. It remains martensite, but carbon is getting reduced. When we are going for medium carbon, 200 to 500 degrees Celsius, here you can see that cementite is formed and very fine distribution of cemented particle is observed in the matrix of ferrite. The structure is said to be truesite. So here martensite, I would like to tell you martensite is having BCT structure, body center tetragonal, and this is getting converting into truesite structure. Truesite is having better properties than that of the martensite. So you will say that conversion of truesite from martensite is happening in medium temperature tempering, and when we are going for high temperature tempering, then you would be having the conversion to spherodite. Spherodite is having the excellent machinability, it is having excellent properties, so that is why high temperature tempering will give you the better conversion. So it does not mean always we require that only. There are some application where we require martensite structure also. It is not that every time we require the other structures. If you will be asking me here, I would like to tell you that have you ever gone for the shaving? Have you ever gone for the shaving? Have you ever gone for the shaving? So you must have seen that when you are going for the shaving, then you will have some razor blade. That razor blade is having the martensite structure. Okay, so my dear, whenever we are talking about the corrosion resistance of martensite structure is excellent. So if you want corrosion resistance, then also martensite structures are preferred. But when we don't prefer, then you need to convert it by going into the tempering procedures. I feel everybody understood the tempering procedure. So now my dear, here we have shown the properties which will be getting resulting. After hardening, if the strength is this much, then after tempering the strength will be this much, and after annealing the strength will be this much. So you can see strength is highest in hardening, lowest in annealing. Okay, then if you are going to compare the truesite structure and sorbite structure, then toughness is going to be more in sorbite, less in trusite. Toughness is going to be more in spheroidite than that of the trusite. And my dear, when we are talking about annealing, annealing is divided into many parts. The very first annealing we are calling it as process annealing. Second is said to be the stress relief annealing. Okay. Then third is said to be the full annealing. Okay. So likewise, annealing is divided into many parts. Stress relief annealing is only done to remove the stresses. Process annealing generally is done, like if you remember in the metal forming, whenever you study a large number of processes. Yes, Ashray, that is having hardness and brittleness, but yes, as I said, by reducing the carbon content, you can reduce the brittleness. Okay. So when I am saying razor blade, it is having martensite structure, but there are various ways to reduce its brittleness. Okay. Braid also, when you are going to just fold it, it gets broken. So brittle do not mean ki when the glass is going down, it is breaking into parts. Like blade also, when you are going into do like this, it is breaking into parts or not. Have you seen that razor blade? Whenever you are going for saloon, those peoples are using two parts of that blade two times. They are dividing it into two. One part will be used for you, other will be used for someone else. Yes or no? Yes. So when we are talking about annealing purpose, it is improving the mechanical properties, improving machinability, restore ductility, refine the grain size, also make homogeneity. Okay, all these are the applications. So first we are having the stress relief annealing. So when we are going to do the annealing only for the purpose of relieving the stress, we are heating only in this range. We are not going into the critical temperature range. Okay. So here the process is used to relieve the internal stresses. We are going heating the steel uniformly to a temperature 50 to 80 degrees Celsius below the lower critical temperature line. Here uniform cooling is most important because here we are just going to remove the stresses. So for stress relief annealing, this is the heating range. It is below the lower critical temperature. Here target is just to relieve the stresses. So heat it, hold it and cool it. Then my dear, we have process annealing. Process annealing is applied. Process annealing is applied when we are talking about to increase processability and remove the residual stresses of cold working. If you remember when I was teaching you metal forming, you have forging process, wire drawing process. I told you wire drawing process is not a single pass operation, it is multi-pass operation and it is cold working. So when we are going to convert rod into wire first, then you are going to do the process annealing in between so that the ductility is getting restored, and once again we are going to do the operation. Okay. So whenever we are going to have this process annealing, it is done with the metal forming operations. That's why the name is process annealing. Okay. Here the heating is done from 650 to 720, that is the lower critical temperature, and holding is done based on the size of the component, and then slow cooling is done. Okay. It can also reduce, like whenever we are talking about heat affected zone in the welding. Okay. So there also sometimes stresses are coming. So to reduce that, we can go for process annealing in some of the cases. Then my dear, you can see the range for the process annealing of temperature is this. Is it clear for everyone? Up to lower critical temperature. Spheroidal annealing. Okay. This is generally done to improve the machinability, and this is done in this range of temperature. Okay. This is done generally to improve the machinability. Okay. So my dear, you can see now. Heating will be enlarging the grain size. Then after that you will go for cooling, and these kind of spheroid will be forming and they will give you excellent machinability. You may be thinking, sir, from what kind of questions will be coming? Questions will be coming like, first they will say air cooling is given in which of the following process? You will say normalizing. Brine solution, that kind of questions have been there in previous years, you can see that. They can also ask you what kind of structure, fine pearlite structure we will be getting in which of the following process. So that kind of questions will be there in the GATE examination. Now my dear, there is something called as diffusion annealing, which is done from 1100 to 1200 degrees Celsius. Diffusion annealing is generally done whenever we have some non-uniform composition and you want to make it uniform. For that, high temperatures are required, because in high temperature the degrees of freedom are increases. So movement becomes easier, and then only the diffusion of one element into other can happen. So you can see that transfer of mass from high concentration to low concentration is happening in diffusion. So it is applied to medium carbon steel and high carbon steel to uniform the carbon elements present in that. Okay, it is done from 1000 to 1200 degrees Celsius. And as long as we are calling it as annealing, it means the cooling will be at the slower rate. Okay, so this is the diffusion. You can see previously we were having non-uniform carbon, we heated it, then furnace cooling will make the uniform carbon everywhere. Everybody understood annealing? Everybody understood annealing? Yes. This is the comparison of hardening, full annealing and process annealing. Grain size of hardening is lesser. Grain size of full annealing is highest. Strength and hardness is highest after hardening, least after full annealing. Ductility, machinability is going to be highest after full annealing, lowest in the hardening. Residual stresses are highest in the hardening, lowest in the full annealing. So from this also you can get a question. Okay, then we are reaching to the normalizing. Normalizing, very simple. I already told you, you are heating and then putting it into air. You will be getting fine pearlite structure. Here the rate of cooling is around 50 to 80 degrees Celsius per minute. Okay, and normalizing will give you the fine pearlite structure, I already told you. Then we are moving to this. Now you are comparing the same four things again. When you are comparing here, hardening is having lesser grain size, normalizing is having slightly better. Similarly, strength is lesser than the process annealing. Sorry, this is the hardening. This is the hardening. So this is about ductility. Ductility is less for hardening, more for normalizing, more and highest for full annealing. So these comparisons are there. We have adjusted this normalizing column in between. Now we are moving to the next process, guys. Surface hardening operations. The last one of heat treatment. After these operations, we will enter into the triple T diagram. Within 10-15 minutes, I am going to leave you. Okay, happy now? तो भाई देखो, ये part ही theoretical है, इसमें मैं कुछ नहीं कर सकता. And I can just tell you the things which you need to remember. But whatever was numerical, I have explained each and everything. Now please tell me, everybody is ready for vibration for tomorrow ना? सभी चाहते हैं ना vibration का marathon? Everybody would be there ना tomorrow? Otherwise I will not take. I will take, I want students live. Otherwise there is no meaning of taking na. Because already when recordings are available, I am taking live. It means you should come. I am not teaching you for recording this, because recording of last year are also available. So if I am taking live, I need you guys to come live. Some people are saying ना, सर मैं recording देख लूँगा. अरे फिर recording तो पढ़ी है, मैं live क्यों पढ़ा रहा हूँ आपको? ठीक है ना? I am not teaching you live for recordings. Even sometime मेरा दिल करता है कि सिर्फ live ही रहे session, उसकी recording available ही ना कराई जाए, ताकि जो serious candidate है, he will join live anyhow. Okay? Because some students are going like, कुछ इधर से पढ़ लेते हैं, कुछ उधर से. अरे जब सब आपको यहाँ अच्छा पढ़ाया जा रहा है तो सब यहीं से पढ़ो ना. Okay, fine. Okay guys, moving further. When we are talking about surface hardening processes, so when we are talking about surface hardening, if I want to just harden the surface, nothing more than that, then for that there are 5 processes. One is carburizing. Second is nitriding. Third is cyaniding. Fourth one is flame hardening. Fifth one is induction hardening. When we are going for carburizing, actually we are going to diffuse the carbon atom onto the surface. Carbon increases hardness. Sometimes we are going to diffuse the nitrogen. Sometimes we are going to diffuse cyanide, because the addition or diffusion of all these elements will increase the hardness. It will increase the hardness. Clear for everyone? Clear for everyone? So this is said to be surface hardening processes. How they are done? Carburizing can be done in the liquid form, solid form, gaseous form. So based on that, three types of carburizing is there. So when we are talking about, first of all, we will start with the flame and induction hardening. In the flame hardening, like this is the surface. First of all, I would be passing the flame from that. This is the flame. After the flame, just wait guys. After the flame, water spray is followed, and because of that the surface will become hardened. So we call it as flame hardening. And when we are talking about the flame hardening, the specimen surface is heated up to austenitic phase by using acetylene gas flame, and water spray is provided. We will get martensite structure. This process is applicable for section hardening of complex and intricate shape. And whenever we are talking about this flame hardening process, non-uniform martensite is formed on section due to non-uniform heating and cooling. So heating and cooling, if it is going to be non-uniform, it is going to get the non-uniform martensite, which we are getting from here. So that is why for uniform we will be going for diffusion and annealing. Okay. Then my dear, we also have seen the flame hardening, that we are passing the flame. In induction hardening, we are going to pass the current from the surface. Because of current, the surface will be heated. Then you are going to provide the water sprays. This time it is said to be induction hardening. This time it is said to be induction hardening. So in the induction hardening, the specimen is heated by using high frequency AC current, alternating current. And because of eddy current, heat will be produced. The hardening temperature is reached, water spray is there, and it is not applicable for complex and intricate shapes, because maybe because of current, intricate part can melt out. So generally it is used for crankshaft, gears and all. And here uniform martensite is formed. Okay. So my dear, we are going for the case hardening by addition of carbon, by addition of nitrogen, by addition of cyanide. So in this method of hardness, the surface is improved, diffusing the interstitial element like carbon, nitrogen and cyanide. Here steel for case hardening are usually made 0.18% carbon maximum, or usually 0.15% carbon steel with 3% nickel. This they are saying the composition, which is generally hardened. Okay. Now my dear, when we are going for carburizing, we are going to add the carbon, and this process is done at 850 degrees Celsius temperature. And whenever we are talking about case depth, like if you are having this, so 0.5 mm you can obtain in 2.5 hours. Okay, like if you want to obtain this case depth, so for 0.5 mm for 2.5 hours are required. Here we can do it in the form of like provide the surface with the exposure of CO2. If you are providing that surface with the exposure of CO2, carbon atoms will get diffused in the surface because of high temperatures, and we call it as nothing but the gas carburizing. Okay, if you are going to provide that in some liquid form, then it is said to be the liquid carburizing. So like depending on what you are providing. So here you can see in gas carburizing, CO2 is used. In pack carburizing, carbon paste is used. So either we have pack carburizing or we have gas carburizing. Okay. And then my dear, when we are talking about nitriding, here it is done at 950 degrees Celsius. And here we are going to add nitrogen to the surface. In the previous case, iron got reacted and making Fe3C. Here it is going to make Fe3N. Nitrogen is having more hardness than the carbon. That's why hardness provided in nitriding is always better. Okay. Then my dear, when we are talking about cyaniding, in the cyaniding you are providing both carbon and nitrogen, but nitrogen is more active and nitrogen is going to diffuse first, and then carbon will be getting diffused and will be making the surface harder. Okay, these are the properties which will be improved after nitriding. And when we are talking about application of nitriding, they are done in aeroplane engine, F1 car engine. Okay, the disadvantages are high heating temperature, I already told you. Okay, and how we are providing the cyanide. Cyaniding, we are providing NaCN plus Na2CO3 plus NaCl. Like for nitriding, we are providing ammonia gas. For carburizing, we are providing CO2 gas. Okay. Then my dear, when we are talking about this, 900 is the temperature range, 2.5 mm is the case depth we are going to get. And in the cyaniding process, when we are going to compare, low carbon steel specimen is heated up to 900 degrees Celsius, and from cyanide mixture, carbon and nitrogen, they will be getting diffused, but nitrogen diffuse first, carbon diffuse second. Is it clear? And here you can see case depth of carburizing, cyaniding, nitriding. Means you will be getting more case depth in cyaniding than, more case depth in carburizing than in cyaniding, than in nitriding. Case depth means, everybody understand, the depth of hardness. Okay. So my dear, as you know, when we are talking about low carbon steel is not saturated with carbon, so it will be able to get more and more amount of carbon. So case depth we can get more for low carbon steel than medium and high carbon steel, because that one who is already saturated will not be taking more carbon atoms. Okay, that is important. Now my dear, we are coming on to, let us say, this one question, and after that we will be entering into the triple T diagram to complete this chapter. Just try to solve it. Give me 1 minute. Okay guys, you can see this question. The binary phase diagram of metal P and Q is shown in the figure. An alloy containing 60% P, 40% Q is cooled from liquid to solid state. The fraction of solid and liquid at 1250 degrees Celsius. So the composition is 60% P. This is the line given. Okay, 1250 degrees Celsius. Okay, so you know that C, D, F. They are asking you about fraction of solid and liquid. For liquid you will write FD by CD. Upon this. Solid will be CF. CF. Can you tell me the answer? Here it is 8 by 36. (28 by 36). Everybody is getting C is the answer. Everybody is getting C as the answer. Please tell me that. Okay. Ashray, you got it. This is 32C. 68. F is 60. Okay. So my dear, actually when we are talking about this diagram which is named as triple T diagram, this is said to be temperature time transformation diagram. Actually the story behind this diagram, if you will study, that is of utmost important if you are going for GATE XC paper with material science. There is a one complete chapter which would be requiring to make this curve actually. Means whatever I taught you from the morning to till now, around 6 hours are over. 3 to 4 hours are alone required to reach into triple T diagram actually. But that part is there in GATE XC paper, not in GATE mechanical paper. And here we are preparing as per the GATE mechanical paper. So that is why how this diagram is plotted, we are not going into that. I will just tell you one thing, that when this diagram is plotted, first of all this is not an equilibrium diagram, because here we are talking about the transformations, and that will be depending on how we are going to do the heating or cooling. Like if you see this diagram, here you are having temperature in degrees Celsius on y-axis. Time is there in the x-axis, and we can show transformation in this diagram. And y-axis on the other side, sometimes we show the hardness, like they have written hardness. So here my dear, just imagine, if we are going to cool, first of all this is the temperature. Okay, let us say I am starting cooling from here, and when I am starting cooling from here, and then I am going to hold it at that temperature for very large duration, then my dear the result will be coarse pure light. And if I am going to cool it slightly on the faster rate, because it is time given, it is time given. So if I am going to cool it at the faster rate and then I am going to hold it for longer duration, the result will be fine pure light. Now my dear, when we are talking about the pure light structure, what are the applications of pure light structure? Have you seen piano? The wires of piano are made up of pure light. The suspension wires of bridges are made up of pure light. And cutting tool which are tough, they are also made of pure light. Then my dear, whenever we are going to go for more fast cooling, we would be going for, once again, going for that temperature, holding for so long, we will get bainite structure. Once again, holding for so much, we will be getting bainite structure. Here bainite name is provided on the name of a researcher, Mr. Bain. Okay, and when we are talking about bainite structure, it is used in case of, if you want to improve the creep resistance, we use bainite structure. If we want to use the wire in the power station, we use bainite structure. And if we are going for the application of welding electrode wires, then there also we are going for the bainite structures. Okay, then my dear, if you are still further increasing the rate of cooling, then you would be reaching into the martensite range. Okay, so now if you will be cooling, you will be resulting into this martensite structure. So I already told you martensite is used in the razor blades, surgical instrument, because in the corrosion resistance is more in the martensite structure, and surgical instruments are required which are having least corrosion or zero corrosion. So that's why we are going to refer that. Also sometime for turbine blades we may be going for martensite structure depending on the need. But martensite can be having different cases, like less carbon, more carbon and all. So this curve is also referred as C or S curve, because you can see this is formed like C and it is also formed like S. And if you see this S and C, one more interesting fact I would like to tell you, that this is the curve which is showing you the starting of transformation, and this is going to show you the end of transformation. And when we are going to make this curve in reality, to reach to this diagram 3 to 4 hours are required, because we are using the concept of Gibbs phase energy. We are going to use the concept of thermodynamics to reach to this curve. There are a large number of expressions required for that. Okay, in one batch I remember I taught this in 2020. Then students said, sir, why you are teaching this? We are not interested in material size XC. So from then onward I left teaching this. Okay, but if you want I can share the notes how this diagram is plotted. Okay, I am having that notes of that class where I have taught. Okay, so if you require I will give you, but no need for gate mechanical for this. So guys, with this we have completed almost complete material science as per the syllabus, but I am saying this is only a part of syllabus of ESC. For gate it is the complete, because in the ESC they are also asking you the effect of alloying element, when we add sulfur which property is getting improved. So all those things are not there in gate. We are also having the topics like polymers, ceramics, nanomaterial, ferrous material, non-ferrous material. They are there in ESC, they are not there in gate. Okay, don't worry Vinay and Aniket, I will share that. Okay, I will surely share that. Okay, so guys, here I will be leaving the session. I feel you guys enjoyed the material science. So tomorrow everybody tell me what marathon we have tomorrow. Everybody remember tomorrow marathon? Tomorrow what we have? So tomorrow we have vibration plus Tom 2. And if you would be joining this, tomorrow we will decide what to do for the rest of the production. If today, like the way you have shown the response today, if the same way response will be tomorrow there, then we will go for the production second part also. Otherwise, we will not. Okay, so that is going to be the completion of this session. So tomorrow we will be meeting at 10 AM once again to complete the vibrations and Tom 2. Goodbye for this particular marathon. Hope you guys enjoyed. You will get the PDF in next 10 minutes on my Telegram channel. Do like the session before leaving, share it with your friends and subscribe the channel if you have not done yet. And I would also like to tell you that ki marathon schedule you already have. Okay, so you can download the app, link is there in the description. Mechanical by Dheeraj Sardana is my Telegram channel. And also you can download the app and fill the Google form if you want one-to-one counseling. Goodbye.